right?
Yeah.
Yeah. Yeah. So what they've come up with, they're very clever. They say that, for example, when light goes through a diamond, let's say, right? Because they say diamond is what slows down light the most. So their excuse is, well, light doesn't slow down. What happens is it hits the individual particles inside the diamond, and it just bounces around back and forth, and it appears to take longer, but it's actually going the same speed inside the diamond or inside the material. Yeah, that's the story.
Fascinating.
Yeah,
I always
sophistry
like
to
those
plug
old
in
radios.
yeah.
Sorry, I always like those old radios where they use crystals to tune them. But a lot of times they only had like one station. But I always found that fascinating. I always thought in the future that maybe technology would develop to eventually have crystals within the circuitry. I mean, they already do to an extent, but they should develop that more. I know that that's the future.
I made one of those, bro, when I was a kid.
Word.
I made one of those radios. Yeah.
Yeah, me too. My dad bought the kit and we set it up. I was probably about 7 or 8 years old, and yeah, I got to lay in my bed and turn that thing on, and I get like 1, maybe 2 stations. Cool.
Was that cool or what? Huh? Yeah.
Hell yeah. I mean, heaven, yeah. I didn't mean to say hell yeah. Heaven, yeah.
I think I used toilet paper and copper wire. I can't remember exactly, but I think I used toilet paper, copper wire, a crystal. Yeah, and the thing worked. I was amazed.
This sounds like a DMOC experiment.
I'm amazed.
Yeah.
I'm amazed any Canadian get anything to work.
Yo, who's that?
I know, right? Yeah.
Yo, who's that trying to summon the devil?
I'm not trying to summon anybody.
Was that Napalm?
No, not trying to summon anybody. Rocky, he got it to work because he put a little bit of maple syrup on it.
Did you ever see that Gilligan
American,
Island?
he got his American friend to help him.
See that Gilligan's Island where you start receiving radio transmissions, Gilligan's fillings in his teeth?
Yo, who here got mercury
I think I saw that episode. Yeah. The professor
Mercury
was using him as an antenna or something. They were turning him. Is that the one you're talking about? Gilligan's Island?
Yeah, they had some really good scientific stuff on that show, didn't they?
Yo, how many Globers here got mercury fillings? I bet most of you guys got mercury fillings. Probably filled one.
I've got mercury fillings, but I won't say I'm a Glober. Until I see some good evidence, anyway. Yeah, I'd love to get them taken out.
I had my fillings removed during that scare time. I put porcelain. I had a couple. I took them out. Mercury poisoning and all that stuff. Yeah.
Yeah, that's smart. Porcelain is expensive, though.
I watching that. What's that guy?
Expensive.
I can't remember his name. Is it something Fox or I can't remember the guy's name? Ah, shit. I mean, his teeth are in good nick, but they're kind of yellow. And I remember watching him. He usually does nutritional stuff. And by the way, your teeth's natural color is yellow, audience. If you're young, you probably don't realize that. But yeah, this guy, I remember him saying, the only damage ever done to my teeth is by dentists. And that stayed with me, that comment. I was like, oh shit. That's interesting.
I can't say the same thing. I mean, I spent a lot of money on my teeth, fixing my teeth and working on my teeth, probably because of my American diet, but they did a good job. My dentist is all right.
Yeah, I was just, if we're looking for a topic change or something, I was just thinking about how, and I don't, if we're not, I will just join, so I don't know what's going on. But anyway, I was just thinking about, I'm waiting for Jace to join in. What was wrong with SE's? What SE said then? Speak up about the light slowing down.
Because it's game over.
Oh my god. You know, this is what I'm going to say, is that I can't speak for anyone else, but just from my own experience, like being in this argument for several years. What happened after 5 years was that this globe idea seemed just completely absurd. I don't know if this happened to you. And I don't mean our everyday experience of flat and stationary. I don't mean that. I just mean the whole notion of this ball covered in water hurtling through outer space. Did anybody else think of, like, did it just hit you how silly it is, how ridiculous it is? Now let me just
When I
say,
was
Chaiki, I know. I'm just going to say for the audience, for the neutral and the globers that are rolling their eyes, I don't mean that means that it's not it. It might be. I'm just saying the whole idea of it seemed absurd to me. That's all.
when I was young, I did wonder what's happened in Australia. How they live there, upside down. But I realized that I had a dispute with the teacher. She said, this up, this down. We had a map. North is. I said, who said that north is up? We live on a globe. Who says it this up and this? No, that was what decided. He said,
Yeah, it's just
I laughed her.
all
She
relative, I
was,
guess they'd say.
She was maybe the one teacher I could get along with.
Down under. Oh yeah. Is it really down
But
under?
then you understand they are not upside down. They're straight up.
I mean, it would be kind of
So
interesting,
Jay
though.
had an issue.
Sorry, I see. Go on.
To be honest, I don't remember.
No, you were first, bro. Finish up.
Ignore the fact that I'm talking.
I was just going to say it'd be interesting to see.
Ignore the fact that I'm talking, really, because you had to say something.
Sorry, you finish
It
up.
was
I
his
don't
turn to
recall.
talk.
I just wanted to say I don't recall learning gravity or anything like it in school.
I was just going to say it'd be nice if they'd show us a plane flying upside down. I realise they're not upside down to them. I'm just saying it would be interesting to see a plane flying upside down from a different reference, from a satellite or whatever it was.
That would be difficult. You see, even the debris that fly by them, and it's not so small. It's hard to track it. You want them to track an airplane on the horizon. Nah, impossible.
Holy cow! Look what Jace read to.
Yeah, I'm just reading it.
What I said was apparently oversimplified. Have a read on that. Holy cow, Jace.
Would take me a month to write something long as this.
I'm telling you, Chaiki, this is something else. To say exactly what I said, but in a different way, of course. More scientific like.
The problem is I can't use the microphone. If I'm on Discord, I can't use it to dictate text.
So after he said almost exactly what I said, he said that I'm wrong. It's amazing.
I didn't read it, to be honest. Something that needs to stay spoiler.
I
Yeah,
botched
I
an
mean,
explanation horrifically that was wrong to begin with.
I I don't know. I realize I'm not sharpest knife in drawer, Jace, but you see, I mean, you seem to be saying the same thing as SE. Am I being an idiot? I don't know.
Because I didn't use I didn't make it difficult enough to understand. You understand? I explained it simply. That's the problem. And I didn't use almost unpronounceable words. I tried to keep myself clear and concise. So that's
Yeah,
a
you didn't.
problem for these guys.
You need some $10 words, SE. That's your issue.
Yeah, yeah.
uh,
I'm just wrong, according to Jace. I didn't even state the incorrect correctly.
Hang on. You got to throw an LOL or laughing my ass off in there somewhere too. LOLs are his bread
Yeah,
and butter.
yeah.
He figures it adds at least 50% umph or more to what he's saying if he just says LOL.
I should have at least explained the incorrect correctly. I mean, damn it, what's wrong with me?
Yeah, I know. You just can't stop making mistakes here. You're going after the truth instead of an appeal to authority. How dare you?
Yeah, don't laugh too hard, Jace. Come on, you need it later for the dog walking. You're gonna run out of breath.
Did everybody go quiet?
Yep.
Y'all putting me to sleep.
Don't worry, SC will come up with something. Some controversy.
So it's up to me always. Why don't you come up with something there, Checky? Give us a
What
little
can I
brain.
What can I come up with? S is not flat. The bottom line.
Okay, we
Wait a sec. Wait
agree.
a sec. That's
Next.
ironic. You said, hold on. You said bottom line, like the bottom of the world, bottom line.
No,
The
no.
Earth isn't flat.
Look.
Oh,
You got to start somewhere. You don't start with integrals. You start to add numbers. Maybe. Then you subtract. It's more difficult. Then you multiply. When you divide, it's more difficult.
ooh.
So let's
Tell
start
me
with the
more.
shape of the Earth, huh? And then we'll go to
Yes.
dark matter, to quantum
Hold on. Yeah, let's
mechanics.
not go to dark matter.
All this
Another
thing you
really
need to
important.
learn like 10 years to understand.
Do you think if you talk louder, then you'll be able to get your point across? So, my friend, that's great. Where's the Earth curvature then? I don't care about dark matter, clear matter, whatever you got.
It's there. It's there. I have a
Where?
picture
Where did we go?
that show that the Earth is certainly not flat. The geometry
Okay.
don't allow.
Oh, the geometry doesn't allow for it. I see.
Yes, geometry doesn't allow.
So you
Geometry
found
says that if Earth is
drop
flat,
over.
we'll see something different.
You found your drop over distance 3959 radius value confirmed.
Not yet.
Okay. Well, might want to start there because any picture you show with geometry,
I will. Shut the fuck up. I will. No, I don't have any picture.
It has to match. So reality has to match your math. Otherwise, it's all just kind of bogus.
Yes, it will. Don't worry.
It will. When's that? When you go and do
When's
that?
Let's say 2 months from now.
All right. We'll be here, partner. Good luck.
Yep. The order the auto level. It'll take some time until it reach here. Take some time until I take it out. We'll do measurements. We'll see what's the radius, the real radius of the Earth is.
Hey, check. Is it Boker Tov or Erev Tov for you?
Let's say Laila Tov.
Laila Tov.
Yes, it's night. 10. It's after 10. Let's say Erev is until 9, 10. Then it's night.
Chike.
Yeah, I'm here.
Why so serious?
What the fucker is barking all day?
Relax, buddy.
I'm chill. I was so
Remember.
stoned. I was so stoned. It's fading. I need to renew it.
What? You were so stoned? Is that what you just said?
Yeah, it's fading. I need to renew it. To reload.
Careful, a water pipe is harsh on your lungs, huh? I had a friend who had a big problem.
Well,
I'm
Your
serious,
friend,
Chuck.
your friend is a wuss.
I don't think so, bro.
Mm-hmm.
What proof do you have, SE?
I take full lung from the bong.
Only consequential proof, like not solid proof.
So subjective perspective
Circumstantial.
truth. Yeah, circumstantial,
Subjective, yeah.
relative proof. Okay.
Ooh, relative. Yeah, I like that.
Fantasy proof. Yeah.
Say it's all relative again. Ooh, it gets me hot.
What do you say?
Drop harder
Relativity?
for me, baby. Drop harder.
Oh man, you know it's so funny that thing Napalm dropped. That's how their pipe would look like. These dudes were from Laos, the country, and they would take a pipe like that and make a water pipe out of it. Looked exactly like that.
Wouldn't that be
Isn't
a
that
bong?
isn't that where the neighbor from King of the Hill's from?
Is it? Yeah.
It,
These dudes were serious bongers. Let's put it that way.
That's paraphernalia. Yeah, but Chuck, you're a gentle dude. He's a gentle man. He likes dogs. Can't be acting like that, bro. Come on, man. Chuck's a cool dude for a Glober.
The fuck Glober? Who's the Glober?
I was gonna say, apparently he doesn't claim Globe, dude. That's his thing.
Not yet. You're not ready for it.
Whoa. I thought we had a very good discussion and we talked about perspective and all these different things. So what do you say it is, my friend Chike?
Well, it's not flat. That's obvious. If we put
Oh,
all the rules we know, if we follow them, we'll see that this picture is a geometric impossibility.
okay, so it's anything but flat. Got it.
Simple rules of parallelism. If a line is one let's say 1 foot above the floor, you mark 2 points 1 foot above the floor. You connect them with the line. The line will never touch the floor. They are parallel. However, when we look at the picture, we see that the line that we connect of 2 equal elevation points is not parallel to the water. The water is not parallel to the water. So it's certainly not flat. I have only 2 points. I'm not Soundly. So I have only 2 points. If they had there every mile they had this tower, built this tower, we would see the curve. Very good.
So you just don't want to make the positive claim that it's a globe. Is that what's happening here? Because that's
Yes, because I don't have really enough data. When I
okay.
have data, when I have data, if I have data, I'll claim globe.
Huh.
But
Well,
Larry did it. Larry did it.
Mm-hmm.
Hang on.
No
That's
one is
honest.
convinced.
Chike, at least that's honest, you know, and like I said, I hope you pull through and bring us some gravy, my friend. Absolutely.
For sure.
Yeah, because somebody's going to be disappointed.
Right.
Whatever I find, I give you that. I won't alter the result.
Oh, right. You know what? I'm gonna trust you on that. I'm gonna trust you on that right here
You will
and now.
see.
I just said it
You will
live.
see because if I take pictures you during the morning, you probably see the horizon move significantly. But if I do it
Hey, Chike.
at noon, it wouldn't move.
Okay. Yeah, I'm excited to see it for sure.
Hey, Chike. I got a couple questions for you. I got one question is, you think, right, that we went to the moon on top of the Earth being a globe?
Yeah, a bunch of people did go to the moon. We.
So you also believe in the moon landings?
I know that happened. People still
You know what happened?
People still image the junk they left there.
I just don't see how you could not think it's a globe then, if you believe that, because they obviously, you know, they got the pictures and everything. So I don't. That doesn't make sense to me.
I got a picture of a unicorn.
They have a vault, but you know, like the how's it called, where the Americans keep their gold, full of stones from the moon. Everyone
Fort
that comes to
Knox?
take a piece, yeah, the Fort Knox. Everyone that comes to take a little stone, they need to go take the bags out. They keep them in certain conditions, cut the piece of stone and send him, or they take the whole stone, depends size.
Why
Do you think?
would they put?
Do,
Why would they put? Oh, go ahead.
do you think that the moon rocks that turned out to be petrified wood? Do you think that's a fake story?
It's a bullshit story. I'm telling you, they have a huge vault full of stone.
Oh.
Why would they put so much emphasis on protecting those stones? But
Because
I
how
wasn't
many
finished.
times?
I wasn't finished. Why would they put so much emphasis on protecting those stones while simultaneously destroying the technology and the blueprints to reobtain the stones if need be? Like, that makes no sense.
It makes a lot of sense. If you destroy the technology and you know you're not going to get any new stones, you protect the stones you already got.
But why would, again, that makes
That's
no
logic
logical
for you.
sense. Like, why would you put more emphasis on protecting the rocks instead of the tool that got you the rocks in the first place? That makes
Because
no sense, Chike.
because they didn't have a budget, and they couldn't. I'm sure they would be glad to send another rocket, but they didn't have the budget. They cut them off.
Do you know how much of a budget is required to harness those rocks? You know how many people and the building and all of the infrastructure and utilities put forth to keep those rocks in that vault? It's a lot of money, dude.
There are people there, yeah.
No, I know. I watched the whole
But you
video.
know how much would it cost to keep all the machinery that will keep that technology? And we see we have much better technology today. Why we want to keep a technology from the 60s? Huh? Who rides a car from the 60s?
Whether or not they saved the technology, at least the blueprints to rebuild the technology, like, they don't even have that.
I'm sure they do. What it helps you if you need to build a new machine to bend a little, I don't know, piece of metal that goes somewhere in the, all this thing rusted or was recycled already, and they
I
make
know,
them
they
better, and they make them better today.
Yeah, I
Better,
agree.
safer.
I agree. Things get better over time, but what about all the information that they cost little to no money to keep that they just got rid of?
Didn't get rid of. I saw a video of Smarter Every Day, and he went there to the guy that designed or worked on the first stage, I think, first or maybe first and second stage Yes, and he explained to him how all this thing work. Look it on the. And another guy talked to the same guy about the computers that they have there. Forgot who it was, but it was the same guy, same engineer. He worked in many places. Forgot what he's doing now.
I saw that. I think it was the Saturn V rocket. The what? Yeah, the moon landing thing.
Yes.
Yeah.
The first two stages. The third was out his domain, but
But that don't
first
mean
two
to say
stages.
that it actually. That doesn't mean to say that the story is true, though. You get that, right?
Of course, it's true. Of course,
Well,
it's
I'm
true.
just. That's the
He
thing. I
worked there.
mean, you can actually
They have
entertain the
the
idea
blueprint.
that it's not.
The idea they don't have the blueprints is ridiculous.
No,
I'm
no,
sure they
dude.
have the blueprints. That doesn't help them any much.
Can you entertain the idea that outer space is fake completely, and that they're doing it from a studio?
Any idea? I entertain my sanity. Or maybe I'm insane. I don't know. There's no way for me to tell. The only thing you can tell is how you perceive things.
Well, I would have
What
thought
it look.
healthy skepticism, Chike. That's the same place to be, in my opinion.
Yeah. Well, there's not much I can do about it.
Yeah, you can't force us all to think how you want us to. Oh man.
This crazy. I think I talk rationally, but I don't really know what comes out of my head. What other people hear. That's the nature of mental state. You can never know what the other party tell you. Maybe sound to him very different. Look perfectly logical for
Jackie, I have
him.
a question for you.
The way.
Can you accept a contradiction?
A contradiction?
Yeah, can you accept a contradiction in order,
which
for whatever
contradiction?
reason, can you
If there is a
I'm sorry?
contradiction. I don't understand if you say a or the.
A contradiction. Let's start with that.
For sure.
You can accept a contradiction.
For sure. What I must accept a contradiction.
Okay, can you give me
I
an
must spot
example
it.
of an accepted contradiction?
Yes, I have an example. You know I have it. It's when Bev says that planes do not exist in reality, and then it says that horizontal planes definitely exist. That's a contradiction.
Yeah, but that's Bev. Why are you talking about Bev now? I'm talking about
I
you.
gave you wanted an
Can you
example.
accept a contradiction?
No, I won't
But that's
accept it.
somebody else's
I'll
example.
reject it. I'll reject the contradiction. I will spot the
So
contradiction
you
and
will
reject
not
it.
accept a contradiction.
Absolutely not.
Okay, fair enough.
Bring
So
me a contradiction
you
and
cannot
I'll reject it.
conceive of a thing of a way that. Jackie, let me ask the question, bro. There's no conceivable way for you to accept a contradiction.
No, unless I didn't spot it somehow.
Okay, all right, fair enough.
Now, can you think about contradiction? You think I accept?
A contradiction that I think that you might hold.
Okay. Yes.
Yeah,
What is it?
you said it before.
What is it?
Oh no, that wasn't you. Okay, let me try this on you. Somebody else said it. Can you think something can be accelerating and not moving at the same time?
100%. I'm accelerating. I'm not moving.
So there you go. There's your accepted contradiction.
It's not a contradiction.
That you can be both
Force imply
accelerating and
acceleration.
not moving at the same
Force imply
time.
acceleration. The acceleration does not imply movement. Certainly not in general
Oh, wow.
relativity.
Well, isn't it a change
So you
in
don't see
velocity?
the contradiction. So you can.
If you're
Sorry,
accelerating at 9.8 meter per second square left, and someone push you 9.8 centimeters per second square right, you don't move. Still accelerating.
So acceleration without movement. So you can have so you do have accepted contradictions. There's a perfect example right there.
It's not a contradiction.
Does anybody agree with Chaiki here? Anybody on the panel? Does anybody agree with that?
I feel like that's where you feel like that's where you'd feel it, isn't it? SE acceleration. That's where you feel it. Like a constant velocity, yeah, you're not going to feel it. You're not going to know. You know, well, there's things that could let you know, of course, but acceleration's where you're going to know. You're going to feel it. You're going to feel
but we're
that
not even
change.
talking about that, Andy. Yeah.
All right, I missed what you're actually
I-
talking about, but that's where you're going to feel that change in velocity.
Yeah, agreed. But he's saying that we can have acceleration without movement.
Yes.
Yeah.
Let's do Einstein equivalent principle on a small enough space. You can tell acceleration from gravity. Yes. So I put you in an elevator that's moving up. There's no gravity. Just the elevator accelerates it up. What you feel? You feel
Is it moving?
9.8. Yeah,
Is the elevator moving?
Of course, it's accelerating.
So what's your? It's a non sequitur.
Now, why? Hold on.
Well, you said acceleration without movement, and the elevator is moving.
Hold on, I didn't finish. It's equivalence principle. Now, you think you're on Earth because it's accelerating 9.8 meters per second square. We stop the elevator and we turn on gravity. You don't know. You don't feel the difference. You don't know you stopped moving. The force on your feet is the same force. You can't
but
tell.
the elevator's moving, no?
No, it stopped moving. Stop there. We turned on gravity. There is a switch. Gravity on. Elevators off. You don't
you
feel
have a gravity switch in this. Wow.
Yes, something new. It's a thought experiment.
We're off into
You don't know
fantasy
that
land here, right?
the elevator stopped. You have no way to tell. The force on your legs is the same force. Didn't change.
Yeah. So how is this acceleration without movement? I don't get it, Chucky.
Well, Einstein tell us that we move in space to seek our natural state. Everyone wants to be at the lowest gravity potential possible. It's in the center of the Earth. They try to move there, but there's sand and rock that don't let us move when we want to go. They push us back. So we keep accelerating the same direction without moving, and the Earth, all the rest that wants to get to the center, push us back. Earth not moving, we not moving, no one moving, and still there is a force.
Maybe I'm at a loss of words here. I don't know what else to say. I mean, how can you reply to that? You think that we can have acceleration without movement, and you're trying to come up with these crazy ideas that, frankly, make no sense.
Do you feel the pressure on your bottom? You feel it? That's called force. F equal ma. It's a law of nature. That one is true.
I don't know, Checky. I don't know what to tell you.
What do you
It's a
want?
tall
You have
order.
force.
You got to
You
come
have
up with
force.
something better than that.
You have force. You have acceleration. Time s. You feel the force. We feel
And no
it.
movement.
Are you
And
moving?
no movement.
Well, are you moving relative to what you stand on? No, you don't.
Mic check.
You're fine.
You're good, Rick. Yeah.
Chaiki's not the only one that believes this. This is general relativity. I mean, it's like when you throw a ball up and it reaches its apex, it's not moving upwards anymore. It's actually still moving because the Earth is moving towards it. So you can have acceleration downwards towards the Earth without movement of the ball because the Earth is moving towards it. That's the whole 3 days. That's why Chaiki is saying this. He's just repeating what a man, Einstein, his God, has told him. He said it. Einstein told him
He didn't
this,
tell
so
me.
I
Explained
believe
it to me.
it. Yeah. Einstein told me this, so I believe it. Have faith in it. What does that sound like?
Well, Einstein make a good argument.
Religion.
No, he make a good argument. He didn't tell me. He explained it to me, and explained it good.
Right, but didn't leave you anything to prove it. Just left it to faith, right? You either trust me or you don't. It's called faith. It's called a religion.
No, you follow the logic.
Yeah, but other people can follow other logic. So you put your faith
There's
in
no
that
other logic.
You cut me off again. So you put your faith in that
Checky,
logic.
come on. Let's have a combo.
Yeah, no problem. You put your faith in that logic, which I have no problem with, and I put my faith in another logic. It's called faith. Things we can't prove to each other. You cannot prove that that ball is still moving or the Earth is moving towards the ball. It's just a theory.
Okay, let's hear your logic.
What do you mean? Let's hear mine.
You say I believe in another logic. I want to know what it is.
The opposite. Just take the opposite of the bullshit you just spouted that you can't prove that you have faith in from this man called Einstein. Just take the opposite of that, and that's me. I don't think the Earth is moving up towards any ball that I throw up.
I didn't say the Earth is moving.
Yeah,
Huh?
yes, you did. That's what general relativity says. That's what you're believing in. Yes, you did. You said
did I
moving.
say Earth is moving up?
You said you can have acceleration without velocity. That's what Einstein said. That's your exact words.
Acceleration
Is it not? Is it not? Is it not what you believe?
Where is velocity? Where is velocity in F equal ma?
Let's get to the go back to the beginning. Is that not what you believe? You just told SC you can have acceleration without movement like 100 times, and then you went into a dialogue about Einstein proving it.
Yes, simply with logic.
With logic, yeah, theory, which you put your faith in, right? Wholeheartedly to come here and repeat it to us. We have different logical conclusions, which are the Earth is not moving towards any ball. You can't have acceleration without movement because that's not logical at all. You have to invoke some type of Einsteinian theory, right, that you call logic, which is illogical at best, maybe crazy.
Well, Einstein says this. Look, I'm in an inertial frame. What is inertial frame? Inertial frame that everything moves in unison. For example, you take a ball, you let it go, it stay where it is. Should stay where it is. On Earth, it falls, but it should stay where it is in inertial reference frame. And Einstein said, if I free fall and I take a ball and I let go, it doesn't fall. Continuum stays where it is. So that's the real inertial reference frame. Then he say F equal ma. Suddenly I feel force. I hit the ground. I feel force. Where this came from? must be accelerating. Newton said F equal ma.
Isn't the definition of acceleration though like a change in speed? How would you not feel that speed?
Velocity.
Yeah, how do we not feel it though? That's what I want to know.
What do you mean you don't feel? You feel the force. How do you feel change in speed? Without eyes, you're blind. You don't have eyes.
Your
You feel the force impart on you. All direction. You feel the force. That's your feeling. I'm slowing down. I'm speeding up.
You
don't
feel
really
that,
know.
don't you? You know it. When you accelerate, when you feel acceleration, you know it.
Yeah, the airplane take off. You stuck to your seat. You know you're going this way.
Yeah.
So you close your eyes and you sit on your couch, and you accelerate. You're going this way. You're going up.
Is the airplane moving while you're doing that?
No, nothing moves.
The airplane's not moving. Holy cow!
No, the airplane moves. No, I talk about your couch on your porch.
Jesus, I don't know if Xanax worse or what.
Nothing moves.
So that's what I was trying to address. How about the opposite, Chike? How about there's nothing that's not moving?
That's fine. Is this what we observe?
Yes.
What's moving?
The tree leaves are moving. That's the only thing I can visibly see moving. The ribbon. I'm sitting in my truck. I'm not moving. My truck's not moving.
You're moving. You're moving a lot.
No, you can't tell me that. I'm not. I'm sitting right here. Trust me. I'm not moving.
Do you have temperature? Do you have temperature?
Put your faith in me, sir, not Einstein.
In you, I'll not put no faith.
Einstein is dead. He's not sitting in my truck. He has no clue what my truck is doing. The leaves on the tree in front of me are moving. The ribbon hanging from the post in front of me is moving. My truck, not moving.
So
what? I mean, you can believe the opposite. You can believe nothing's moving, or you can believe my truck is going 1,000,000 miles an hour. I don't give a shit. I don't care what you believe or put your faith in. But don't say it's not faith, because there is no way in hell you can come here in a plane that's not moving, get in a car and travel on the roads that aren't moving, and come to my truck and prove to me that it's moving.
Why are you so religious, Chike?
Me religious? Did I say the car moving? Why are you storming in
Yes, you did say the car is moving.
No, I said the car is not moving.
It has to be moving. It's on Earth. The Earth is moving. Millions of miles an hour.
Did I claim the Earth is moving?
You said it.
No, I didn't.
You said everything is accelerating.
You quote Einstein.
You said everything
every
is
other
accelerating.
Accelerating, yes. Didn't say moving.
So the Earth isn't moving? You don't believe in Einstein?
We're not there yet.
You can't quote Einstein
No,
every other
I
word.
don't discuss. I don't discuss
I know
these
you cut
matters
me
with
off
you.
again. I know you
I
cut me off.
don't discuss these matters with you.
I know. Keep going, but you don't have to discuss it with me. Just go on mute. I'm gonna tell the audience. You can't discuss. I'm not talking to you, Chikey. You can't discuss. Listen to you. Listen to yourself. You hear it?
Chikey, come on now. Come on.
You hear yourself,
That's the
Chikey?
point.
That's you losing. You can't bring up Einstein every other word as your whatever, the person you put your faith in logic, and then say the Earth isn't moving. Pretty simple.
Chikey, you there?
Yeah, well, what do you want me to say?
Just checking.
You said I can't say something. Of course I can say whatever I please.
I said I wasn't talking to you, Chikey. I was talking to the audience. I don't care what
I
you
didn't
say.
talk to you. I was
You
talking
can
to
say
IC.
whatever you want as you cut me off
Why you
again.
inject
Dude.
yourself into
Do you have
conversation?
an issue? Do you have an issue? Because I don't want you teaching people this, but I can't control you. But what I can do is tell the audience how ridiculous it is when someone like you comes on here and says that the Earth, although Einstein quotes and quotes and quotes Einstein this and Einstein that things aren't moving, but they're accelerating, or I don't even know what you're saying. I don't even think you can repeat it.
True, I can. I'm sure you convinced the audience because the argument you brought was perfectly clear, its premises valid, sound, and the conclusion was correct. You understand, Rokia? You said nothing but words.
Said that I'm sitting in my truck that you can't prove that's moving. That's a fact. I see trees, limbs, and leaves moving. That's a fact. I can prove it. I see the ribbon on the pole moving. That's a fact. What you can't do is prove that my truck is moving. Factual. These are facts.
I didn't.
Yeah. You
I
have to
didn't
say
say
that.
it moving.
You
You
have to
don't
say
tell
it.
me what I have to say.
Everything in Einsteinian bullcrap is moving, has motion.
I don't need to
It's on
follow
the
your
Earth.
failed
The Earth
logic.
is spinning and rotating and moving through orbits in
You
free
sure?
space.
Did you measure it?
What are you talking about? I don't believe it. You do. Einstein did.
No, I don't believe it. Who said?
So you don't believe Einstein? You just quote him every word? That's weird.
No, I follow his logic.
You followed
Don't need
his
to
logic
believe
except for
anything.
the.
I
You
don't need
followed
to
his logic
believe.
except
It's
for the Earth moving.
logic. It's logic. Don't require belief.
You pick and choose. You pick and choose what Einstein logic you believe in and want to spout here. Well, how about coming up with your
Again,
own
you
logic?
keep with your beliefs, and I don't require
Not my
belief
beliefs. You just said it over and over
because
again. Einstein,
logic
Einstein,
has no
Einstein.
belief built into it.
I tell you what, pay me $100 how many times you mention Einstein. How about that?
Yeah, okay.
Yeah, you don't
Count
want
them,
to because
count
you
them.
know you mentioned him like
Count
20
them, count
times
them.
in your
Go ahead.
conversation in the last 10 minutes. But now you're
Count them.
reneging on it. So do you
Count
not believe in Einstein?
Count them. I'll send you $100 for each time.
Yeah, I bet you
Go
will.
ahead.
I bet that's a lie. Do you not believe in
Of
Einstein?
course it's
You
a
want to
lie.
answer that?
Of course it's a lie. Why would I send you money? Because just because you
Exactly.
said
So
so.
why would you say it? Why would you say it? Do you
Why?
believe in
Why would
Einstein
you?
or
Why
not?
would you say it? Why
I don't
would you
need your
say send
money.
me $100?
Yeah,
You
you
short
want to
of
stick
money,
on that
Rakia?
because you don't want to
You
answer the
short
question.
of money?
Yeah, no, I'm
Why I
not
need to
short of
send you
money.
money? Why you say it?
Yeah, you want to dwell on
all
this.
right,
This is the
bloody
game you
hell,
play.
calm down. Jeez.
Right,
Both talking at the same
exactly.
time.
The question on the table is, do you believe in Einstein? His logic.
Believe in Einstein. Again, logic does not require belief.
So which part of Einstein's logic do you trust? Why are you picking and
All of it.
choosing?
All of it.
So the Earth is moving. My truck is moving then, right?
No.
Yeah, see you later.
Can I change the subject a little bit? Andy,
Yeah.
you were asking earlier to Chaiki about feeling. How would you feel motion? Could you ask that again? Maybe I can answer.
A change in velocity. That's my understanding of acceleration. Please correct me if I'm wrong.
That's right. Yeah.
That's my understanding. That's how we feel it. That's how we, that's the way I see it anyway. So
Right. Oh, but there are different ways of accelerating.
The proper acceleration. You're gonna explain that to me now, aren't you?
I'm not sure actually. I'm not familiar with that term. But like you gotta be
proper
familiar with
acceleration is simply the acceleration you can measure force with the gravimeter or accelerometer. When you free fall, you can't measure it. It doesn't exist at all. You're inertial.
Yeah, well,
that's why you're inertial when you free fall.
But you don't have to appeal to relativity to explain that. Actually, that's why I think I can offer a simpler explanation for Andy. So even if we go simply with Newtonian mechanics, we don't have to assume that falling observers are inertial. We can still say they're accelerate downwards. they would still be unable to detect that acceleration as acceleration. Think, for example, on how we detect acceleration, how humans feel that they're accelerating. So we have the vestibular system, and inside of the vestibular system, there are some cavities with some like small crystals. They're usually called ear rocks. And if I push you, like if I accelerate your body with my hands by pushing you, your head is going to accelerate first, slightly before the crystals do. So the crystals are going to lag behind, and they're going to end up in the back of the cavity. And you're going to feel that because you feel that all those crystals are all going towards some direction. That's because I'm pushing you, and I'm not pushing the crystals. I'm just pushing you, and there's a delay between me pushing you and then you pushing the crystals. Is that making sense so far?
Yeah, I like that. I like that. This is good.
Right. So if we're talking about, for example, let's say we are in space completely floating, and those crystals are now weightless. They're not going to go to the bottom of it as they are usually on Earth. They are always at the bottom of that cavity. If you're weightless, if there's no gravity or nothing pulling them down, they're just going to float inside of the cavity. You're going to feel weightless. Now, if we are on Earth, but you fall, you jump from a bridge, for example, and you start accelerating downwards, not just it's not that the gravity is pulling your body downwards, it's also pulling the crystals with the same acceleration. So your whole body, your vestibular systems, the crystals themselves are all accelerating downwards with the same acceleration. So there's the crystals are not going to go up or down or to any particular direction while you're falling, because they're falling with you. There's no bias for the crystals to go anywhere inside of that cavity. So you're going to feel the same thing as you would feel if there's no gravity. So the experience of someone free falling should be the same as if there's no gravity. Did that make sense?
Yeah, that's a really good explanation, actually, Bacon.
Hold on. That's how gravity
Thank
feels.
you.
Nothing.
Well, wait a minute. I like the explanation. I thought about that with them being in space as well. You know, floating around and not having that orientation of down. That must be terrible. You know, I imagine that'd make you feel well. I wonder if it'd kill you. You know, just a few days of it. I don't know. Maybe.
Well, I like the question, but just to make the point, just to solidify my point, you can test that with your smartphone, because the way your smartphone detects acceleration is like a different system, but it's pretty much the same idea. You have these tiny weights. Oh, hang on, there's a lot of dogs here, but give me one second.
The bacon's being attacked.
Don't forget, this gentleman told me that I can't use my phone to do these measurements. So
yeah.
It might be a bit lower now. I guess you probably can still hear them. They're not mine, they're the neighbors, but anyway. Yeah, there's like a bit of a weight inside of the device that detects acceleration, and when like you push your phone, you accelerate your phone, there's a bit of a delay, so that small mass gets shifted relative to the device, and the phone reads that as an acceleration. Once you're dropping, all that mass goes to the center. They all relax. Let's say there's no bias to any direction, and the accelerometers are going to read 0 in all directions. So if you drop your phone not only reads 0 acceleration, it can't know in which direction it is accelerating. And if you put on the table, then you get the mass that is aligned vertically is going to go down, and the phone is going to register as an upward acceleration. Just like your vestibular system does. Like if you're in space and you accelerate upwards, those crystals are going to be brought to the bottom of the cavity, and you're going to feel the same thing as if you're in space accelerating upwards as you feel here on Earth, where things naturally accelerate downwards. The feeling should be interchangeable based on how we feel acceleration, or even how phones detect acceleration.
My only objection was that you feel nothing, you're not in gravity. That's how gravity feels. If you feel nothing, you know you're only in the gravity field, and that's it.
I mean, you must feel a bit disorientated, though, right?
No,
I mean,
no.
Chat,
No.
you
How
gotta
can
go
you
to. You gotta go
feel?
to.
How can you feel
Suppose you're on a
nothing?
trampoline. On a trampoline, can you tell me when you reach the apex and start falling? You can't. You
How
accelerate
can you
up. You
feel
stop.
nothing?
You
You say
stop.
you would feel nothing. How can you feel nothing?
I think he
There's no
meant
force
no
on you.
acceleration.
No forces.
Why do you go to sleep at night? Why do you need to rest?
Because I'm tired.
Is that supposed to be related? Just asking.
You don't think that standing up takes energy?
Is that supposed to be related?
What I know.
Yeah, so you would feel that at the end of the day that you're tired.
The most of the calories you burn at rest. It's the maintenance of the body, not runs. Well, marathons maybe, but 10 kilometers even. It's not much calories. You burn daily about 2,000.
Are you saying that you burn more calories sitting on the couch than going for a run?
Yes, because you sit a lot on the couch, and you run very little. There's not much required.
Is that your life experience or everyone's life experience? Because I hear you doing this. I hear you doing this often. That you like say something that everyone does that I think maybe only you do.
Well, count your calories and tell me how much you burnt running today and how much you burnt sitting on the couch.
Well, I've been working all day. I haven't even sat on the couch yet.
Well, then you burnt them working, but it's not the physical that took it. It's the maintenance of the body.
Shay, can I ask you a question? Hey, buddy, you understand that what you believe in, right? Your worldview is based on faith. Your fundamental basis is faith, right? Like no substantial evidence, not empirical evidence, none of that. If we agree on that, bro, we cool, bro. You know what I'm saying? But you stop believing in Yod He Vav He to believe in Einstein.
I'm sorry to disappoint you. I don't have beliefs. Well, I must have one. Is that what I perceive is how it is.
But it's a philosophical premise.
Right. That's the only thing I believe in. The rest are facts. If I perceive it as fact, it's fact. I don't require beliefs. Show me logic, show me the rules, your premises, and follow the logic.
It's what you believe in is illogical, though.
Yes.
That's what we're trying to.
Must be
that's
logical.
what everybody's trying to tell
it's
you.
It's not illogical. I don't believe it. If there is no logical argument for it.
It's illogical.
I wouldn't say it's illogical, but if you don't bring a logical argument, I can't. I don't accept it. Belief, no
you
belief.
believe in acceleration without movement.
What do you mean? I believe. I'm sitting on the couch.
How can you prove it?
I feel
what is the evidence that we're moving? What evidence? So what is the evidence that we're moving? What do you have to bring to the table?
Again, I didn't say we're moving.
See, you can't have it both ways, though. You can't say that we're accelerating and then at the same time say that we're not moving and then not prove either one. You can't prove that we're accelerating or that we're moving.
Again, I prove that we're accelerating by measuring the force I'm part on the couch. Can take
I'm referring to the earth.
Yes. I stand on the scale.
Not the items, not the
I
things
can measure
on the
the force.
earth itself.
I can measure the force. There is a force there. I'm sure there is a force there. I feel it.
So how fast is that?
Zero. I'm not moving.
Well, how fast is the Earth accelerating? And I'm not talking about in reference
9.8.
to the sun. I'm talking about within the fabric of space and time. How fast is the Earth moving through space, empty
I
space?
didn't say it's moving through space. Why you ask me?
And, well, this is that
Chuck,
double talk.
I gotta admit, Chuck, you're not making a lot of sense to me.
Why?
I don't know. I'm not being able to connect everything you're saying.
Why? That I don't say that the Earth is moving in space? I don't know. I didn't observe.
Yeah.
It's not
Or you're
required.
getting me confused. Well,
It's
yeah,
not
but if
required.
you
We're
say
talking about one subject. Does not require the other.
right,
Hey,
but
maybe
you
we're
know you're
getting somewhere. Hold on. Maybe we're getting somewhere because he just says that he can't prove that we're moving through space. So maybe we're actually getting somewhere, making some progress.
think he meant he's not concerned with that for this current conversation.
Yeah, forget I read about Tycho Brahe and the measurements he takes. I didn't measure it. Did I did it myself? No. So I forget it. Nothing's moving. I don't
Bacon,
know
do you think
that
we
someone
can have
observed it moving. It's not what you're
Bacon? Do
talking
you
about.
think that we can have acceleration without movement?
Acceleration without movement. Well, if you're spinning, that's acceleration. You don't have to go anywhere to spin, right?
Are you not moving as you're spinning?
I can move in a fixed location, so I wouldn't call that moving.
You just said I can move.
Oh, sorry. I meant spin.
In a
I can
fixed
spin on a.
location.
Sorry. Yeah. Yeah, I misspoke there. Sorry. But yeah, in the Newtonian understanding of physics, no.
So
Yeah.
no. Okay. Thank you.
Oh, don't forget the first part of
So
the sentence.
Checky, you're on your own, bro. You're on your own on this one, bro. I'm sorry. You got to rethink this one.
No, I think Zanik is with me.
Zanik, huh?
Mm-hmm.
I'm just trying to wrap my head how you can see a possibility of acceleration without movement. I just can't see it.
Well, you gotta picture time as an extra dimension and a space that is non-Euclidean. So yeah, not that easy to visualize that. I'll give you that. I don't have an easy time visualizing that either.
Yeah, it's like, come on, this is
Well, but I mean,
thinking person. I mean, even if Einstein said it, I mean, come on.
oh yeah, it's not because Einstein said it. It's because I mean, it's a use like it's something that can be formulated.
Wasn't Einstein a fraud,
which
though?
means it's not something people are just vaguely talking about it. You can mathematically describe it. So it's not just something vague, right? It's something well defined and well formulated.
So
and it has implications. Hang on just a sec. If those implications have consequences to reality, you can test them and maybe even use them for your own benefits, like putting satellites into orbits or having GPS or stuff like that. So even if it's hard to wrap your mind around it, even if it's completely impossible to imagine it, if it's something that can be formulated and it's useful, then there you have it. It's useful. That's all it is.
He does sound, he sounds like a lot. He sounds like a lot of double speak, though, doesn't it? As well.
Real quick. I just I wanna ask Bacon. Bacon, you said that it's well defined, right? So what is the value for the acceleration or velocity or speed of the Earth, however you want to phrase it, right? And not in reference to the sun, mind you. I want evidence that actually proves that the Earth is moving without using reference points. So you can't use the sun and you can't use the stars.
I'm not sure if I understand what you're asking me. Sorry. Can you
You said it's well
reformulate
defined.
it? Yeah,
He wants
the idea of
evidence.
relativity.
Give me the
He wants
value. Give
evidence
me
for
the
Earth's
value.
movement.
Give me the value of the speed of the Earth.
Which
Give me
speed of the
something.
Earth?
Acceleration, velocity, whatever. Just give me something. Give me a value. You said it's well defined.
Once per day.
Well, yeah, well, the what's well defined that I was referring to is relativity as a model of explanation. That's well defined. It's not something described in
You're not
English
answering.
using
I'm not
vague
talking
words.
about relativity. I'm not talking about
Yeah,
relativity.
I'm not
What,
answering
give me,
because hang on. I'm not answering because your question didn't make sense to me, and I'm trying to explain why. Not because I'm trying to give you an answer. I don't. I really don't think your question is answerable because I think it's under some misunderstandings of what I said.
I'm not talking about the speed of the rotation of the Earth, right? I'm not talking about that. I'm talking about within its point in space, right? Empty space. How fast are we moving through the cosmos? Do you
But
have
that
that
wasn't me. That
number?
was extremists.
Well, you seem, but you're the one that said it was well defined.
I said relativity is well defined. I didn't say I wasn't talking about like specific numbers of velocities. I'm talking about the explanation on how gravity works and how space time works. That's well defined.
They don't have any fixed points in space in their model. They can't do that. I don't even know how they drop a plumb bob, to be honest, if they don't have any fixed points in their model.
They can't do nothing without using the sun or the stars as reference points.
Wait, what do you mean? Why? Can I use Earth as a reference point? I mean, we use Earth as a reference frame all the time. So I don't understand
But the thing is,
what the issue is.
Copernicus, Einstein, Hawkins, they all said that you can't really use the stars or the sun as reference points to come to any reasonable conclusion. And I'm paraphrasing, but they all said that in their own words. And then when you say things like,
You know that
relativity is well defined, or that when Chaik is talking about acceleration and everything is accelerating, where is the evidence?
Oh, if you want to know how we tested relativity, that's a different question you're asking me now. I'll tell you, I'm not that good in this subject. All I'm saying is that relativity isn't just words. It's just something that can be interpreted differently by different people. And some people say, well, according to relativity, you should expect this, and the other person say, no, you should expect that. And there's no way to sort out who's making the right prediction. Well, it's not like that. So if you apply the formulations of relativity, you should get the same predictions, regardless who's doing it. That's what I meant. So now, if you're asking about specific values of acceleration, I don't see how that really relates to my point. And even if it did, I wouldn't know how to answer that question because I don't know much about relativity. All I know is the basics that I'm trying to give you guys. I can't go much further than this.
It's theoretical physics is basically my point, and I'm over. That's it. It's all theoretical. Thanks.
Sorry, was that a question?
Model. No, this is going to be a statement. In their fantasy model, listen to this now. This is very important. You've never been in your life to the same twice. You have never, ever been to your same fishing spot at the same location because it's moved. You've never been to your same camping ground. No, that's moved as well. You might think you went there, but you didn't. You went somewhere else. So this is their model. You've never been to the same place twice, ever in your life.
That's only if you're using a different reference frame than the Earth, right? If you use Earth as a reference frame, then of course you can.
Yep.
Yeah, so position is something that is relative
movement,
to a reference.
acceleration without movement. Sorry, go on.
I think I might have a delay. I might have spoken over you. Yeah, position is something that is relative to a reference frame. I can't tell you my position is 10 kilometers. If you don't know where that 10 kilometers starts and in which direction it goes, you need a reference frame to talk about position or motion. So the fact that there are other reference frames other than the Earth, that's not a contradiction. That's not something that is insane. It's just a simple concept. You don't have to use the reference frame of the galaxy to say that you've been to the same place twice. You can use the Earth as a reference frame. That's fine. Reference frame. You can pick reference frame to make claims however you want. The fact that you can pick different reference frames is not a contradiction or a refutation of anything.
Well, you can believe whatever you want. I just put the fishing spot and camping spot as just like a paradox sort of a thing, right? We all know we've been to places where we've been before, right?
Yeah,
But,
that's
for
exactly
example,
what I'm
here,
trying
I'll give you an example of another contradiction. Are you moving right now, or are you stationary? Are you sitting down? What are you doing?
I'm sitting on my chair.
If you don't mind me asking.
I'm sitting on my chair.
Okay, so are you moving right now? In your paradigm, are you moving, or are you stationary sitting in your chair? What do
in
you
my
believe?
paradigm, that
And what does
question
your
is
paradigm say?
in my paradigm, that question is frame dependent. So the question is incomplete.
Oh, that's a clever
Okay,
answer.
let me
That.
rephrase it. Of course, bacon is one of the top.
Welcome to last 200 years of physics.
That's a good one. It's a good one. That.
No. Well, I know your model. Don't worry. Okay, let me rephrase that. Right now, are you stationary relative to the cosmic background radiation, or are you moving?
I have no idea how to evaluate that relative to the cosmic background radiation.
Okay, let me rephrase it. Are you moving relative to the great attractor, or are you stationary relative to the great attractor?
What is the great attractor? Is that the direction in which our galaxy is like orbiting or moving or something? Or all galaxies are getting closer?
The Lakina cluster and this cluster and that cluster, yeah.
Oh, I
and
think
us
so, yeah.
too.
Is that attracting the Milky Way too?
Yes.
Then I'd say yes.
So we are moving at millions of miles an hour, right? So you're moving right now at whatever, let's give a speed 800,000 miles an hour in relation to the great attractor. You're not sitting in your chair stationary.
Yeah, not relative to the great attractor. No, you're right. You're right on that. Yeah. I'm still sitting on my chair,
so
but
you
we are
see,
both moving.
That's a contradiction in terms.
How is that a contradiction?
You're both stationary and moving.
No,
yeah, it is
I'm both.
in my world. In my world, it is. Yeah.
It's not a contradiction because you omitted a part of the sentence that is relevant. So I'm stationary relative to the Earth's surface, and I'm moving relative to the great attractor. There's no contradiction there because I'm giving you the full context of either claim. You can't just remove both contexts, which is the reference frame, and then tell me that I'm contradicting myself because each one of those claims came from a different reference frame. So if you remove the reference frame and put them together as if they were in the same reference frame, of course they're going to contradict each other. But they weren't made; those claims weren't made from the same reference frame. They were made from different reference frames. You created that contradiction.
No, I understand. I understand how you look at it from your paradigm, right? But what I'm trying to show is the absurdity of the model that you believe in, which makes you believe like right now you're traveling at, let's say, 800,000 miles an hour. That's what I'm trying to show.
Well, I mean,
because I know I ain't traveling at no 800,000 miles an hour now, but you seem to believe that you are.
Well, there's really no way you would be able to assert that for sure. I mean, we don't have a sensor of velocity that is independent of reference frames. Like just the way we detect acceleration. Like if you think about how our receiver system works as I described previously, there's no way that would detect that speed because that speed doesn't do anything with our receiver system. It doesn't do anything with the phone's accelerometers. So you can't say I know for sure just because you're not detecting it. That's something that shouldn't be detectable anyway.
Well, you've been convinced of that, right? Had you not gone through the school indoctrination and believing in this relativistic nonsense, which I call, right?
But
You would not be able to be convinced that you're moving right now. But because you bought a story about this dude Einstein, that he came up with this while envisioning his friend falling off a roof or traveling on a beam of light, you bought into this madman's fantasies, right?
Well, here's where I disagree.
Knows that he is not traveling at under 1,000,000 miles an hour. You can't convince any logical person of that.
Yeah, I disagree that I just bought that story. I'm just indoctrinated with it because I didn't just repeated the claim. I explained previously the whole process on how we detect things and why it wouldn't make sense for you to detect emotion. It's not that I'm just claiming you shouldn't detect it because I was told so. I literally described how we detect things and then showed why that's not a way you can detect this motion. Like I'm taking that as a conclusion. I'm not just taking that for granted. Don't say I believe that because I was told so. That's not a fair assessment. I have that as a conclusion, a logical conclusion. You might disagree with my conclusion. You might think I'm being unreasonable. But don't just say I believe that because someone told me so. I have my
Do you think it's
reasoning.
outside of the realm of possibilities, Bacon, that a lot of us think that you just have an emotional attachment to a story you can't
Are
let
you
go
aware
of?
of the different wobbles that the Earth goes through? And apparently,
I
there's like
think
a
I know
third
some.
wobble now. They're on a third wobble, so it's
I
not
think I
just
know.
the axial tilt for the 26,000 year cycle, but not now you have like three
Yeah.
wobbles, dude. So you have that one, and then I already forgot the names. And up one, there's a cycle of apparently 800 years where the Earth has to wobble, and they need this for their model to work.
No, we don't need this. It's how it works.
They need three different wobbles
No, they
on top
don't
of everything
need
else that they
this.
keep adding to all these patches. It's a third
Who
wobble that
needs
they
it?
need.
Who needs it? For what purpose?
Relativity needs it.
What? Relativity doesn't need anything.
Yes, it does.
No, it doesn't. What does it relativity need?
I'm not
What to
listen. All
survive?
I'm
What
saying
do
is
you mean
that
by need?
it's part
Need?
of your model. Part of your model, the heliocentric
No,
model,
it's
where the
not
Earth.
part of our model. It's part of
Yes,
what
it
we
is.
observe. It's what we observe.
You
It's not
needed the
required in
axial
any
tilt.
model. Not required in any model. However, the wobble is probably built in the model because there is that experiment something they discovered in space, that if you rotate a bolt which is not symmetric, it changes, it flips every now and then. I think the Russian saw it first.
What? I didn't.
How do you convince
What's he
a
talking about?
populace that they're...
Let me look for the video.
Go on, Jackie. How do you convince a populace of the unconvincible? I mean, the fastest I've been is what, 550 miles an hour? Now, I can't even fathom going 1.5 million miles an hour. Like, that's unimaginable for me. Never mind at different vectors and this stuff. And like, how do you convince a populace of that?
So, Chike, you believe that the Earth wobbles? Like a drunkard? You think it just kind of wobbles along here and there? You think the Earth gets drunk? If that's the case, I got some news for you.
Hey, if you think the Earth's a globe, I got a bridge to sell you.
There it is. We're testing.
Hey, I can hear you.
What's the video? Don't hear me.
What?
Watch the video. You wouldn't have to believe anything. You'll see it.
All right. You know, if the Earth were to move, right? Like if it were to wobble, theoretically speaking, any of the wobbles, right, it would be noticeable on Earth, as in the light, right, the tropics, those lines of demarcation at 23.5 degrees, they would move by a significant amount from where
They
they
will.
are right now.
They will.
Theoretically, they would, yes, they would, but they haven't. There's thousands of years of evidence, archaeological evidence, that they have not moved. The tropics have not moved.
Tropics are moving, according to Larry. Definitely moving.
The tropics have
Yeah,
not moved.
few 100 feet a year.
Listen, I'm not talking about temperature, right? I'm
No, I'm
talking
talking
about
about the tropics.
the movement of the sun at the ecliptic, right?
Exactly right.
There's a precession of the equinox, yes, but the tropics on Earth have not moved.
Yeah, they move several hundred
No,
feet every year.
no, they haven't. You know how
Well,
we
then,
know?
when Larry here, ask him.
Well, hear me out, right? Even the Georgia Guidestones, Mike, check.
What about the Georgia guy?
Even the Georgia Guidestones that was recently built, right, has a little drilled out hole that lines up with the star Polaris.
Is it?
Theoretically speaking, right? Hear me
Have
out.
you verified? Have you verified it? Were you there?
Hear me out. If the Georgia Guidestones was still here 2,000 years from now, if you look through that hole, Polaris would still be there.
No, it won't. It's
I mean,
moving away.
Polaris,
It's moving away. Observably. Observably. You talk nonsense. You don't know the facts.
the Polaris is moving. Forgive me. I misspoke.
If you were to go to the Georgia stones, you'd see that you have enough field of view that Polaris can move significantly, and you can still see it.
You're right. You're right.
So that's not indicator for anything.
Forgive me. I misspoke.
The Egyptian had a different North Star. The
Listen, I
stars north
misspoke,
and then.
dog. You hear me out? You hear me
I
out?
hear you.
Hear
I
me out.
hear you.
I misspoke. Okay, so I'm correcting myself. I didn't mean to say Polaris. I meant to say that is a phenomenon that you can see right now, but that will not always be the case. You're right. But the sun on the equator, right, on March 20th, on the horizon, where the sun is on the horizon and at the equator, there are ancient architectural monuments, megalithic structures all around the world, temples, ancient temples, some 800 years, some 1500 years, some thousands of years old. And they were built by design with specific windows. Now, there's a name I wish I remembered, but it's similar to a gnomon when it casts a shadow. But instead of a gnomon, they literally use a god ray, or what do you call him? A crepuscular ray or some shit like that, right? They use that to measure time. And if the alignments were not precise regarding the angle of the sun at the equator, right, with a specific tropics, because they also had solstices. So on the winter solstice, the sun would also shine from a certain angle onto the earth, and it would shine through a little porthole, and that little porthole would then radiate a god ray into the temple, and always from time to time to time would shine its light upon a certain statue or a certain area in the temple that was considered highly sacred. So like usually it was an idol of like a pharaoh, right? They would put in a certain place in the temple, and that god ray on the winter solstice from year to year to year for millenniums would always shine its light. And even today, they still shine their light at the specific time period on the horizon. If there was axial tilt, if there was a wobble, these monuments would not be in line anymore, but they are still in line. And some of these monuments, some of these temples are dated to thousands of years old. If we're talking about 2,000 years, you would have at least a 25 to 50 degree difference from where the winter solstice is today, and the sun will not be at the right angle.
Well, nice story, bruv. Can I see it? All you said now?
Yeah, there's plenty of independent astronomers. There's papers all over it.
What papers? I need to see the rays hit the monument.
Academia.edu. Look them up. Type in axial tilt
You look them
precession.
up. You look them up and then post it.
The sun's eccentricity. Look it up, dude. There's so many independent astronomers.
It has nothing to do with astronomers.
Yes, it does.
You were talking about a crepuscular rays and certain time of the year that the rays will hit certain monuments. I want to see it. I want to see they still hit it at the time they're supposed to.
Listen. Even NASA agrees, right? You know what NASA has to say about this matter?
Don't care what NASA says. I want to see
I'll
it.
tell you. But I'll tell you. I'll give you the link as soon as I'm driving. As soon as I go home, I'll send you the link. Promise. But NASA has even said that the Mayan temples that still line up with the solstices and the equinoxes today, even though they were built thousands of years ago, right? They say that in order to rationalize their model of the wobble, right? They say that the Mayans built the temples with a future generation in mind, so that they built the temples in a way that it would line up in the future, not in their time, but in the future they would line up, and that future is us.
Well, the Mayan can do whatever they wish. The Mayan can do whatever they wish. If the solstices move, if the tropics move, all Mayans' intentions are out the window. Check it now.
What'd you tell that dog?
Told him to be quiet.
How do you say that? That was cool.
I told him, check it. He will cut his big balls. Maybe he will be quiet.
See, according to my model, the Earth has never moved. It's the only thing that's fixed. Everything else moves.
I didn't claim anything.
The sun, the moon, the luminaries, the wandering stars, they all move. They all have their own specific circuits, right? Some are in lockstep, some are not. Contrary to popular belief, the sun is not in lockstep with the stars. That's a big erroneous assumption by even many flat earthers. Still assume that the sun is in lockstep with the stars. Yes, the sun seems to have the same acceleration or speed as the stars, but they're in separate circuits, and they do. There's a slight dilation between the sun and the stars. That I don't believe the sidereal year is actually accurately recording that speed. But like, if the sun is always fixed to the earth at a certain circuit, and that sun has never moved from its circuit, it's not deviated from its circuit. It's been consistent. There's no such thing as like erratic motion of the earth where it wobbles, and in the tropics would have to move. They would have to move. But that's not what the ancients recorded. That's not what we see in reality. The tropics do not move. They have not deviated from their specific line of demarcation. They have not. I stand firm on that. The sun and the moon are consistent. The moon isn't going away an inch a year, a couple inches a year. That's not happening. That's why also that you can't follow the tropical year the way that modern astronomy follows the tropical year or the solar year, because they use the backdrop of the stars as their foundation. And when you use the backdrop of the stars, which is what a sidereal year is, and then you reference the tropical year against the sidereal year, and that just creates more of a headache. But if you're coming up with the year, right, by the revolution of the Earth around the sun, and they use the stars as a backdrop to see when the Earth has actually made its revolution, or when the sun has made its revolution. There's a specific metrics, but it's all based on erroneous theoretical understanding of the universe. Once you find that out, then you can figure out the equation of time properly, which then can unravel and lead to a better model of the geocentric Earth, flat Earth. I think the main puzzle to this all is time and the equation of time. Not enough focus is dedicated to that. Now we leave it up to some guys in Greenwich, right over there in Switzerland, somewhere in the Netherlands over there, and they come up with the model of time using atomic clocks and this and that, and theoretical physics. Don't you know what I mean? Like,
dude, you're free to make your own model, man, but you guys don't, because when you do, it'll just be disproven. Right, like I've sat here for years listening to people ask you guys to make models, and there were points where
You mean like a map? Or like what model?
yeah, exactly. What model?
Yeah, do you want like a map, or do you want like a map or like a model of how the planets are moving, or what? You want to know where like the land masses are? What are you talking about?
Sure.
What?
Sure. Personally, I was not saying I wanted a model. I was just stating the observation that I've made over the years, that whenever a model is put forth of the flat Earth, be it a map, a model of one observation or multiple observations, and anything of the sort, it's just so easy people can easily see where the flaws are or where the incorrectness is. So the desire to make those kind of things just really isn't there anymore. And that's very telling.
You think models can depict reality? Is that what you're saying?
What do you think they should depict?
I think that you can use models for things for sure. I just don't know if they depict reality exactly as it is. Do you think they do?
So you would take time to make a model that doesn't depict reality?
No, I think models are like, they're like mathematical constructs, right? I mean, even when the guys were like coming up with the heliocentric model with Copernicus and this and that, they were basically saying, oh, this is just easier to work the numbers around. They weren't saying like, oh, this is definitely a depiction of reality. They were just saying this makes it a lot easier for us to do this math.
Is that true, though? I don't think that's true.
What, you don't think that it's a little more difficult to do the math if you did geocentrism versus heliocentrism?
Oh, yeah, it's definitely more difficult, and it violates a whole bunch of laws and just the overall principle of parsimony, but I don't think that was their reason at the time.
You don't think that was their reason, was to make the math easier, like in Copernicus's day, where they were probably didn't like have a calculator?
No, I don't.
That's
I think
interesting.
that could have been part of the reason.
So yeah, like I mean, you're talking about people. Yeah, you're talking about
Nonetheless,
people way before gravity. But what before Einstein came along, all that. You know what I mean? These guys couldn't prove any of that nonsense. So like, they were definitely doing it as just a mathematical construct. They would never say, "Oh, this is for sure the way it happens," without ever testing it, right?
well, there were cultures like the Greeks and Romans who had their ideas of gravity. It's not like Newton and Einstein were like the first ones to realize that things fall to the ground. They called it impetus in Greece. Um, but yeah.
No, when I'm talking about gravity, I'm talking about like the theory of relativity, of why when we look out, it looks as if the Earth is in the center, but it's not. That's what I'm talking about. I'm not talking about things falling to the ground. You know what I mean? So like, yeah, that when everyone was looking out, they were all like, "Oh yeah, it looks like Earth's at the center and everything's going around us." This is hard to figure out mathematically. If we just switch it to the sun in the center, look how easy this is to figure out mathematically. And that was it. I don't think they were stating at that point that they're like, "Oh yeah, because it's easier mathematically, we know for sure that we're going around the sun."
Um, sure. I think it had a lot to do with, yeah, kind of like you said, observations, and then the mathematics on top of that, and like what's more parsimonious. Do we have all these epicycles and all this other stuff going on that just makes things way more complicated, right? So they're kind of weighing their options there.
Yeah, I guess, but now we're like way more mathematically advanced, so we don't have to think like that anymore.
Okay.
Yeah, so like the mathematics work in a geocentric model just as well as a heliocentric model. It's just if you're in kindergarten, we're going to do the heliocentric model because it's 2 plus 2, and that's much easier for you. You know what I mean?
Yeah, I get what you're saying, but I don't think that it's only covariantly that it works. It doesn't like actually work, right? You're violating like tons of laws on top of the idea of parsimony, on top of getting incorrect values for predictions, for observations, when you do a geocentric thing. But this is diverting from like what we were talking about before, with people trying to make flat earth models and how that usually goes.
Well, I feel like the model that you're suggesting, you had to make a lot of assumptions on distances in order to get this parsimony. I'm not sure. Can you explain parsimony to me?
It's like a form of Occam's razor, where you should first be going with the things that require the less assumptions. So Occam's razor is like when you have two competing hypotheses that have equal explanatory power. You should choose the one with the least amount of assumptions, right? The principle of parsimony is like your ideas should start with things that have the least amount of assumptions before you start moving. It's only when that those ideas get disproven, then you should move on to more complicated ideas and ideas with more assumptions.
So, like, just real quick, so using that principle to explain seasons in your model versus seasons in my model, which one would you suggest takes more of like the Occam's razor approach?
The globe, obviously.
Really? That's interesting.
Yes.
The globe, because don't you have to like invoke a tilt and a certain distance to the sun and this and that? You know, like when in the flat earth model, it's just like, yeah, when the sun is around the Tropic of Cancer, it's summer for the areas that are in the Tropic of Cancer. When it's at the Tropic of Capricorn, it's summer for those places that are at the Tropic of Capricorn. So I don't understand your theory being more the sun is actually further away from the northern hemisphere, yet it's summertime, but that's because of the tilt. And then it's because the light rays are coming in parallel. Like, you don't see how you're like really having to like make up a lot of things in order to get these seasons to work.
No, I think the light rays coming in parallel is a measurement. But nonetheless, they formulated the globe Earth or the heliocentric models, based off of observations that were made. And right, you can go with the whole flat Earth idea, right? There's two ways you can look at like seeing observations of like the stars. You can say either they're moving or the Earth is moving, right? It's gonna take that much intelligence to figure out that there's two options, right? But when you go with the flat Earth thing, now you have like a whole array of things that you have to support. Like, how is the sun moving? Where is the energy for the sun to move coming from? Where is it coming from for the moon to move? What are these things made of to begin with, right? Like, there's a whole bunch of unanswered questions that you would have to one by one support the answers to these questions to actually have any credence to that model.
Okay, then your model has that same problem, because I could just flip that question back on you and say, why is the moon axial rotation slower than the Earth's axial rotation? And where did the moon even come from?
What do you mean, how is the moon's axial rotation slower? What does that mean?
The moon has a slower axial rotation than the Earth.
It's isn't it gravitationally or tidally locked, right? That's like a prediction of the idea of gravity, right? They took measurements of the moon's size or whatever, and
How'd
then
the moon get there in the first place? So you got to take a step back.
just comparing that to the size of the Earth, you would think, okay, well, if this gravitational thing actually exists, the Earth seems to be much bigger. It would have much more gravity, and so it's going to tidally lock the moon. And that's exactly what you see. There's a few different ideas for how the moon got there. The one that I would say is most supported and most plausible is the impact hypothesis.
So something hit the Earth, a piece of the Earth flies off, goes out into space, and somehow starts slowing down compared to the Earth. Like, why don't those two things stay at the same speed? What's slowing the moon down? Like, doesn't this sound like it's violating one of Newton's laws or something?
Well, like I said, that would be a prediction of this whole gravitation thing, right? So the moon would be rotating when it formed from the debris of this impact, but it's only a portion of the object that hit the Earth plus the Earth's material that formed the moon, right? So it's much smaller, much less mass than the Earth. So the Earth's mass is going to have a much stronger gravitational effect, bringing the moon to a tidally locked configuration. It's like what gravity would predict.
What was the Earth like spinning when the moon hit it? Or when the whatever hit it?
Yeah, the impact hypothesis, they call it like a Mars, similar to Mars-sized object called Theia. And yes, the Earth was rotating at the time.
Was it tilted then, or is that what caused the tilt?
It's posited that that was what caused tilt, though that's with less, someone's hot miking.
Lion, you're hot micing.
I buy new one. They're not that much.
Lion, you're hot micing, bro.
All of them are $8.
Alright, so I'll buy the next one. So you can stay.
I think he's not at his mic. Someone's gonna have to mute him.
I want them to get hit.
Yeah, I don't even see Jeremy in here. But Jace, don't you understand what I'm saying?
Torah?
Like, if what's that?
Is it Torah?
Yes.
Who's hot micing?
Oh no, Lion.
Lion.
Yeah.
And I got this.
Okay.
Continue. That's
But Jace, like, don't you see? Like, if the Earth is spinning, Mars hits the Earth. The Mars-sized object hits the Earth, and it flings off an object. And now that object would be spinning at the same rate that the Earth was spinning. Do you agree, or what?
Oh no! It's not that like it hit the Earth and man, he's still hot
I'm gonna
micing.
take a shower, so it's gonna take a while.
Yo, Lion, you're hot micing, bro.
Like oil.
Let's see, is there a way you could mute him?
I got him. It's good.
Adam too.
Thanks. Yeah, so the impact hypothesis is not like this Mars-sized object hit the Earth and like chucked out the moon fully formed. The hypothesis is that it hit the Earth and all this debris, it caused like all this debris to get chipped off the Earth, all these small, billions and billions of pieces of the Earth's crust and the object that hit it. And then due to gravity, those objects, that debris started clumping together, right? It started smashing into each other, clumping together, becoming larger and larger until it reached the size of the moon.
Gravity would have done.
Well, can you create a
larger
model?
objects around it would have pulled the smaller objects towards it. He's talking about how that's how gravity formed it. That's not how gravity is explained.
Yeah.
The less mass object, the billions and billions of particles that are less mass than the surrounding masses would be attracted to the larger masses, not to each other. Thank you. Try again. Strike one.
This hypothesis
Was gravity different way back then, billions of light years from now?
The hypothesis was made primarily from simulations, right? They plugged in the laws of gravity as we understand them, and the result of this collision is you get a bunch of debris things. Some of them fall back down to the Earth, but the other ones are moving in an angular. They're going around the Earth in an orbit, colliding into each other, forming a larger and larger collective mass until eventually it reaches the size that the moon is currently.
It's getting
if that's the case, we should
bigger
have one giant satellite made up of all the satellites.
Why isn't it attracted the
Kia, you're kind of breaking up,
things
man.
that are around it now? No, it would keep getting bigger. It wouldn't stop growing, and it wouldn't get to a certain size and stop attracting particles around it.
You're really breaking up a lot, but I think you're saying that it could have kept getting bigger, and it did until all the debris had either collected into the moon's mass or fell back down to the earth, right? Once all the debris was gone, there was nothing for it to use to keep getting bigger.
And it did that at the distance that you say the moon is at from the Earth right now. So, like, it has to be a specific distance from the Earth to do that. Or would all the satellites, if we just left them there over time, would have one giant ISS satellite?
What?
It's like the the rules of gravity and this coalition of all of the ingredients necessary to make up the moon from these chips of asteroids going around the Earth. Is there a specific distance between the Earth and now where the moon is, how it formed and coalesced together?
Yeah, it happened at a distance, right? It's supposedly a little bit closer than where the moon is today.
My point being, what I was walking you through, Jace, is you did say you can model this, but then you said in a computer. So a computer simulation is like at that point evidence for you. Is that correct?
Well, right, you have to think, well, like, what are the options here? Like, I can't grab a Earth-sized object and a Mars-sized object and collide them together, unfortunately. But what I can do is look at the observations of the Earth, the observations of the moon that we have, the laws of physics that we've developed, turn that into a simulation and see what happens, and run the different hypotheses to see which one has more plausibility or credence, confidence, whatever.
Yeah, I guess if like you think a simulation is like the same as the real thing. I mean, if there's never been an observation of like another moon forming or something, I don't even know why we would even come to that hypothesis. Like it'd be one thing if someone was like, "Oh man, did you just see that? We just watched something hit Jupiter and create another moon." And then you made the hypothesis for the Earth's moon. But it's like if you don't have that observation in the first place, you're just like telling a story here.
No, you're taking the evidence that you do have along with a simulation of the laws of physics that you know of to come up with a hypothesis, right? It's not a story, man.
You
I take
don't
it
think?
back to a minute. Ed,
Yeah, go ahead, Barrel Rider. Sorry.
I just wanted to take it back to you guys you're on this how the moon forms thing, but you guys were originally talking about Occam's razor. And you brought up the seasons and how using Occam's razor, which would be a better idea of how the seasons work. And
No.
You guys were talking about that, and then when it was over, all the arguments were made. Hey, you just hand waved it and moved on to another subject. Or what about that? How about Occam's razor and the difference in the hypothesis about how the seasons work? You
Yeah.
address that?
Yeah, do you know that Occam's razor is that with two competing hypotheses with equal explanatory power, right? That's the key part. Equal explanatory power. You should go with the one that requires the least amount of assumptions, right? So to me, the flat Earth explanation or hypothesis has nowhere near the explanatory power as the globe Earth, and it requires a lot more assumptions nowadays. Like if you're going to say that the flat Earth explains seasons, then I have like tons of questions for you that you're probably not going to be able to answer.
Well, he just said that when the sun is closer to the tropics, and whatever the sun is closest to, they warm those areas more, making that summer and then winter in the other part of the earth. And what you have to do with the globe is you got to tilt it. You got to you got to do all these different things. You have to make all these assumptions that uh, uh, it's tilted, that the rays are coming in parallel, and I think there's some other assumptions mixed in with that.
Yeah, you have
How
to
is
assume the Earth's a ball.
yeah.
Like
So
nowadays, most of those aren't assumptions; they're measurements nowadays. But nonetheless, right? Just to start with, what is making the sun move? Where's the energy coming from for the sun to move around?
The same thing in your model, dude. Something put it in motion a long time ago.
Okay, but
we're not really.
what is causing it to? Would it have to be going in circles? Correct. It's not just moving in a set direction. It's going in circles. How?
How is the sun moving in circles is just a question. Like when we think about it, that's like me asking you, how is the sun moving in your model around the great attractor? You're just going to go back to the
It's due
Big
to
Bang or
gravity.
whatever. What?
It's due to gravity. The sun is gravitationally
Yeah, but what put it in that motion?
Can I offer something?
The matter that formed the sun was already moving, so it already had momentum. That momentum is conserved because there's not like an atmosphere or anything else to stop the momentum that the hydrogen and helium and all that had that formed the sun. So it's still moving. It was moving when it formed. It's gravitationally bound to the great attractor, and that accounts for the path that it's taking.
That's all assumptions too. What you just said was all assumptions.
None of that is
A lot of them.
But
Ether,
you're
go ahead.
diverting from how is it going in circles in this model that you're proposing.
Yeah. What about like? Have you ever seen like plates? You ever seen like plates spinning on like a stick? You know how people do that? Like
Sure.
spin, and like how like the plate kind of moves around that central point off of the stick. You know what I mean? But it kind of centers back. So like, imagine if like the stars were kind of doing something like that, and like, what if we called it like dark wobble? You know, like what if that's explaining it?
You're free to call it whatever you like.
Right, but I'm just saying, like, because like you were saying about Occam's razor, and I was saying like we can replicate that. We've yet to replicate, let's say, like orbital mechanics. You know what I
I
mean?
like that. Dark is
Dark
in
wobble, bro.
vogue right
Dark
now.
wobble.
Dark is in fashion.
Dark
Yeah,
is
yeah, I like it, bro. Yeah.
dark is in, huh, Essie?
Dark wobble, man.
Dark is in, guys. Yeah.
Jace, you said something about you can measure the sun rays as parallel. What instrument do I do that with?
The irradiance of the sun, which is another problem for you, by the way.
Wait, I measure it with what? With what?
Like a solar array, a type of instrument that's used to measure like the irradiance of something. The sun, in this case.
Does it like tell you how many inches apart each ray is or something, or what's going on here? Can you break it down for a simple man? I know you're a really smart dude, but
Yeah, I would just say, right, you'd have to look at exactly on the detector these detections are happening. But right, I'm not super familiar with that. I'd have to look into it a little bit more to give you the exact specifics. But I have, I'm aware that these kind of things are done.
didn't Eratosthenes assume parallel light rays because of he just assumed a distance and size or something. So like now you're saying we can verify those parallel light rays?
Yes, exactly. Like when I'm using a charged coupled device and like a photomultiplier, right, I can see where the detections are actually coming from, like the X, Y, Z, and T coordinates of where the detection was made. And you can do that with the things that kind of measure the spectral irradiance of the sun. And if you control it in specific ways, that give you a good indication of if these are divergent rays, parallel rays, etc.
And we don't need to know anything about the light source or distance of the light source or size of the light source. Is that correct?
No, you just need to know that it's a light source, right? But again, like I'm trying to talk about your model, and you keep, right, you're just fishing for where like my knowledge ends, right, instead of trying to support your model.
Oh, well, you're talking to a creationist, so it's going to be hard, unless you believe in creation for me to explain that to you. Like I think that the sun does what it does because it's in a circuit and it follows the law that God gave it.
I but like you don't see like the massive contradictions like when you hold um what you suppose are authorities, which are really just people that are scientists. You hold them to this crazy high standard of evidence, and you have to manipulate independent variables and dependent variables and have a hypothesis and show the cause to an effect. Right, for the globe stuff, you have this crazy, ridiculously high standard, but for your actual beliefs, it's like the complete opposite side of the spectrum. It's like, oh, God did it. It's it's in the Bible, and that's good enough. Like,
Well, mine's a belief system. You're claiming yours as fact.
so you're saying it's not what you believe is not a fact.
Well, I can't prove it to you with science. I can't prove that God created the earth and set the sun in its circuit. You're the one claiming you can prove exactly how the sun got to where it was, what it's doing, and all that. So I'm just asking you because from what I've read in what I look through, it says no one will ever know the answer to that.
Yeah. Well. Right. I don't actually say in that, like, though there aren't like theorems or formal proofs of how the sun got to where it is, right? I would more accurately say we can provide evidence and hypotheses where we can ascribe different confidences to these observations, data, measurements, etc., for how these things came to be.
Yeah, I get that. So you observe it and then you plug some numbers in and make up your own story. And I just go with the story that's been given to mankind a long time ago. So it's like you're like just making it up as you go when what I believe hasn't changed for, since the beginning of time.
Oh, semi sort of, right? Like you're gaining knowledge, right? When you're learning something new, you're making up what you know, right? You're making observations and you're making up explanations for those observations and testing their accuracy and their precision.
I agree. On Earth, I can do those things. I would never turn to the heavens and try to explain it like that.
And say, well, that's one of the areas where I differ from you, scientists differ from you. We do think that you can apply the same rules that you apply here on Earth to things that are outside the Earth.
Yeah, I would say that's flawed logical thinking.
It's just an assumption too.
No, you have to show that there's actually a reason for not being able to apply those same laws.
Well, no one's been there, so no one can.
You have to show that like the physics is different in some way that we can't understand. It's not the same as the physics here on Earth.
Yeah, you'd have to look through my paradigm in order to know that, right? If the Earth is flat and everything's going on above it, obviously the physics aren't the same for what's on Earth and what's above it, right?
There's a lot of places that, in your science, Jace, where the laws that we have that govern what is going on here on the Earth don't work. The places far away in the little tiny areas, quantum. So there are some discrepancies between what we find here on Earth and what we observe happening in what they call outer space and things like that. Like just having to have dark matter is one of those things.
I don't think so. Like, right, you can eliminate dark matter and dark energy entirely, and you're still going to have the Earth and all the physics on the Earth. Those are hypotheses that have been put forth because of observations, but they're not observations related to the Earth.
Yeah, I think he's actually extremely right there, because they are observations that when we applied the Earth's physics to, the math didn't add up, so we had to add in a placeholder number in order to fix that problem. And then on the quantum level, just like he said, again, the same problem happens.
But what happens? I get you for the difference between the predict.
Breaking up for you guys?
Yeah, he cut out. I think the ether is knocking at his door, getting ready to unify all this science for him.
Yeah, I'll be right back, but I'd like to hear what quantum discrepancy you think there is.
Thought that there were discrepancies in the gravity of quantum, like that you can't apply Newtonian or Einsteinian, physics about gravity, quantum, like you can, in our reality that we have. I mean, I guess quantum is a reality. It's just small, looking at the small part of our reality. But I thought there were discrepancies between the gravity uh, we see at the quantum level, and that's why they go into these things of like stuff popping in and out of existence, and all these really wild sort of crazy theories about explaining gravity and things like that in the quantum level. Am I wrong about that?
That's what my understanding was. Like, the moon formed differently from how an atom forms, right? Because they use different forces, right? So I don't know.
Is my mic better?
Yeah.
Can someone say, is my mic better or no?
Didn't you hear me? It sounds good to me.
Yeah, it sounds good.
Um, so what I will say is, right, that's still an open question. There's some physicists who the current status of the situation is, right, people like Sean Carroll and others have developed quantum mechanics or quantum field theory within general relativity. But the thing with it is that the predictions are the same as just regular quantum field theory and just special relativity, um, up until a certain energy scale, which is a very high energy scale. At this really high energy scale, the predictions actually do differ. So you could differentiate between the two frameworks. But the problem is we don't currently have the instruments and the engineering to actually do those kinds of tests. So in my opinion, it's just more intellectually honest to say that we just don't know. It could be compatible, it could not be. We could someday test these things and show that it is compatible. We could someday test them and show that it's not compatible. So it's better to just say that you don't know, but some physicists will try to make arguments, and chemists and others will try to make arguments that they aren't compatible due to X, Y, and Z. I don't agree with them. I don't agree with that method. I think it's just more honest for now to say that you don't know.
Can you apply that same exact thinking to the general relativity, like reverse the two scenarios?
What do you mean?
Like you said, basically it could work within the framework of general relativity, but we're not sure. What if a quantum guy was like, well, the quantum stuff could work with on the big scale without general relativity? Like, couldn't that just be reversed back and forth there?
Kind of. It kind of is already, right? Like the quantum mechanics has its classical limit where it just turns into either Lagrangian, Hamiltonian, or Newtonian mechanics, whichever one you choose to work with at that point. But it's still, you're within the limit of quantum mechanics, so it's still quantum mechanics there. The the discrepancy that you're talking about is the more larger scale than that, the relativistic scale, which is a different limit that, like I said, we can't really test yet.
So we were talking about a few minutes ago was what you made the statement that we use the physics uh, we know and make models and things like that, but so we can, as we showed here, that physics that we know here on Earth don't apply perfectly well to what observations we make out in space. And even you are saying that there's some discrepancy. Some people have some different ideas about what's going on the quantum level. So that the point is that we can't use the physics that we have on Earth here, make those models about what's going on out in space, because those physics don't work out there in a lot of ways. And even on the quantum level, there's still a lot of debate about that too. So, our making models and stuff based on the physics that we have here on Earth kind of incomplete.
Which is weird because that's what the Bible predicts.
Hang on. Give me a couple minutes and I'll be back.
I mean, I thought we were trying to get to Occam's razor, like the simplest way to explain, and this is getting complicated, isn't it?
Well, yeah, you know what's funny, man? It made me think of like the Flat Earth Society, where like, you know, basically people are like, yeah, well, what's your alternative to gravity? What's your and then that's where they came up with, well, fuck it. You know what I mean? We're going up. You know what I mean? Like you know what I mean? Just fuck it, man. Like you know what I mean? Like, you know, just if you want an explanation, here's one for you. Like, you know what I
Yeah.
mean? Like, you know, out of all the possibilities, like, you know, and I feel like it's almost like if flat earthers took some stance, like, you know, like I was talking about, like the dark wobble to explain the procession or something. You know what I mean? Like, you know, like, or like, you know, what they, you know, take any one of their points that are they take to be a fact, like the tilt. You know what I mean? Like, the fuck is that? You know what I mean? Like, we're tilted, but the North Star is always right there. And like, you know what I mean? Like, that's an assumption.
Yeah, it's like they're just making it up as they go, right?
Well, I mean, kind of, but like, you know, I mean, if you will, the globe model has its efficiency. The issue is that, like, it's like, you know, take when they try to say that you can't do celestial navigation on a flat Earth because of whatever, you know, well, we could just come up with like, well, that's dark refraction. You know what I mean?
Yeah, we have. It's called an azimuthal grid of vision, right?
Well, no, but no, but that's not good enough. Just so that you need something mysterious, like, you know, dark refraction. You know what I mean? Quantum refraction theory. You know what I mean? And that explains away that problem that nobody can explain, but it's might be good enough for them.
Gotcha. So make it like incoherent more so.
Well, it doesn't matter as long as it's well, no, it's coherent, but it's, you know, it's paradoxical but coherent, and if you don't get it, it's because you don't understand.
You're
That's
not
it.
educated enough.
Yeah, that's how you win. Okay, I got you.
You know, well, I mean, that's what they're asking for. Is they're like, well, what's your other model? Okay, fine. Well, I got a dark, you know, the procession is easily explained away by the dark wobble. You know what I mean? The idea that you can't, you know, use celestial navigation on the flat Earth is bullshit. And you're saying that the reason that ground positions match up, well, that's not the case because you've got, you've got quantum refraction happening. So therefore, you know, you would never detect the curvature if there ever was any anyway.
Yeah, I'm sorry you can't understand this. That's not my fault that
Right,
you
you know
don't
what I
get
mean?
it.
You just don't understand. You just don't understand it. You should go get an education or something. You know what I mean? Like that kind of fucking attitude, and then maybe they'd be like, "Wow."
Yeah,
Because
use
that's
the word dark just to get out of jail.
I don't know if that'll help you, but
Dark
like, yo,
quantum.
what do you think about that quantum refraction?
Quantum refraction.
Yeah, quantum refraction. You know, Jace, this is why we can't. You know how you guys say like the ground positioning of the stars, you got to put in the Haversine formula or some bullshit, right, and all this other shit. Well, that's only because of dark refraction or quantum refraction. So forgive me. It's the dark wobble explains away the precession, and then quantum refraction explains away why it looks to you like it's curving and why celestial navigation, why you would think you're on a globe. You know what I mean? Like, is that good enough? Like, you know what I mean? Or can't we just be as honest and be like, well, we don't really know, but here are the possibilities. You've got the globe explanations and quantum wobble, you know? It's just like, because, I mean, they're great, you know, like the globe offers these great ideas, but either way, it's like, you know, because you know what I mean? Like, what if I just came out with like a paper and tried to put it forth and like, you know, like, would that make it good enough?
Oh
Oh,
no,
you
your
were
mic.
muffled.
Yeah, your mic's shit, Issa.
Yeah, I know.
Oh, that's better.
Well, someone carry the torch for me. I'm a little busy anyway.
No, I was
But
just
I,
going to ask Jace. Jace, you made the comment on different energetic scales earlier when you were talking about whether or not you're unifying this stuff. So when you say different energetic scales, what do you mean by that? Are you kind of alluding to everything is energy just at a different scale?
1 second, but can you elaborate more? What in what sense?
That's what I'm asking from you. You
I
made the
don't
comment
know what
on
you're referring to. I'm not sure what
you,
you're referring to.
you made the comment earlier. You said, well, on different energetic scales, different rules apply, blah, 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 blah. So when you were kind of laying this idea out of different energetic scales, what do you mean by that? And could you give like a definition of energy that would be residing upon these scales? What is energy, and what do you mean by different energetic scales?
Um, I'm still I don't know what really you're referring to because that's very context specific. I know I have referenced things where people have said that like the Cavendish can be explained by electrostatics, but right, when I say that that's happening at a totally different energy scale, what I mean is that you can do electrostatic experiments in the lab and come up with the Coulomb's constant and all the variables involved, per the charges involved, right? And you'll see that, like, when you apply that to the masses and stuff in the Cavendish experiment, that they should like smash together at super quick speeds
I don't.
and force and stuff because the electrostatic constants are much larger. They're like 10 to the 26
Yeah,
power larger than the gravitational constants.
yeah. No, I wasn't talking about electrostatics. I know lots of times you try to read in what the question is to make some sort of
Well,
explanation that
I
I'm not
don't
asking
know.
for.
I don't know
I
what
said
you're
earlier,
referring to.
you made the reference in the question that Torah initially asked you, right? And you referenced on different energetic scales we have different rules that apply, whether it's Newtonian, whether it's quantum dynamics, whether it's
Yeah, I got you now.
you know,
I wasn't
all of.
talking. Sorry, go ahead. Go ahead.
I'm just you said on these different energetic scales as you go up or you go down, right? So that you're alluding to everything being on a energetic scale of some sort, and there's some sort of sliding scale, right? Whether you're moving up an octave in energy, if you want to think of it that way, or whatnot. So I was just curious as to when you said that, what you mean by energy and scales.
Yeah, I shouldn't. I don't think I did, but if I did use the word energetic scale in that context, I shouldn't have. But I don't think I did. Like energy, when I'm talking about energetic scale, I'm talking about things in terms of um, the magnitude of the strong nuclear interaction is typically what I mean when I say that, and that's usually in reference to things like I said before, the Cavendish and whatnot. What I was talking about earlier is more I would describe it more as regimes of physics, right? There's like at a specific scale, like size scale, um, you have I guess you could say it wouldn't be a scale, it's just at a specific energy. You have like the quantum mechanics. Then there's a limit, right? You get to a certain size of an object, or it has a certain amount of energy, or wavelength, or momentum, whatever. So usually these things are determined in quantum mechanics by the de Broglie wavelength. So it gets to a certain size, and then the h bar in the frequency of the path integral you're doing goes to zero, which means now all the equations simplify, or you could say turn into the equations of classical mechanics. So at that point, you can choose to, depending on which path you're going down, you can choose to describe it in Hamiltonian, Newtonian, or Lagrangian mechanics, right? Then you get to, but the quantum, it's still quantum mechanics, right? It's just h bar has gone to 0, so you're not having to work with like the Schrodinger conditions or the Feynman path integral conditions, etc. Then you get to another. So there's like the quantum regime, the classical regime.
Yeah.
Then you get
Yep.
to like the relativity, where if things are moving very fast, a significant fraction of the speed of light, you'll start to get into the limit of special relativity, where you have to use those correction factors. And if you're talking about things that are very large, have a lot of mass, then you start to get into the limit of general relativity, where you need to consider those kind of correction factors.
Yeah, along all these scales and these different mechanical, I guess you would say, points in which you would switch to like a different application. You say these things, right? You were using the term things. Is it a thing throughout the whole entire scale? Meaning, is it thing isn't necessarily a technical term, so I don't know if you're talking about a mass. Before you had mentioned energy. What exactly are we talking about? I know once we get to the quantum scale, what else could best describe what you're measuring, metering, or predicting, other than the term energy at certain levels? And if we're calling it energy, what would be kind of your definition of energy? And I'd also be curious as to your definition of mass when you're talking about masses, once these energies become condensed into the form in which we would have a solid mass.
Well, right, that's a lot of questions. So it's going to require a bit of talking to answer. To start
All right,
with,
then just disregard, actually, because I actually have to run, so I won't be able to stick around for the answer. So to be continued.
Sounds good.
I don't know what that was about, Napalm, but thank you.
For what?
Whatever Jace's fucking long-winded explanation was going to be.
Boom.
Very winded. I'm sure it would be very winded, but you're welcome.
Yeah, most people just choose to use the mechanics of the kind of scale that they're working with, right? So if you're working with a tennis ball, there's no need to start with general relativity and simplify, go to the weak field limit with the three conditions, and simplify Einstein's field equations into Newton's equations, right? There's no need to do all that work. You could just start with Newton's equation, right? A lot of people choose. But it can be done. It can start. I posted pictures in the PDF of deriving Newton's equations from Einstein. But you could have the situation with somebody throwing a tennis ball. You can do it in a relativistic form. Start with Einstein's equation. Get it eventually.
I can hardly hear you, Jace. Your microphone's horrible.
Yeah, your mic sounds like dog water, bro.
Hey, can I ask you a question, Jace? What's your opinion on you know how there's like that phrase of like nature abhors a vacuum? Like, where does that arise from in like classical, whatever? Like, where does that arise from?
I think is my mic better?
It's still a little shitty, man.
How about now? How does it sound? Still terrible?
It's still a little muffled, but go right ahead. I can hear you.
Yeah, your whole thing about the vacuum, right? I feel like that's kind of like a philosophical position of just like every time you have to break something down smaller or, um, remove objects from a certain area of space, right? There's always something new that you find. So it's just a cute little phrase that like nature always gives you something new to discover whenever you're trying to make a complete vacuum.
It doesn't have. It's not rooted more in like a scientific kind of like a maxim almost, right? Though.
Look, it could be, uh, right? There's different, and when you're talking about a vacuum and science, there's like different concepts. So you have to be like really specific. Like you can remove all the air from, you get a vacuum chamber, remove all the air using a pump, right? And you could say, oh, this is a vacuum. But, in more exact terms, it's really just an area of really low pressure. And even if you exclude the few gas molecules that are still left in the chamber, even if you say that, oh, we can remove every single one of those, well, there's still these quantum field theory effects that are happening. So there's still really something there. It may not be physical material with the components that make up material, but there's still something there in that vacuum. So it's like every time we try to get to the vacuum, we find out that there's still something there.
Like I just wonder, like even how old that phrase is. You know what I mean? Like when it was kind of postulated.
Pretty old.
Right. Like and that's what makes me think. Like what was there? If let's say it's something like Greek or even something like that, or I don't know how old it would be, but and maybe it's more recent than that. But I wonder if it is connected to like vacuum chambers or what I mean. I wonder where it rose from.
Yeah, I just typed into ChatGPT, so they're saying that it was sort of a Greek idea. Yeah, this concept was prevalent in the ancient Greek and medieval worldviews, where it is believed that empty spaces could not exist in nature because they would immediately be filled by surrounding matter. So yeah, that's kind of interesting. I like that it says in summary at the end, by the way. In summary, nature abhors a vacuum reflects an earlier and incorrect understanding of the natural world that was later disproven through scientific experimentation and the advancement of understanding of physics and the behavior of gases. It's interesting, though.
So do they now say that nature is acceptable with vacuums? I wonder how that. Well, I guess that's just an old saying. I guess. Yeah, I could see where it gets muddied with. I wonder why they say that about gas.
From what it sounds like they said there is that like the Greeks thought that you couldn't like pump the air out of a vacuum chamber. Like you couldn't make a box, set up a pump, and pump all the air out of space in one box. But we now
And they were kind of right, but you
do
could put
that.
gas molecules in there. You're saying.
No. They were wrong. It said they were wrong. They are wrong because we can't do that. We can build a box, hook up a pump to it, and pump out the air molecules. But with our modern understanding, the gas fields that are completely right. But
It's
with our
also
modern
it's kind of the
understanding,
context of nature, not like scientific man-made advancements. Maybe I don't know. You know what I mean?
sure.
Like
But
it's
I
not
mean,
as
I
much
guess
of a
there's
maxim
still
as I thought it maybe.
they'd still be wrong, right? Because, like, I think even you would agree, you go to a portion of the atmosphere that's like for that.
What do you mean? Implying space, you mean?
No, you can go like, what was the guy's name? The Bob Globert guy. He made the balloon that went up to where there was like 0.00001% atmospheric pressure, which corresponds to like one gas molecule per like square.
Not Baumgarten or one of them. Are you talking about? Are you?
No. It's a globe guy.
Oh, huh. I haven't
Baldy
seen it.
wears glasses. Sensible, Mr. Sensible, maybe.
Oh, huh. I've heard of that too. I think I follow him, but I forget.
Yeah.
Where there's that little amount of atmospheric pressure.
Yeah. You can go to a region of the atmosphere where like there's definitive space between the gas molecules with nothing.
Interesting. Because like I was under the assumption, because it's like, does that propose the idea that there's a vacuum, like, or is that just by definition, if there's just no air pressure, it's in a vacuum? And if that's the case, do we go to, like they were saying the moon is in the Earth's atmosphere, which is weird.
Yeah, well, that's where definitions become very important, right? Like when you read these eye-popping headlines that the moon is in the Earth's atmosphere. Well, what do they mean by atmosphere, right? They don't mean like that there's 14.7 psi in the
Well, no, but the idea that there would be any psi.
correspond to that. They mean that like there's 1 or 2 hydrogen atoms per like square inch in the area that the moon is in. Calling that an atmosphere to me is a bit of a stretch, but I could see, that is eye-catching headline.
Forgive me, I got a phone call, man.
No worries. I just said right the headline, right, that the moon is in the Earth's atmosphere, the little eye-catching headline, but really they're talking about there's like 1 or 2 hydrogen per square inch or
Right.
whatever. That would be a significant stretch to actually call it.
Explain it away however you want to, Jason. I'm only kidding, though. Just come at you with the typical, It's in our atmosphere, Jace. But Jace. No, that's awesome.
Well, people do really
That's
try
cool.
to.
I know, bro. I know. I'm not gonna. We don't. I know. I mean, it's interesting to me. I mean, I don't, because I don't know. You know what I mean? But I find it. I always like to take with some seriousness. I don't want to shit all over the ideas. You know what I mean? Because my main issue, it becomes just in the sense of a more philosophical idea. Like I was kind of getting into it yesterday. Like the idea, it's kind of like, that's why I don't mean to be a dick, but it's easy for me to be a dick about this subject in ways, you know what I mean? But forgive me, man, because I like your vibes. I like to be able to ask people like yourself, questions. But it's also like just interesting how without all of the knowledge of like if you just were to live life as though the earth were flat and you had to like even if you had to navigate or whatever it is, it's like all the space knowledge, all the idea of the sphericity and all that matter of fact stuff, you know what I mean, that you might call science and all the rest of it is so it's so inconsequential to like a man's day-to-day life, you know what I mean? It's like weird.
Yeah, I
It's
get what
weird.
you're
It's weird. It's weird to like fight so hard for the understanding of an idea that is irrelevant to 99% of the population. You know what I mean? On
Yeah,
either side,
I get
really.
what you're saying, but to me, I think the truth is important.
Right, but it's so because once you get to the thick of it, it's so almost you're really leaning on what becomes hearsay at some point. It's technically hearsay, whether or not we accept it or not, or whether or not you know what I mean. Machines have run like if you were to radar test somebody at a certain speed, it's still hearsay. You know what I mean? Like in a weird way. And now, whether or not you accept that data to be fact. You know what I mean? Like, and that's all intriguing and like could lead one to believe that the Earth is a sphere. But it's weird that like there are alternative explanations potentially, and you know all of that information is essentially, like I said, inconsequential to the daily routine of people. You know what I mean? In a weird way, it's weird how it's become so volatile. You know what I mean?
Yeah, and I mean, I get um, what you're saying. That like you have to make discernment and stuff, right? Because one person, one man can't do everything. So at some point you have to make discernment from what other people are doing.
It sucks, man. You're jumbling up a lot right now. It's hard to make out what exactly you're saying, brother. But I'm kind of getting the gist of it. But I just wanted you to know. You have to get my headphones so I can listen better.
I tried resetting my Discord, changing my headphone orientation. Is it any better?
It's kind of
Barely.
like muffled a little bit.
It just reminds me of like a mic in like inside of a shirt or something like that, like a headphone mic inside of a shirt. It,
It's really annoying me. I'm trying everything here. napalm still here? Napalm. Good question earlier.
Quiet in here or what?
Yeah, it's quiet. Anybody recommend a TV show?
The TV show From. It's a good show.
Oh man, who's that? Is that Elijah? Because that was really low.
Yep. From. FROM. TV show.
Yeah, I can't tell what you're saying, dude.
Recommend going online and going to WSL.com and watching the surf contest, Tahiti. Uh, that's really beautiful there. How'd the French end up with Tahiti anyway? They've been American.
I feel like watching a good sci-fi show, but there's just nothing out there, as far as I can see, anyway.
sensational pseudoscience. Extraordinary claims are everywhere, but is there any evidence? We are the Center for Inquiry Investigations. We use science and its methods to examine these claims and disseminate our findings to the public. This episode, Flat Earth. With a growing online community convinced that the Earth is not a sphere, we invited a group of flat earthers to join us as we put the curvature of the Earth to the test. We're on our way to the Salton Sea to not prove but reconfirm that the Earth is a globe and not a disk. This better work.
So I have an open browser.
This episode, Flat Earth. With a growing online community convinced that the Earth is not a sphere, we invited a group of flat earthers to join us as we put the curvature of the Earth to the test.
Got an open browser and I there it is.
I see. You still there?
I'm here.
What's up? What's up?
What's going on?
Nothing, man. So you think that we think that light when light's refracted, it slows down, and that's because it's bouncing off of particles in the material?
No, I said that that's what your explanation is of when, when light enters a certain medium and it appears to slow down. It takes longer time, right? So you guys say that the reason that happens is because light interacts with whatever it is inside the medium. For example, a diamond. I gave an example. So it bounces around, doesn't slow down, it stays the same speed, but it bounces around, therefore taking more time to leave. Is that not what you guys say?
I get you said it differently earlier, but yeah, that's semi sort of. Not necessarily that it bounces around, but there's two different kind of interacting explanations.
Okay, would you like to run them by us? Or me? Well, I
Yeah.
was like, there's so many people, yeah.
One of them is what people refer to as the classical or the Maxwell's kind of electrodynamics explanation, which is that light is an electromagnetic wave, and so when it refracts, it means it's at a similar wavelength as the wavelength that makes the electrons in the atom in the atoms of the material oscillate or resonate. And so when the light passes through, it causes those electrons to resonate, and they also emit electromagnetic waves from that resonation. And the superpose of those waves, the superposition of those waves, is the resultant wave that you see, and that's why it bends and changes speed, et cetera, et cetera. Then there's the second explanation, which is the quantum mechanical explanation of like the light. The photons have a path integral, which is defined by a Lagrangian, and the material changes the Lagrangian, and thus the resulting path integral that you get, or the path that it takes through the material, is different than if there was no material there at all, and the velocity is different compared to if there was no material there at all.
Yeah, basically redirection of the light explained differently, one by waves and the other one by quantum. More or less.
Yeah, more or less.
Yeah, okay, so yeah. That's quite an explanation, huh?
It is indeed.
And why diamond? Why would diamond be the one that interferes with light the most? Is it because it's more dense as a material, or?
Yeah, I guess, diamond is pretty dense, and just the resonant frequencies and stuff, right? It's the things that contribute to the refractive index. It has a high refractive index, so it bends the material more, or it bends the light more.
Wouldn't this be the diffraction, or would it be both? Because it sounds to me like diffraction.
Well, you can have like diffraction along the edges of the diamond, right? The light that kind of hits the edges will diffract, but the light that goes through is just it's refracted. It's the path is changed, or it's bent.
I have some questions too. Do we find any of these particles crystal-like in the atmosphere?
What particles?
Was anything in the atmosphere crystal-like?
Well, you can get like water droplets, right? So usually the gas molecules are the atmospheric molecules are gases, but you have some like water droplets and stuff, so that can change the refractive properties of the atmosphere.
Okay, you said water droplets and stuff. I mean, I'm very curious because it just sounds like what we talk about. The more dense the medium, whether it be a diamond or the atmosphere or whatever, the less likely the light is following a constant path and constant speed.
Yeah, I agree.
So you agree with the more dense the atmosphere, let's forget about the diamonds for a second, that light is going to act different than if the atmosphere is less dense.
Yes.
Is it going to change speeds?
Yeah, that's a good question. I would say it will refract, right? And just, I mean, you can kind of deduce a speed from the refraction, but I don't know if you could like directly measure the speed of the light through the atmosphere per se.
But yeah, that's what I'm kind of getting at. I always talk about the bending of light. You never mention how fast or slow it, sped up or slowed down. If it's changing direction, and another crystal like, let's say diamond, and that's quote unquote slows it down, right? Whether it's measurable or not, that's the theory. Then it would seem to be doing the same thing in the turbulent atmosphere where the light is bending and warping and causing all these, crazy illusions or whatever, like where things are bent or magnified or whatever. Like the light would be doing that, right? Reflected light that we're observing, that's all warped, disturbed.
Yeah. I mean, I can agree with that, right? There's definitely some refraction and other weird effects that can happen, and likely there's a change of the velocity of light from that.
Wow, where have you been for the last 6 years? Like that's pretty easily said, and that makes common sense, right? It just goes along with physics and with what we know about light and with reality and with common sense. I mean, it just seems to be correct. So I agree. I think that's why we get the the bridge looking a certain way at a certain angle, or when the light source is a certain way, because it's reflecting and changing speeds and doing all types of disturbing things, as it reaches your eyeball. Especially looking over distance.
Especially when there's a lot of heat rising up, heat haze. That does a big number.
Yeah, I would say that's a big one. Moisture, whatever. I mean, it could be a number of things. Temperature change. I agree on all those things. Say it
all
does.
Of that, yeah.
Yeah, to say it's not a mixture or a variable, or just the first 5 miles is doing this, and the second 5 miles is doing this, and for 1 mile there's a cold, downdraft coming from a storm cloud. I mean, you can't just say it's constant through this corridor, and that's why the mountain is there. No, you can't sell that. Like, that's a tough sell. Anyway, you can sell it. They've tried very hard to sell it, but it's a tough sell, right? Like, it just doesn't add up when anybody can go out and experience, extreme temperature changes. Just travel on the water and just hold your hand up. I mean, you don't need special tools. So if you're viewing an object over that particular lake you just traveled on, of course the light is doing some strange things and making those objects in the distance appear bigger or smaller or higher or lower or whatever it may be, along with the known perspective issues that the human eyeball experiences. So I mean, I've studied this for years now. I'm no expert, but I can tell you what, I can hold my own with anybody on long distance observations and videos and pictures. I mean, I can show you some amazing things that I never thought was possible.
Yeah, you do have some of the best observations over water. I mean, hell, you live there, bro. So, yeah, that sunset with the boat. Yeah, those the sun splitting in half. You want to talk how the sun sets? Yeah, check out some of Rakia's videos.
Well, how any light above you would set. You can actually get measure a flat surface in a field or whatever, accurate enough to know that it's not the earth, the ground itself obstructing the light, and then put a light above your head and have someone, carry that light the same height above the ground into the distance, and the light disappears. I mean, it not only disappears, but it looks just like the sun. Not
Yeah,
hard to
Ricky,
do.
I'm right here in Prairieville, so I mean I see the Lake Pontchartrain all the time. I do HVAC.
Oh, really? I think I've talked to you. I work in Prairieville. I was off of Highway 22 today, so that's a little
Oh yeah,
past Prairieville, but I'm in Prairieville every day,
yeah.
all day. Yeah.
Really? Yeah,
Yeah.
that's awesome. You know where on 42 where the neighborhood Walmart is in Galvez?
Yeah, of course.
Well, I'm in Autumnwoods, which is the neighborhood kind of behind there from Airline.
Oh, nice. Yeah, I mean, I'm in
Yeah.
that area, Highland and Interstate, every day, all day. That particular area and then surrounding areas. I live in Denham. I head central right now. I
Oh,
just
you're in
left.
Denham Springs?
Yeah. I just left your area an
Yeah.
hour ago.
Well, I'm in Hammond right now, put in a Daikin unit.
Yeah, cool. What's your name again?
Yeah, I don't know if you've seen my name is Rex. But yeah, like my company name is Air Innovations.
Air
Been in
Innovations.
business for 9 years. Yeah, Air Innovations.
All right, but I'm going to look you up.
Heck yeah. Whew. But yeah, dude, that's awesome. I know you live in Denham. I figured you were further east, closer to Pontchartrain.
No, I live in Denham. I have 30 acres there, and then another house, a main house, and then I spend 2 months out of the year in Florida, but mostly here. So I'll be in Florida September 3rd. I'm going to Florida for a while, and then Costa Rica on the 23rd.
Man, that's how I want to be when I grow up.
Yeah.
Heck yeah. Yeah, we just moved back down here. Like I was born and raised in Baton Rouge, but I've been in Shreveport Bossier for 14 years, and we finally made the move back, which is pretty cool.
Yeah, I used to own a vending company, and we went all the way to Bossier City. It's crazy.
Nice.
That was a long time ago.
Yeah, I like it up there, but it's just boring. Nothing to do. I'm about to make some noise. I'm gonna go back to mute. But I'm listening.
Well, HVAC, I mean, you've learned all about containers and pressures and all that, and how quickly gas will escape or fill the container or change.
Pressuring up a unit right now to make sure I ain't got no leak.
Right, like right. So you know
I mean,
all
after this,
about
I'm throwing a
that.
vacuum. Yeah, man. It's
Right.
Yeah.
Common
It's
sense stuff, but once you
simple.
start doing it yourself, yeah. Yeah.
Yeah, I've been
People
in
just
business
don't
for
realize,
9
and they don't
years.
think you know what you're talking about.
Right. No, yeah, that's 100%.
So are you guys telling me those O-rings that I posted wouldn't work in a vacuum environment?
Not only would they not work, they would fail very quickly. And if NASA has these special O-rings, I want to see them. I want to know what they're made of, and because we used to deal even with we're dealing with a project right now that just has 140 pounds pressure on a fire hydrant that we have to pass inspection on, and you should see the joints and O-rings that we has to put on these joints just to hold that pressure, right? Like,
Yeah,
it's
not
crazy.
to mention having, something in refrigeration. Ooh, some of the pressure you got there. I mean, and the thing is that these O-rings, even on my gauges, they don't last. They don't even last a year where you really need to go ahead and replace them. So, I mean, for whatever they have up there, supposedly, to last that long, that's the other thing. It's it wouldn't last hardly any time.
20 more than 20 years dynamic O-ring system.
Are you guys referring to Flatzoid's presentation regarding the guy that tested all those different materials in the vacuum for 24 hours, like meat and metal and a mobile phone? Did you see that?
No, I'm referring to the ISS O-ring system and outgassing and stuff like that.
Well, Flatzoid, he was on someone else's show for a few minutes, and he showed a video of a guy that did an experiment in a vacuum with a heat source in their radiation and a mobile phone over 24 hours in that vacuum. He made a perfect vacuum with like dry ice or something, and the phone would just split in two. Everything just sort of dehydrated and crumbled and dried up over 24 hours. All the metal became brittle. Wood just became like oak became like balsa wood. Only in 24 hours.
Yeah, they have no idea. Yeah, absolutely.
The only thing
That's when they said they put the
was a
car in
balloon.
space.
Yeah, exactly. How can that car just be? I mean, they haven't been up there to go and inspect it, but
Well, they showed it on camera. I mean, they said it was just the normal part, which actually you could tell it wasn't. But you know, um, when you think about what they've taught us about vacuums and how violent it is, our atmosphere. You put something up there, you damn well. I don't get it. I mean, they're smarter than me, obviously, right? Because common sense takes a hold of me and says that doesn't seem possible.
Well, they got them this special material that you don't got.
maybe their idea of a vacuum isn't what we think a vacuum is.
Ah, yeah.
Because it's so vast, you know.
Yeah, we've learned over the last year, especially that what they're calling space isn't really that high up. You know what I'm saying? Relative. If you go side to side, like I've traveled as many miles as the ISS is up today. You understand what I'm saying? Like it's not very high up, and I don't know. If the
Yeah, but then they had to shift
under
the
an hour.
they had to shift the goalpost not long ago and include the moon inside the Earth's atmosphere because without doing that, it just wouldn't have worked, you know.
Well, I think more of that's coming, right? So you can look up and really dig deep and start researching the superfluid stuff, which makes their observations and their distances way off. Like they would have to redo everything, where the moon could be a lot closer. You know what I'm saying? So depending on the medium that it's in, they're admitting that the moon,
Yeah, well,
could
that was their
appear
way. That was their way to explain how they got to the moon, right? Because otherwise, they'd have to escape the Earth's atmosphere to do that, and that posed quite a lot of problems.
They definitely have problems. A lot of problems. Heat, cold, radiation, pressure, lack thereof.
Well, in a vacuum, it's the pressure difference that causes the movement or suction or whatever you want to call it. So if you're in the ISS and you have that pressure difference, that would cause a sucking or whatever you want to call it, just like a vacuum. Hoover discovered that, right? He changed the pressure, with a motor and you can suck things off the ground or you can lift the car or do whatever. It's the pressure difference that does it.
Well, we had talked about the Earth or the moon being in the Earth's atmosphere earlier, and I just looked up one of the studies where these headlines came from, and the study found that there's 70 hydrogen atoms per cubic centimeter at the distance at which the moon is at. So like, if you want, you can say that that's the moon going through the Earth's atmosphere, but that's like an extreme stretch. Like, there's orders of magnitude of 10 to the 23rd atoms of gas down here at the surface, right? There's multiples of 6.022 times 10 to the 23rd, and that's the density of the gas here at the surface. Per cubic centimeter. So calling 70 atoms of the lightest element, hydrogen, and per cubic centimeter in the atmosphere, like, that just seems like an extreme stretch to me.
How did they measure that? Did they have like an ice cream scooper on the outside of the rocket on the way to the moon?
That's exactly what I was just thinking. I mean, I don't mean to make fun of it, but I don't even think they sent anything up there to measure it, much less how they measured it. So it's either a theory or a best guess or whatever you want to call it. If you want to tell me you measured something here on
They
Earth,
claim
or
it's a measurement.
yeah, I understand that they
Yeah, they're claiming,
claim a lot of things. Yeah.
They're saying they used an instrument to measure the Lyman alpha lines of the hydrogen. And from those lines, they correspond to a concentration of the hydrogen. Kind of like what chemists do, right? Like, I do sort of the same thing to measure concentration of solutions and solids and gases and stuff in the lab.
Well, that's why the how do you say that word? Spectroscopy observations of planets and stars and stuff, and they try and tell you redshift, blue shift, all of this garble. But like, you can just use a simple color spectrum filter on a lens or on your phone or anything on a camera, and you're not going to get hydrogen and all these different neon and different gases and stuff extruded from these observations here in the lab. It's just, I don't know how they can say that these colors represent different gases.
Well, of course, you can't just put a color filter in front of something and think you're going to get the atomic emission absorption spectra. There's a specific process you have to go through to do that. In the lab, you need to use a diffraction grating and a slit, an aperture, and a prism. Right? There's different components that you need. It's not just a filter. Especially either the grating or the prism, because that's what separates out the different lines, right, at their nanometer wavelengths. So if you have like a 500 nanometer line and a 510 and a 600 and a 650, right, you need a grating or a prism, otherwise you won't be able to separate those from each other.
Look, that's fine down here, right? That's fine here in regular Earth territory. And that's how they pass the lie, right? I'm not saying you, bro. I'm saying the story of the spectroscopy, space spectroscopy, that is. Here in a closed environment with all the controlled variables, yeah, you can get down to exactly what the stuff's made out of, right? But that's a whole different story when you look out there billions and trillions and billions and trillions of miles away. That's a whole different ballgame.
I would say depends on the materials. For simple materials, I could use literally the same exact spectrometer that I would use for kind of astrophysics. For those light sources, I could use that same spectrometer on determining what the simple material would be, something that's just like an element like hydrogen or iron, right? So it doesn't always require these really specific controlled conditions.
Okay, let's say I was to because you're saying you can point something so far away and tell me what it's made out of. Let's say I was to tell you, okay, use your spectroscopy, and I wish I would have thought of this, but I hadn't. The old barrel in the room, and I forget who it was to shut him out. Let's say I was to put a barrel across the room and fill it with something and ask you, okay, have a look at it with your spectroscopy. Tell me what's inside the barrel. Do you think you can do it? Never mind halfway across the universe, just a room away.
Confused as to what you mean. In order to do spectroscopy on an object, you have to be able to receive the light from that object.
Right. And you are receiving the light. You're receiving the
You're
light from
saying
the
I'm in a
barrel.
different. You said I was in a different room and there's a barrel. So how am I gonna?
No, in the same room, a distance away. Like I don't know, pick a long, or you can even put it outside if you like. Pick a long runway in an airport, right? You're on one end of the runway with your equipment, and on the other end of the runway, I put a wheelbarrow and I put something inside, and I tell you, okay, use spectroscopy. Tell me what the wheelbarrow, what's inside the wheelbarrow, what it's made of, and what's inside of it.
Okay, so trying to understand the situation because there's this very specific way that these things are done.
Exactly my point.
If you have a wheelbarrow, right, and it's just exposed, the top is open, and say you have some kind of liquid in there, if the sunlight can hit the liquid in the wheelbarrow and those and reflect off the material and make it to my spectrometer, then I can kind of
No,
tell
but
you
it's closed.
what's in there.
It's closed. The wheelbarrow is closed.
Well, then I can't do if the light can't make it to the spectrometer. I can't do spectroscopy on it.
It can make it, but only the exterior of the object is making it to your eye. The exterior of the wheelbarrow. So you can maybe tell me, yeah, it's made out of wood, right? The light that I see coming from there, it's made out of wood. But there's no chance in hell you're going to tell me what's inside that wheelbarrow, right? Using spectroscopy? Correct or not? Is that a correct statement or not?
Yes. If the light from the material can't make it to your detector, you can't do spectroscopy.
Okay, so when you look at an object and you say that's a star billions and trillions of light years away and it's made out of this, and that, or a planet, and we think it's made of this atmos and this and that, the ridiculous claims that you make, that's just nonsense, right? There's no way to know that, right?
I don't see the relation with your wheelbarrow thing. If the light from the star is making it to your eyeball, I mean, if you can see the star, that means there's light coming from the star making it to your eyeball. So
how do you know it's a star?
Easily just replace your eyeball. You can replace your eyeball with a detector and do spectroscopy on it.
Yeah, but how do you know it's a star? How do you know it's just not some rock?
Well, that's a definition
shining
thing.
How do you know what it's just? It's incredible, like hubris to think that you can even make a claim of what that is, especially at the distances that you claim, which we just went through. Spectroscopy is at best like what's at the outer edge of the object at best, and that's assuming nothing went in between you and that object that's billions and trillions of light years away, so I don't know, man, if that's good enough for you. I mean,
well, right, you're mixing a lot of things here. First of all, you said, how do you know it's a star? Well, in the context of that question, right, before you went into everything else, right, that would be just a definitional thing, right? We call the things in the sky that we can see, that shine and twinkle, right? We have given those a definition of a star. Now, how do we know what those are made of, right? And spectroscopy could reveal to us, like you said, that they're actually just rocks. They're not stars. They have the composition of a rock. So then we wouldn't say that that object is a star. We'd say it's a rock. But when you do the spectroscopy on most of the things that we've defined as a star, right, they turn out to be what we would expect to be a star. And now you can kind of deduce that you're getting signals from inside of the star, not just the surface, because there's a law. There's a black body radiation law and some other radiation laws that refer to the surface temperature of an object, not just stars, but even objects here on the Earth. And then you test those surface temperatures that you're getting in these astronomical spectral readings, and you see that, okay, well, you need these extreme temperatures and pressures to get those kind of conditions to replicate these signals that you're getting. And so that's how you can go through the process of determining the internal components. You need specific densities, so you can't have density without something having an internal portion of it. So it's like deduction of these things on top of signals that you're measuring.
Yeah, that's very nice story you laid out there, but really it's all based on assumption. When we say star, you think of a thermonuclear reaction in a vacuum, right? So that's assumption number one, correct?
No.
No, what's a star?
It depends on the context, but yeah, you can think of it as a thermonuclear reaction, and then you can do the spectroscopy to verify that.
Yeah, based on an assumption. So you think that light that
Based
you're
on what
getting
assumption?
from whatever that is, you think that's coming from a thermonuclear reaction, trillions and billions of light years, miles away, in a vacuum. That's what you're assuming.
The distance is a different process. We're just talking about the thermonuclear part of this, right? And so that comes from spectroscopy, right? I said there's the radiation laws, the temperature radiation laws, like the Rayleigh-Jeans law and Planck's law, things like that allow you to determine temperatures of objects based off the radiation that they're giving. Then Cecilia Payne developed the correlation between the ionization states of elements in the lab, like sodium, potassium, calcium, and these extreme charged states like 14 plus, 15 plus, right? And these require these in order to ionize potassium and sodium and calcium and all those things to these extremely positive states, it requires extreme temperatures and pressures in the lab. So when you see those exact spectral lines in the spectrum of the star that you're analyzing, right, there's no evidence to say that it's not the process that you can replicate in the lab, right? Or the conditions that you can replicate in the lab. So step by step, you deduce these things.
Nice story, but there's absolutely no way that you can reproduce those set conditions. So it's a cool story, just an observation based on spectroscopy. You witness something and you deduce the story out of it. There's absolutely no way that you can prove this. And I mean absolutely no way that you can prove this.
It's done in labs every day. You can replicate these things.
Yeah, you can say that, but there's absolutely no way you can recreate the set conditions out there. You can just point something to it, get a light spectra, and then make a story up. That is all that you can do. You have absolutely no way to prove that out there is something that's made out of gas in a vacuum doing a thermonuclear reaction producing this. It's just a story. Just a story. Just don't try to sell it to me, and don't try to say it as a fact. It is not a fact. It is just a story.
I mean, Copernicus himself said that. Oh, my bad. Go ahead.
Yeah, it just kind of sounds like projection. Like it's really not that difficult to actually replicate these things, right? Like atomic absorption emission spectrometers do it all the time. There's also literally like nuclear reactors, nuclear explosions that are replicating. I don't get it. It is a fact. You can see these things with your own eyes. Like, I don't get it, man.
Don't straw man me. I
All
never
right.
said anything that you can't see these things. Do not straw man me. I said what I said. Go on, Jeremy.
Okay, even Copernicus said that no conclusions can be drawn from astronomy, and no hypotheses can be can be done from astronomy. You can't draw any conclusions from it. He knows because he was looking.
Well, thank God we don't base our scientific knowledge on what like one person said or what people say in general. And even the one thing we used to really give credence to Copernicus for, the Copernican principle, is now in like dire questioning. So using his authority as some kind of slam dunk argument is just insanity.
I'm not saying I'm not saying it's a slam dunk argument. I'm also not saying he's the only one. He's the only one that thinks like that, because I would also tend to agree that no, you can't do any hypotheses and you can't draw any conclusions from something when you're just looking at it.
You just looked at it and made up a story. And not even you. Somebody else looked at it for you and made a story up for you, which you're trying to sell right now.
I've done stellar spectroscopy myself. I've built spectrometers for that. But nonetheless, right, that's just a lot of projection, right? And Jeremy did an argument from authority, right? There's hundreds of thousands of other scientists who would say you can draw conclusions and make hypotheses from astronomy. So, like, just saying.
Oh my God. I didn't make any argument from authority. I gave a quote from Copernicus. Okay, I don't know what you think just happened. Stop making shit up about me, please.
Yeah, you gave a quote from Copernicus. Big whoop.
Yeah, well, I didn't do what you said, did I? Big whoop. Stop fucking making up shit about me, please.
Jeremy, we don't draw conclusions. We don't say what it is. We can't.
Oh, you don't?
But
Okay. That's
no,
new. That's news
no
to
one
me.
says what it is. You keep asking. So what
Oh,
it
okay.
is? What is an electron? We don't know. But we
no
know how it behaves. That we can describe.
There's no point.
Oh, you mean
quoting Copernicus, because he made lots of other quotes as well, didn't he? He did say, "It's indeed as though seated on a royal throne, the sun governs the family of planets revolving around it."
Yes, I didn't give you every quote Copernicus ever said. I just gave you one quote he said about something that was pertinent
Right.
to the conversation.
So when was it? How long ago was it?
Dude, it's just a quote from Copernicus, guys. Don't get so. I know this scares you, and because a lot of people agree with it, but don't get too worried.
Well, Einstein said they wouldn't be able to build an atom bomb. So this is in theory, this is all good, but they would not be able to build it. And they did.
Yeah, that's why quotes, which are just arguments from authority, are worthless.
So if you
People
quote
are
someone, it's an
wrong
argument
all
from
the time.
authority. If you quote someone, that's an argument from authority.
Most of the time, yes.
Are citations and papers arguments from authority?
No, those are not. Well, scientific ones at least are not.
So it seems we veered off topic. What were we talking about again?
It started with the
51.
atmosphere and gases and the moon being in the Earth's atmosphere. Then
And
we
you
moved
telling me
on
what
to
stars are made of?
No, you
And you
diverted
telling
to that. I was talking about the research paper where they actually measured the claims that you guys make of the moon being in the atmosphere and what the exact claim is that the researchers were making. Then you guys diverted to spectroscopy and stars and because I brought up the spectroscopy that they were doing to measure the hydrogen around the moon. So then, of course, it had to be diverted to stars, and thinking that somehow what chemists do is different than what astronomers do, even though it's literally sometimes the same instruments that we're using. So that makes no sense. Yeah,
astronomers
and then
don't do anything; they just look.
Well, I don't know
That's
what the
all
argument
they
is
do.
about the moon.
Tell me, how do you know
I don't
that
know what
the
the
sun?
argument is. Hold on, Chike. We started at the same time. I don't know what the argument is about the moon being in Earth's atmosphere. I mean, I'm looking at a whole bunch of shit from NASA, from space.com, European Space Agency. They're all saying the moon is in Earth's atmosphere. What's the problem
Oh,
with that?
come on,
Why'd you
tell me.
say we're making that shit up? I'm wondering why Jay said, this is not for you, Chike. I'm wondering why Jay said we're making that shit up when I'm just reading it right now off of all of
No,
these mainstream
I didn't
websites.
say.
For
No, I didn't
hold
say
Jace.
you
on,
For
make.
Chike.
Jace.
Hold on,
It's for
Chike.
Jace.
Yeah, I didn't say you were making it up, right? I said we were talking about that before, and right, making the specificity. I have the paper that all those other articles are referencing, where they measured the moon, the hydrogen around the moon, right, and the number that they got was 70 hydrogen atoms per cubic centimeter, right? And I said what I said before is you're fine if you want to say that that's the moon being in the Earth's atmosphere, but like when we think of the atmosphere here at the ground level, the number of molecules, of gas molecules of the atmosphere are multiples of 6.022 times 10 to the 23rd, right? That's the amount of gas molecules that we consider an atmosphere here at the ground. So saying that and that's per cubic centimeter as well. So saying that 70 hydrogen atoms per cubic centimeter is some grand atmosphere that the moon is in is an extreme stretch to me.
Wait, what I
Did
want to
anyone
know
else
is
use the
how
word?
the.
Hold on, can I respond to that,
Jeremy,
please? Like,
no, don't hold on. Now, I start talking. It's a simple question. How do you know those atoms came from us? They come from the sun. How do you know those that they count came from us?
okay, in
You followed
response,
an atom. You followed an atom from Earth to the moon to see that it came from here.
It's in the air
okay,
bars. Check your
in
No,
response
how
to
do you know?
Jace.
You have sun, wind. Yes, you have solar wind. It's made of electrons, hydrogen, maybe a bit
Solar winds.
helium.
Solar winds aren't
Yeah,
made of atoms.
yeah.
Yeah,
The
it
solar
is.
wind is not made of atoms.
Well,
No, nuclei.
Yeah,
They
yeah.
can
yeah,
So it's
merge
not.
and
together
it
later.
does. There's some even like water molecules in solar wind. So it's not like high concentrations, but technically there are atoms and molecules in the solar wind. But the major constituent is particles like electrons and
Yeah.
protons or hydrogen nuclei,
It's
helium nuclei, etc.
it's fluff in the breeze atoms from the solar winds.
Okay, I don't know if I see use the word grand or I didn't use the word grand. I don't know if you're just posturing or what you're doing, but we're not the ones that made this shit up about the moon being in Earth's atmosphere.
No,
We're just
it's not. You didn't
telling
make
you
it
what
up.
the
No,
mainstream.
you
Yeah,
didn't
we're
make it
just
up.
telling you what you. What's up?
Someone
Yeah,
in the
never
main,
said that you did.
someone
Yeah,
in the
but you.
mainstream picked up on the fact that the moon is inside the geocorona, which is the very outmost part of the exosphere. And the exosphere is the thinnest part of the Earth's atmosphere.
All right, but please try not to interrupt though. The
Okay, fair
point
enough.
is we didn't make this up, and nobody used the
Oh,
word brand. Hold on, man. Yo, were you done? I thought you were done. Go ahead.
sorry. My apologies. Come on, carry on. Sorry, I'll be more courteous.
Thank you. Well, we try. I mean, there is interruptions. I know it gets a lot. We didn't make the shit up. No one used the word brand. Right? We're just saying it's in Earth's atmosphere. That's what your guys are saying. We don't. I don't even fucking believe that shit. But that's what you guys are saying. So
I'd say it's an hypothesis at best.
What
You're
it's
what
not a
welcome.
happened?
hypothesis. That's not a That's not a real hypothesis.
Is
I
it?
just told you
Hypothesis. It's not a theory. A hypothesis.
it's an
It's a
untestable hypothesis.
measurement. It's a measurement. There's
So not a
researchers that
hypothesis.
published. They they published a scientific paper in a journal that was reviewed by their peers, right, where they detailed the method for how they took the measurement using spectroscopic methods of the Lyman alpha line of hydrogen, using spectroscopy, right? And they detailed the number that they measured for how many hydrogen atoms are in the geocorona, as the other gentleman reference. That's what they call it as well in the paper, at the distance at which the moon is at.
No offense, but how do you measure something that's that far away with everything in between you?
Is they used a specific emission line of hydrogen called the Lyman alpha, one of the lines of the Lyman alpha series. And there's a relationship called Beer's law that relates the intensity of that line to the concentration, or in this case, the number density of the hydrogen atoms present.
How do you confirm that it's accurate from 250,000 miles away?
What do you mean? The line shows up at the hydrogen Lyman alpha line. It's at the same nanometer number.
Yeah, what's their base? Like, what did they confirm that their base was correct? And then when they extended the
Hydrogen.
distance. Yep. Where? In a lab?
Yeah, you take hydrogen in the lab, you come up with the Lyman series, the Balmer series, there's another few series, right? And so they did the spectroscopy on the moon, and they looked at the lines that they got. And if you have a line that's 254.4445 nanometers, and then you do it on the moon and you get 254.4445 nanometers, well, the elements, they don't have, two elements don't emit the same lines, so it can only be one thing.
It can only be one thing.
Not even the same element emits the same
There you
light.
go.
The electron, when it moves from high energy state to lower, it emits the photon. Now depend if you go from 6 to 3, or 4 to 2, or 2 to 1.
If you're really
the
interested,
intensity of the photon is different. The energy that the photon has, and
Yeah,
this is in this spectrometer, looks like a different color, like a different line.
okay,
And
so
you don't.
if you're really, I'll just say this because it's pertinent to what you were saying. If you're really interested in evaluating what they did when they did Lyman alpha mapping, and there's a link to the actual paper that started this whole media thing off. This is them looking at the hydrogen geocorona and its extension beyond the moon's orbit.
Is
Now,
only can be one thing sound like science to you? Just be honest.
if you want to evaluate what they've done in this paper, this
No,
peer-reviewed paper,
that's not what I asked.
what did you ask me?
I'm asking you.
Spectroscopy is science. The principles behind it is
Hello.
science. It's
I
been
was talking to that
verified
guy.
over and over
Hello.
again. It's
I know
been
y'all are
verified
excited about all this
over
because
and
it
over
proves you're
again
doing
that the
correct, which
elements
makes you
don't
seem
have
smart.
repeating
Is
lines.
my mic not open?
No, you talk over
Yeah,
him. Wait.
you're talking about a quote that I said. Why are you talking to him about it? I'm right here. Talk to me about it.
Yeah, but he was the one talking. I responded to him, dude. If you don't mind, and when you heard me speaking and you started speaking over me, what difference does it make? So I guess my
No,
mic was open, so I'll ask again. I'll ask the other guy about what you said. Does that sound like science to you? It can only be one thing.
Yeah, it sounds like science to me because it's captured from the Eastern NASA mission SOHO.
Now I know not to talk to you. Thank you.
hang on. I wasn't even referring to this moon thing when I said that. I was referring to spectroscopy. The reason why I said it can only be one thing is because for over what, 300 years now, every single time we've done spectroscopy, it has verified that the elements don't repeat. There aren't two elements that have the same lines. That's been verified over and over and over again. I've verified that thousands, if not hundreds of times. And also in the radio band, in the IR band, in the UV vis band, and in the X-ray and gamma bands, right? So that's why I said it can only be one thing, because nothing has ever shown us that it can be anything else, right? So until someone can show us that it can be something else, we have to go with what we can verify.
Gotcha. So science does prove things.
It gives evidences.
No. It can only be one thing. It's proven.
No, I
That's
didn't
not
say
what I
that.
would
For
define.
300 years, it's been over and over. He's done it thousands of times. Come up
I
with nothing else. It can only be one thing. That sounds like fucking proof to me.
Yeah, I actually agree with you in terms
Thank
of
you.
in the way
Science
you're
does prove.
using proof, right, that of evidence beyond reasonable doubt. Science does indeed do that.
Okay. So beyond a reasonable doubt now, which you would say is proof in the science term, not in the court term.
No, that
In the
is like a
cotton,
court
it's a cotton.
usage.
We're not going to court about this
We
scientific
can
method. We're talking about
go. And court will rule in our favor.
now Chaiki's going to chime in. I'm sure he's done thousands of this test too.
Well, let me
The-
clarify. Let me clarify, right? So when you say proof, I actually, get a little annoyed with the Globers who disagree with you as well, because it's like clear what usage of the word proof you're using. You're not using the formal logical or the formal mathematical usage of the word proof, where you're making theorems, right? Scientists don't make theorems. They may utilize them occasionally, but they're not making theorems. That's not what we're doing. We're not making axioms and forming statements where one is from the other and the previous statement is true, so the next statement is true, and you get a whole structure like that. That's not what we're doing. We're not doing the formal kind of proof in that way. But in terms of how a court would use it, where it's evidence beyond reasonable doubt, science is indeed doing that.
JH, you might be interested in a debate that's taking place, I think, tomorrow. I was just informed of this morning, that two people on the FE side are going to be debating science and whether or not science proves things.
Cool. Who's debating?
It is Jeranism versus Nathan Oakley, from what I understand.
Which one's supporting science?
If they were to have an actual debate, like I sure that would be cool. I love that. But I
Do you think it should just be
Nathan's past is a lot of screaming and calling names.
It's allegedly
no,
supposed to be on some
it
sort of
changed the
neutral
format.
platform with a neutral moderator. Whether there'll be legitimate muting taking place or if it turns into a complete shit show is still yet to be seen. But the topic, like I said, is going to be science, whether or not science proves things or not. So it's funny. It seems like regardless of what side you're on the macro debate of this topic, it seems to be nobody's in 100% consensus when it comes to something like whether or not science does or does not prove things. Which camp would you say you fall into, Jay?
You heard what the man said. Depends how you use the word
Oh, just
proof.
getting him to reiterate, Chikey. Jesus Christ, did I say Chikey? Let me hear your opinion about Jace.
I said, as he said, it depends on how you use the word proof.
Yep.
Yeah.
My observations, right? Whenever Globers have this argument, right, the context in which the other side is using the word proof is always in the context of evidence beyond reasonable doubt, which is similar to the court usage of it, right? I've never heard the other side saying like, okay, we're doing a formal proof where you're making a theorem and you have axioms and derived statements where it's following the structure where the truth is implied from the previous and that kind of thing. So it does annoy me as well when Globers get like all defensive about science proving things, because in the colloquial courtroom usage of the word proof of evidence beyond reasonable doubt or any kind of variation you want to put on that, I do agree with you that science does indeed do that.
My to add on to that though, when I say that science does not prove things, I always keep in mind that scientific revolution can happen. Because if you were to ask someone in 1850, is gravity a force? Then you would get that kind of response of, yes, it is a force that has been proven beyond beyond reasonable doubt. I've done the experiment thousands and thousands of times. And then relativity came along. So I get your point, but I don't think I would put it quite that forcefully. Because, I mean, yes, the idea that we look at the hydrogen that extends beyond the moon. I mean, yes, everything that we know right now tells us that, yes, that is in fact hydrogen based on the spectroscopic analysis. But I mean, if we want to be honest, we have to admit that there is a minute possibility or a small possibility that what we believe is happening could in fact be something else. But on the opposite side of this, the flat Earth side has to recognize that unless they can come up with something better, then this is what we have.
That's not always the case, right? Falsification is not necessarily require replacement, right? You can falsify something without replacing it with something else. So I don't necessarily agree with that, but I understand where your sentiment's going there. But I do find it interesting that many times when in these spheres that we congregate in, these conversations that we have, many times the only time the phrase science doesn't prove anything comes up is usually when somebody's backed into a corner and they use that as kind of an out, right? Kind of a get out of jail free card. Well, science doesn't really prove anything to begin with. That happens a lot. But then I also see that there seems to be a large conglomerate of solipsists within these spheres as well that are fighting for one particular side. And it seems as though this whole, well, we can only know so much, we can never have any absolute, seems to be more of a tenet of solipsism that kind of blurs the lines between whether it would be a tenet of scientism as well.
Well, I guess I should have clarified. I totally agree with Professor Parks there, and you, Napalm. But when I say evidence beyond reasonable doubt, like in the courtroom usage, that's not excluding that science is also provisional, right? It doesn't mean that the evidence beyond reasonable doubt is like an absolute truth, the absolute proof of the absolute truth, right? You still can have new evidence, provisional new evidence that changes your mind, and you should change your mind when that happens. So just to clarify that.
Yeah, I figured that was what your point was. Although I do have to add, why I jumped in was, did I hear correctly that Jeranism and Nathan Oakley are going to be debating whether or not science proves things?
That is what I heard this morning. Yep.
Wow.
And I made it very clear. I was like, well, if this is going to take place, first of all, they need to establish some sort of agreed upon definition of science and proof. Those two things need to definitely have agreed upon terms. Otherwise, they're just going to be arguing past each other the whole entire time.
Okay.
Yeah.
And kind of like what we're doing now, right? Like we're fleshing out, what does proof mean? How is it related to what we would call science, right? Like that all needs to kind of be established first. What is science and what is proof? So then you can then apply that proof to what everybody has agreed upon is science.
I think the category distinction is that proofs effectively are only a construct in mathematics and logic, essentially, and they have a finality and a two-state, or like a binary aspect to them. They're either true or they're not true. When the term is used in science, I think you're kind of aligning it more to the idea of a theorem, which is the best explanation possible at any given time, with all the available evidence, which is constructive in the evaluation of the original premise.
Do you guess who supports who says science proof things?
Yeah, I was wondering that myself. Who's on which side?
Well,
It
Nathan.
seems as though Nathan Oakley would be the one that would say that science proves things, and Jeranism would be the one that says that science doesn't necessarily prove things. That's what I've understood.
I think the problem is that people say, "Oh, I've done a scientific experiment and it proves it proves a hypothesis or something." It corroborates it, and that's a sense in which it has a corroborative aspect to it when it's used as to align itself to other truths or other understandings that we have around us. But it's not a proof in the sense that it's a logical mathematical construct.
Yeah, I mean, you can have a hypothesis that isn't clear enough that you could quote unquote prove, that isn't necessarily the end of the story, right? Like if I see water boiling and I want to form a hypothesis and I want to say heat is the cause of water boiling, right? That's kind of a very general statement. It doesn't have a lot of specifics. And I could do an experiment where I apply heat to water and it boils. So does the application of heat to water cause water to boil? Sure. But can other things cause water to boil? Yes, like pressure, right? Is the application of heat relative to certain parameters? Of course, right? So it's like there can be a blanket generalization statement that could be on its face not necessarily incorrect, but certainly not very specific.
Yeah, and if I tend to think that if someone is evaluating a situation honestly and with integrity, they would state that my experiment proves that heat is a mechanism for making water boil, rather than making the assertion the only way to make water boil is to heat it, because you haven't demonstrated that, you haven't evaluated all the other possibilities that could cause water to boil. All the other phenomena that could cause it all. So I don't think this is the trouble. I don't think in most senses in science people would observe an interaction which would cause a consequence and go, this is the only interaction that can cause that consequence. I don't think that happens very often. It wouldn't be a step these people would take.
You might say that, but I could say, balls appearing to attract towards one another in a shed via my telescope. I could make an assertion there, and there could be other parameters that are taking place, right? I'm just saying.
I actually saw a guy do Cavendish earlier on YouTube. It was pretty good. He was like a high school teacher or something.
Well, then if you think there are other parameters, then devise the experiment to show these parameters.
Yeah, that's my issue with it too. All the parameters I've ever heard for alternative explanations for the Cavendish, right? And Nate Baum, you heard me say this earlier, they're like electromagnetic or electrostatics, and all that we can show that those effects are all like on an entirely 10 to the 26 power magnitude different scale than gravity is. And so the outcome of the experiment, if they were due to that, to those effects, would be significantly different according to.
Yeah, I think that's key with gravity. The only things we can evaluate to show as being emergent properties in its influence are mass and distance. Nothing else has been demonstrated. That's not to say they're the only properties of what we call that attractive mechanism, but in the sense in which we try and work out these variables, those are the only two that are hold fast across all evaluations.
Basically, just saying
I
that.
mean, I don't necessarily want to go into having the debate about the Cavendish that we've all had about a bajillion times, but I do want to say that, you know, if your explanation in that is gravity is the effect that we see. It's not necessarily the cause. We still need to determine that. I would hope that most people would be at least open and honest enough to say that gravity is the effect that we are experiencing, or what we're calling gravity is the effect. But maybe you guys disagree,
So-
but I
think
don't
that's the
necessarily.
case.
But science is not a why thing. Science is a how thing, and the Cavendish shows how quite clearly.
Well, other Globers can correct me if you think I'm wrong, but to me, in this instance, right, what's being claimed as the cause is the mass, right? There's a coupling of the mass to the background space or whatever, right? And what you manipulate, you can manipulate the mass. There's a relationship of that coupling of the mass to the strength of the effect, right? And so by manipulating the mass and having the effect change exactly as you predict, provides good evidence that your cause is at least on the right track.
There you go. So what's your problem with Cavendish?
Yeah, I would say that what you guys would call mass, if you can properly define that, does have something to do with the effect that we're seeing, but I don't know if that's the full stop there. And no offense, but I don't really have any desire to have a conversation with you in after show.
Of course not, because you realize that what you're saying is exactly what I'm saying. You admit that Cavendish is a decent experiment. Okay, so what's your problem now?
Why do you immediately after I say don't want to engage with you throw out some sort of straw man and put words in my mouth? This
Not
is
straw
exactly
man.
why I don't want to engage with you.
Not straw man. You just say that the Cavendish, you can't come up with any other parameters, and then you say but, and I don't understand. But if you think there's other parameters to the Cavendish experiment, devise the experiment and show it.
I'm confused as to why he thinks mass hasn't been properly defined. Like, there's a very specific definition of mass, especially in like particle, atomic, and nuclear physics.
Yeah.
Like, it's definitely been defined. I've provided that definition many times.
Mass is a
Sure.
base.
Can you just lay it out? Can you just lay it out real quick? So when we would you agree with the statement that within Cavendish it would be evidence for mass attracting mass? Chase?
No, I wouldn't. Right. There's nuance here. I wouldn't say that.
That's what I wanted to flesh out is the nuance, right? Like that's kind of
Yeah.
my whole point, right?
The mass couples to what we call space-time, but you can just think of it as the background space or the XYZ coordinate system, right? And that has an effect on the other mass, right? And the resultant of that effect is that the two masses move towards each other. So it's not directly that the mass is attracting mass.
So that's the more specific alleged cause of what we see within the Cavendish experiment, if we want to go down that road, right? There is more to it than just math A, math B, therefore attraction. There is something else taking place, and there is a claim on the table that causal mechanism is what you have called space-time, and you have said that there is a whatever you want to call it, a bending, a warping, a depression, or whatever in space-time that causes the effect that we see. Is the math the cause of the bending and warping of space-time, or space-time the cause of the attractive thing that we seem to experience there, right? But then you also need to have some real good established scientific evidence for this thing that you call space-time right? If it is such a thing, or if it's just a way that we're trying to describe something, but it has no actual physicality in and of itself, but is affecting things with physicality, but has none in and of itself.
Why do you need to talk so much? We know that we need mass in this experiment. That's what we know for sure. Without mass, we can't measure anything. Nothing will happen. How it affects it, space time, no space, and that's a different issue. There must be a
I
mass,
get what you're saying.
two masses that affect each other. That's what we know for sure.
What? Well,
We,
yeah, you can't do anything without mass. Can you give me a scenario where mass isn't involved?
now we
Okay,
don't
so
know.
you just
We
said
still don't
absolutely
know.
nothing.
We still don't know that it happened with every mass. For example, we don't know if if a single particle how it will behave in a gravity field. We have no idea. They're supposed to do a experiment which the name was Alpha G, which they drop antimatter from they put antimatter in some height and drop it and let it fall. And they want to see will it fall down to the ground or up.
I believe that's been done, Chike.
I know they build the device. I don't know if they ran it.
Yeah, I know. I know they have the traps and stuff at like CERN to store the antimatter and whatnot. Even some cyclotrons and synchrotrons have the ability to do that. But you know, the best technology of it is at CERN. And I know they were planning on doing that kind of experiment with the antimatter, dropping it, seeing if it reacts gravitationally the same way that normal matter does now. I believe they've done that already, but you know, not positive.
Okay, if you guys are done with this, I'd like to ask the professor, since he's here, a question. Professor Parks.
Yeah, go ahead, Essie. I'm done.
Yeah, I'm here and not here. I'm actually kind of splitting my attention from this conversation and work emails. But yeah, go ahead. What's the question? Is this about the turkey?
No. Forget that stuff. You're more your knowledge is greater than the turkey thing. But that is a doozy. We can discuss that another time if you like, Professor.
Okay.
I was actually more thinking of the baby galaxies that we discussed a while back. I was wondering if you had a chance to look at that, and also I'd like to know if you had a chance to look at the 5 sigma observation certainty that dark matter does not exist. I was wondering if you had a chance to look at those things.
Sadly, no. My semester is starting, and so my focus has been on getting that, getting my coursework under control. With in terms of the baby galaxies, I have to say that at this point, yeah, that is something of a. I would hate to. I don't want to use the word crisis, but it certainly is a stumbling block, or it is a. What's the word? How do I want to phrase this? It is a problem. It is a problem that we currently do not have an answer to. So I think the implications of that are that I don't believe that it is a test of Big Bang cosmology, but I do believe that it is a test of dark matter, of whether or not we understand how dark matter is affecting the expansion of the universe at such an early stage. But as for the 5 sigma result that that dark matter doesn't exist, wait a minute, are you talking about the age of the universe thing with the tired light?
No, he's talking
No,
about
no.
Pavel Krupa's claims.
I don't think I'm aware of those.
I'll post you a thing. I'll post you.
Okay. Like, yeah, I am not familiar with. Is this having something to do with Mond?
Yes.
Yeah, he's one of the developers of a version of Mond.
Oh, okay.
So
Yeah,
like
and
it's expected that he's gonna champion his, his hypothesis. Like,
Real quick, Professor Parks, can I ask what school you teach at and what you got a PhD, right? Just real quick, I don't want to interrupt this whole thing.
Yeah, I do. In astronomy, Georgia State University. Go Panthers.
No doubt. There we go. All right, thanks.
No problem.
so, Professor, I just dropped you a video on him.
Okay.
So
It's text one.
I'd like to get Professor Park's opinion too on something, or his thoughts on something. Right. So there's another astrophysicist who comes here. He's a postdoc. So he has his PhD. He's doing a postdoc right now. He calls himself Chronic on here. I don't want to give out his real name.
I've actually met him in real life.
Yeah. So about the baby galaxy thing, right? What I've talked to him about this. And what he told me is that the redshift, right, there's like two halves of the redshift thing, of the Z, of getting the Z value, right? There's the pictures, like the images from the telescope, and then there's the spectroscopy as well. And what he told me is that the redshift values that indicate that the galaxies are too big or too massive and too old or whatever, or too young to be that massive or whatever, is only from the images from the telescope. And that when that group or other groups did the spectroscopy on those galaxies or whatever, they got the other half of the story basically, and the redshift value changed to one that's within the acceptable limits. And there's also something called like the initial mass or something, that is like an assumption that's based on our own Milky Way galaxy that also has to be like factored in, and that's what he told me.
Yeah. So the issue there is, so when I was first saw this problem, that was definitely true in terms of the photometric versus spectroscopic analysis. That the spectroscopic analysis hadn't really been completed yet, and so the results were tentative. But from my understanding, there have been a couple of papers that have actually supported the fact that these galaxies are too massive. Well, too massive
Correct.
for current modeling with spectroscopy. So I don't know. Maybe there has been something more recent that has shown that those first spectroscopic analyses were inaccurate or incomplete in some way. But yes, to your other point, there is something called an initial mass function, which is something that we have set up from previous observations. Essentially, what it means is if you have a cloud of hydrogen helium gas with some particulates, and you allow that thing to collapse down, it's going to create a certain population of stars. So typically, we believe that, say, for every every star that is 40 times the mass of the sun, you're going to get 100 stars that are half the mass of the sun. But this is, that is potentially one of the, I wouldn't call it solutions, but it's certainly something we need to look at, because we are making the assumption that the initial mass function we see now is the same as is the same function that would be present at the very early stages of the universe. And I have serious reservations about that, because the metallicity is completely different in the early universe, and that is going to, I believe, play a significant effect on formation rates. And probably it definitely plays a factor in formation rates, but I would suspect that it also has a impact on the initial mass function as well.
The metallicity was, in fact, mentioned as one of the reasons. The problem is, Professor, that especially with these supermassive black holes, right? The problem is that there wasn't enough. There wasn't enough stuff, shall we say, in that early time frame in order for them to feed to become massive, and especially the quasars as well. There's just not enough time in the cosmological time frame that the Big Bang Theory suggests for these things to happen. So that's a big problem.
Yeah, I understand. That's really the crux of the issue, is that there just isn't enough that our current understanding of general relativity states that there is a certain time frame over which dark matter is going to bring that baryonic matter together to create these larger structures. And that time is longer than what we're actually seeing in the past. So, yes, again, unless there are some observations that have shown that the spectroscopic analysis is inaccurate, this is a significant problem that cosmologists need to solve. We do have these problems in cosmology. One of the ones that I'm most interested in is the I can't remember what they call it, but essentially there is a difference in the age of the universe as determined through Hubble flow, excuse me, Hubble flow and CMB analysis. Like the ages are significantly are different, and if you look at the errors, they are statistically significantly different. And so there is
I believe, Professor, 400 million years difference, if I'm not mistaken. Yeah.
Yeah, one is like 67 kilometers per, I think, second per megaparsec, and the other is like 72, and the error bars don't overlap anymore. And they call that, at least Becky Smethurst calls it, the crisis in cosmology.
Yes. Dr. Becky.
One of them, yeah. Shall we say. I mean, there is a discrepancy. It's 400 to 500 million years. That's not a small amount of time. And that's just two measurements, yeah.
No, well, it's two measurement styles. There are
styles,
a
correct.
number of measurements on each camp that show that. But if we didn't have questions, then I wouldn't have a job. Well, astronomers wouldn't have a job. So I welcome.
No, agreed, and I appreciate your honesty. I mean, it's refreshing to hear that. Yeah.
Yeah, and I will be looking into the early universe stuff. Like I said, I just haven't had the chance to because my semester is starting next week, and I've just been kind of swamped with getting my courses prepped and all that kind of good stuff. So.
Yeah, have a look at the 5 Sigma thing. I posted a short clip, but you can see the whole video, the whole interview. It's quite interesting. Quite interesting. I think you're going to like it.
Can you put the person's name in the chat? That way I can. I will watch that video, but I'd like to look at his paper, or read his paper on the subject.
Yeah, who had a chirality? You knew it off by heart. Paul Krupa. What's his name?
I put it in the chat. His name's Pavel Krupa.
Pavel Krupa. Yeah, there it is. Thanks.
Okay, cool. Pavel Krupa.
How long is on this mount?
What?
Yeah, I didn't quite catch that.
The guy that talked about modified Newtonian.
How long is the video you're asking?
No, I'm asking, is that the guy that support mounts? Yeah. So
yeah, that's the guy. Yeah.
How long is on this thing? Is it 5 Sigma?
The whole video is like 20 minutes. The whole interview.
No, the guy.
You mean
how long he's working on it?
I don't know.
He's been doing it since the 90s, Chuck. He's got papers since about 95 of
Nice.
Not necessarily MOND, but on the dark matter problem, and then in the 2000s to 2010s is where he really did his work on developing versions of MOND.
And he made any predictions that we can test? He did tests? or just
Yeah,
analyze other data?
from what I understand about Mond, right, and a lot of this is coming from, my own understanding mixed with things that like Sabine Hossenfelder and Sean Carroll have said, which is that Mond does a great job of explaining certain observations, and that particle dark matter does a great job at explaining other observations that Mond doesn't explain. And Mond explains some observations that particle dark matter doesn't explain. So the most parsimonious thing is not mixing the two, which is what Sabine is a proponent of, that the data just indicates that some observations require Mond and some require particle dark matter, and it's not parsimonious, but it's what the data indicates, and so that's what we should go with. And some people say that no, it's not parsimonious, we have to do more study, more research to figure out which one is correct, or if they're both wrong and it's something different that's correct, or if general relativity is correct all along, more research is needed, that kind of thing.
Let me tell the professor this before I forget. You're going to like this, Professor. There's a new theory out there from a professor in the college at the University of Ottawa. Now, he proposes to solve the baby galaxy paradox, amongst other things. He doubled the age of the universe. Let me say it again. He doubled the age of the universe. I don't know if you heard about that one. Now, he incorporates the entire light that you said in there with all kinds of other stuff. Yeah.
From my understanding, I've read his paper, but I have to say that the mathematics are a little bit beyond me at this point. But I've been told from others who I trust that the mathematics works. I mean, if his base assumptions are correct, then yeah, that would be valid. But the base assumption is that is the tired light theory, which unfortunately has never been observed anywhere in the universe. So,
exactly. Yeah.
So, all right. It's interesting.
So you heard of this? Okay. Yeah.
Yeah. I heard of that one. That one got a lot of traction recently.
So you're saying because of the tired light, you're like, you're kind of skeptical on that one.
I would say
You're saying doubling the age of the universe is getting a lot of traction. That one.
Well, when I say a lot of traction, what I mean is a lot of traction in the news. A lot of people. So it was a single person it's a single author paper. He put it out there, and then somehow, for whatever reason, somebody latched onto it, and the news has just been kind of explode. The science news has been kind of exploding with this idea.
Is there any other way to fix the problem other than what this guy suggested?
I'm not aware of one, but I'm also not a cosmologist, so I'm not aware of what the current, like the most recent modeling is doing. It is a solution, as I said. It is a solution, and from my understanding, the math works. It's just that his base assumption on what light is and does has never been observed anywhere else in the universe. So, I mean, that's kind of the problem with a lot of cosmology, is that in a lot of cases the math works, but the physical underpinnings just have not been verified. Like Mond, for example. Mond, as Jace was saying, in certain cases, Mond, works very well at predicting what the universe is going to do, whereas in other cases it doesn't. Dark matter is a much better explanation for it. So.
Yeah, but they're about to get rid of cold dark matter anyways. But I get that from Chronic a lot. He's not a cosmologist. They deal with the really far out stuff, and just Chronic's in your field, or you guys deal with more local things.
Yeah, from my understanding, research is on relic neutrinos, basically neutrinos that were initially created from the Big Bang. But I don't know what he's doing now, like what his active research is now.
Also, let me just say, as far as things, happening in outer space that we've never observed happening on Earth, is that what you were talking about with the whole light thing?
With tired light, we not only haven't observed it on Earth, we've never observed it anywhere else in the universe. So, if you adopt the tired light theory, then what that basically is indicating is that, GR would certainly have some problems, but the Big Bang cosmology would be wrong. People invoke tired light to kind of go back to the idea that we live in a steady state universe where we did not come from a singularity and the universe has essentially been infinite for all of time. So it would, if more evidence for tired light does come to light, pun intended, then that would radically change our conception of things.
All right, let me throw you an easy pitch here. Well, I don't want to change topic. I see, were you in the middle of this?
No, it's good. I think the professor said he's going to look into the 5 sigma, and I'm waiting to hear his thoughts on that in the future.
Yeah.
Real quick, have you heard of the blue shift? They thought there was a star coming at us, and it was blue shifting, and that's why they thought it was coming at us, because it was blue shifting.
Mm-hmm.
And it was actually because it had a strong magnetic field. You hear about that one?
I have not heard that one. I'm not certain how a strong magnetic field would, what's the word I'm looking for, resemble a blue shift. A magnetic field is primarily going to cause a splitting of the lines. So, I mean, yes, part of the line will get blue shifted, but part of the line will also get red shifted. So, in order to mimic a blue shifted effect, you would have to actually be missing the other half of the Zeeman line. So,
What does that mean as far as the magnet? It'd have to be a monopole. Like, what are you saying?
I think Jace would probably have a better.
Yeah, I got you.
Yeah, you probably got this one because I'm talking about Zeeman splitting.
Yeah. So, Jeremy, magnetic fields, what Professor Parks is saying, if it was just a blue shift, right, there would only be just one line, like as if there was no magnetic field there at all. But when you have a magnetic field, that one line gets split into two. And say the original line with no magnetic field is at 270 nanometers. When you apply the magnetic field, the line gets split into two lines, and neither will be at 270. They won't be at the original place where the original line was. One will be red shifted, so it'll be at a higher wavelength. It'll be at like 275, let's say, and the other will be blue shifted, where it'll be at a lower wavelength, like 265. So that's what he's saying.
That's good to know. Yeah, it's good to know. That was important. So I mean, Witset's been dropped the paper a couple times. They thought there was a star was going to enter our solar system because of the way it was blue shifting. But it turns out that they got it wrong, and I guess they attributed it to a magnetic field. I guess maybe they were wrong. I don't know.
Let
me see if I can dig it up.
Like what he's saying is it's hard to, like, how would you mistake that a blue shift would just be one line shifted to a lower wavelength compared to the original line, whereas a magnetic field would have two distinct lines. So how do you mistake one line for two?
I don't know. Maybe this is the conundrum you run into when you start making up stories on how the sky works. I don't know what they're doing. I don't know.
I think it's probably just a misunderstanding or misinterpretation of what happened.
So let's see. Why are you posting Machu Keiko again?
What I do?
Michu.
Michu. I have this problem. Is Michu Kaku?
My buddy Michikaku, one of my favorite dudes.
Yeah. Well, why? Why'd you? I mean, this is basic stuff. Yeah, telescopes look back in time.
I'm glad you brought that up because I've I've had a question about this, right?
Okay.
So this question, especially to the ballers, this one. So we have a telescope that's a time machine, right? We look back in time, right? That's the claim.
In a manner of speaking.
Yeah. So it's like rolling back a film, right?
You know, like when you have like a radio, you don't hear them instantaneously, right? You hear a delay. Like, when I'm talking to you, there's a delay. Sometimes you'll hear an echo where it comes back and forth. It's a lot of that is it takes that long for the signal to get to you and then come back to me.
Right. I get that, but if it's like a film, right? Like the way they say, like a time machine, like shouldn't we see like parts? Like shouldn't be able to rewind, like put the telescope there and see this time frame, and then a little bit back and see that time frame, and then a little bit more back. Shouldn't it be like that?
No.
No. So it's directly back to billions of years.
Well, it
So the
depends.
tape goes from today to 13 billion years back.
If you
Boom.
look at something that's 1,000 light years away, it's 1,000 years old. You look at something that's 200 light years away, it's 200 light years. You look at something that's the other side of the universe, yeah, it's 13.8 billion or whatever.
Yeah, but how about all the other intervals in between that?
Yeah.
What happened to them?
Well, they're all there. I mean, the stars are different. The galaxies are different positions. Each one's a different time. Yeah.
Has anybody ever thought of that? But because it doesn't make how. Well, if they're all there, why don't we see them? I mean, it's a legitimate question. If it's a film and we're rolling it back, right, we should be able to dial the telescope to, I don't know, 1 hour after the film, 2 hours. Oh, let's go back to half an hour. I missed what's his name said.
It doesn't work like that.
I know.
It's like saying, hey, the TV show that, before there were VCRs, we don't have a VCR. It's like you're receiving the TV live over the air. And if you miss it, you miss it. You can't go back.
Well,
it's just a function. It's just a function, I see, of the, in order for us to see something either with our eyes or with a telescope, light has to either be emitted from it or reflected off of it, right? And that light takes some time to travel. So if a photon, leaves an object 100 light years ago, right, that means you're seeing that object as it was 100 years ago, or whatever.
Okay, and in between then and now?
Or not 100
what
years.
happened?
It'd be much more than 100 light years.
Yeah.
Not 100 years.
In between then and now, the light was traveling to get to us. It took it that long to come to us.
So it was a fixed time frame from the movie coming at you?
Yeah,
You singled out a fixed time frame.
The object still was existing and doing things over the time that photon was traveling. It's just that's how we're going, we see things through those photons, be it with our eyes or with a detector. So whatever information the photon has is how you're going to see it. But yeah, the galaxy or star or whatever it is was still existing and doing things within that time.
I'll give you a better analogy
think...
to comprehend. Go ahead,
Enigma. No, go ahead.
I was just going to give a better analogy to conceptualize it instead of trying to use something like a photon or whatever. I'll go to a sound analogy, which is probably a little bit more analogous than these photon claims. But if you have somebody that's standing 2 miles away, and you have somebody that's standing a mile away, and you have somebody that's standing a half a mile away, if they all scream at the same time, you're not necessarily going to receive that sound to your ear at the same time from each one of those people that would be screaming, because when you're utilizing your voice box, you set up that agitation within the air, and that energetic pulse within the air translates across an area, and it takes a specified amount of time, right? So each person's distance is going to be relative to the amount of time that it would take for that sound to hit you. It's also going to have something to do with the intensity of that sound by the time it gets to you, right? Meaning it's going to dissipate or slowly get degraded over that time frame. And the same could be said if you're sending a sound pulse towards a wall, and then it reflects back from that wall to you, right? So you receive the echo of that sound. All of these could be analogous to light, meaning you're not necessarily receiving the sound from the furthest guy at the same time you received it from the first guy. So you're going to have a delay. So
Yeah, you're
effectively,
basically
they all screamed at the same time, but you're getting it at 3 different times to you. Same with the reflection. That's kind of what they're trying to say, but with light.
yeah, you're basically hearing something in the past. Like the guy says something and then you hear it later. So he already said that in the past and then you hear it. It works exactly that way with hearing, unless you think light is instant. If you think light is an instant thing, then you're not seeing in the past. But if you think light has a speed to it or a propagation rate or whatever the fuck, then you're seeing in the past, essentially, just like you're hearing in the past, like Napalm just explained.
Oh, I get that part. I don't think you guys are getting what I'm saying. You have the song, right? You have an album, right? Led Zeppelin, right? Now you have a sequence of songs in that album, right? Now, what they're saying is, right now we're at the end song, right? But you can go back and listen to the first song, right?
Well, things that are farther away. So if you had, oh, go ahead, my bad.
Yeah. You can listen to the first song, but the songs in between, they're not there. What I'm asking is, where are the songs in between? If you're claiming it's a movie or a record, why can't you dial into the songs in between? You're only viewing that cluster, that whatever, at that time frame. I don't know if
I
I'm
know,
making
but
sense.
The other
But
songs
listen,
farther
listen.
away.
Let me real quick. Hold on, real quick. Let's pretend we got Led Zeppelin albums playing, and there's one 100 meters away. There's one a mile away. There's one 5 miles, 10 miles, 1,000 miles. And let's pretend they're loud enough so we could hear them. We could hear them all, and they all start playing at the same time.
One album here.
What's up?
One album. We got one album
What's
going,
one album?
representing that galaxy that they say is 13 billion years old. Not many albums, one album of that one galaxy. Let's start with that.
Well, they're playing the songs, and the songs are on their way. We're hearing the song we're currently hearing, and the rest of them will get here in time.
No, but you're saying you're playing the first song, and I'm saying, okay, you're saying we went back to the first song. What happened to all the other songs in between?
What do you mean? We're hearing the song that we're hearing. As it comes to us, that's the one we hear.
Yeah, but you're saying you went back in time. So in order for you to go back in time, you had to have passed all those other. You have to pass the 15th birthday of your kid, the 14th birthday. Candles were lit on the 13th, the 12th. Now you're at birth. You're at the infant. You're at the hospital with your son, right?
All right.
Now, what happened to all those other events?
You're taking this too literally. What we're
No. I'm explaining to you how it is.
No, that's not how
reality.
It is.
Yeah.
that's not how it is.
Listen to me again. We have like according to your, we're listening to, I don't know, the second cut on the album. The first cut's already gone past us. The third cut's on the way. Right now, the second cut is passing us by.
Yeah,
No.
that's more true to form.
No, it's not. You're at the
It is.
baby. You're at the hospital now. When you look at those baby galaxies, you're at the hospital.
Okay.
Well,
Yeah,
maybe not at the
when's the baby
hospital. You're
got?
at 5-month-old.
Okay, so
You're
that's
not literally transporting yourself back in time, SC. The signals from specific points in time have not reached us yet, and they will reach us at a specific time in our frame. We're
So
not
you
saying you're actually traveling back in time. You're just looking at signals that were emitted, light in this case with telescopes and galaxies, that were emitted at a certain point in time that have been traveling to get to us and now have gotten to us.
Oh, so we're not looking back. It's not the way they say it. Okay.
No, we
Right.
are looking back in time because they played that song. They took that picture 13 million years ago, and it's just now
How do you
getting
know?
to us.
That's like the nuttiest thing I've ever heard.
Why is that nutty?
You're saying what you're saying now is that you're seeing something because you zoomed in, that
No.
you're seeing something that happened 13 billion years ago.
Yes.
That's what you're saying.
Yes. Why are you having a problem with that? No,
Why
seriously,
am
why
I
are you having
having
a
a
problem
problem?
with that?
Because I think logically. I'm not in fantasy la la land like
Well,
you are.
again, we're using analogies that you
You
seem to
are, though.
understand. You seem to understand the analogies, but can't apply it. You know, we had the one that the people screaming at various different things. You hear them at different times because that happened in the past. It took time for the sound to hit your ears. It's the same thing with light. It takes time for light to travel. Now, light's really, really, really fast, but it's not instantaneous.
Look, somebody convinced you that you have a powerful enough telescope and you zoom it in, you're looking back in time. You're seeing a signal
Analogy.
that left 13 billion years ago.
Yes,
But it
because
hasn't reached there yet. But you're able to zoom in with your telescope to intercept that. You're talking fantasy, bro. Sheer
again, what's your problem
fantasy.
with it? No,
It's just the light that's coming at you. I mean, I actually agree with this seeing back in time thing. I wouldn't agree on the dates or the amount of time, but whenever you look at something, even if I look at you across the room, I'm seeing you in the past. So, but just on a side note, Blaze is doing a trivia thing down on live stream too. If anyone wants to play, thank you.
Yeah, hey, if you guys want to believe that you're looking at something that left 13 billion years ago, did not like lose its thing. If you want to believe that, bro, feel free. But
Like
don't
I
try
said,
to make me look crazy for not believing in your fantasy,
stop
because
using.
that's
I
not going
wouldn't
to work.
agree with the dates. I know I wouldn't agree with the dates either. I absolutely would not agree with the dates, but still, as far as the seeing back in time thing, you're like seeing the past, basically.
Stop using this word belief. It doesn't mean what you think it does.
So it's a
Okay,
fact.
Princess Bride.
Hey, you know,
Remember that from the Princess Bride?
it's a great quote. I mean, you guys, he keeps on using this word and been told that it's incorrect and keeps on using it.
Just think about it, bro. You've been convinced, somebody convinced you that what you're seeing is something that left a light, that left 13 billion years ago, an unimaginable amount of time, and was able to stay intact for you to see it today. I
So wait a minute.
mean,
So you have a problem
wow,
with the
man.
amount of time, or do you have the problem with the concept of time?
Everything, the whole story is nonsensical, if
Why?
you ask.
Well, all right. Well, we've tried to explain it to you as best we can, and so we'll just drop this because you obviously are not going
The
to.
light should have fell apart, NASA.
It gets tired and stops or something.
No,
Splits
no.
apart.
The logical thing is to assume that something could travel for 13 billion years. The
Why?
non-logical thing is to laugh at the person that questions it.
Why?
Gotcha.
Why can't it travel for 13 billion years? What's going to
Yes,
stop it?
exactly.
It's even it's to laugh at when you ask that question, bro.
No,
Why?
seriously. What
Why do
stops?
I think something cannot travel for 13 billion years? You think that's a logical question to ask somebody?
It is. It's a very logical. How long? What's the limit on how long light can travel before it gets tired and stops and takes a rest?
I have no clue, and neither do you. Somebody convinced you that things can travel forever.
Yeah, which means that you have no evidence that the light should stop traveling.
yet you're making claims and mocking people, and when it's you who is looking ridiculous.
No, it's the complete opposite, but you don't realize it, bro. That's the astonishing part.
I'm
You
asking
think,
you to
no,
provide
no,
the
hold on,
evidence.
it's my turn now. You
Provide the
think that
evidence.
it's illogical for me to not understand how something could travel forever. Somehow, you think that's the illogical position. It's
That's
astonishing.
because you're
I
Quebecois,
didn't
dude.
say forever.
It's not necessarily the
I
logical.
didn't say forever. And if you could provide actual evidence that light, there's some actual reason why light shouldn't be able to travel distances like that, then I'm all open to it. Go ahead, provide the evidence.
You see, you don't know how this works. You have to provide evidence that light can travel forever,
The evidence
not
is out
me.
there. The evidence is
You
out.
have the crazy notion, not I.
No, you see what
I
happens
know
here.
things.
They listen. Hold on,
We
SE. They think that they measured. Hold on. They think they measured forever. So if they got the direct measurement of forever, then that's how they know that it goes forever.
See what
Then
happens
it's
here.
just a
Here
straw man.
is there is a scientific theory that's pretty much accepted scientific theory out there that says that light can
Ooh, it's
travel through space.
accepted. Well, let's back
And
down there, SE.
stop,
It's
listen to
accepted.
me, listen to me one more time. And if you are going to come up with something that says this theory is incorrect, you have to provide some evidence against this theory. You just can't say no, because I say so, because my name's SE Montreal, and everyone says, "Ooh, your name's SE Montreal." We'll have to stop. Oh, that obviously.
It doesn't work like that, bro. The positive claim is on your side. Somebody convinced you that something can travel forever. That is a nonsensical statement. That is
No.
a non-logical statement. And I have every right to question it
But the evidence
and
is
ask you
there.
for proof.
You want
There's plenty of proof, though. We show the mechanics of how light travels. Simple spectrometers do that. We could show how these Z values are measured, the different methods, how they all converge on the same Z value. Right? All of these things can be shown to you. You just repeatedly deny them and just say, "Oh, you're illogical," but I have no evidence to show anything. I'm just going to deny all the evidence that you show me and somehow think that I'm right, which is illogical. That's not normal human behavior.
It absolutely is. It distinguishes people that have been Stockholmed and people that haven't. You just said a bunch of things of how you think something can travel forever, claiming that it's been proven. Now I ask you, how can you possibly prove that something can travel forever or 13 billion years? How can you possibly make that statement and think it's rational?
Yeah, because we can show the mechanics of how light travels with a spectrometer. We can take an AAS and AES spectrometer.
Did he stop? Did he drop?
Yeah, it
He
seems
got
so.
disconnected for
He
some
dropped
reason.
out, but he's back.
Yeah, so we use an AAS, show the Z values of the light, right? And then we're just applying that to things like the CMB. You measure the Z value of the CMB. You can't give me any good evidence for why I shouldn't believe that measurement or, take that measurement as real when I can measure it, right? So I have no reason to believe you.
Right. You can believe that the CMB, something that you think is 13.8 billion light years away, and somehow you measured that, you can believe that story. But like I said, I reserve the right not to believe. And I am in the position, you are in the position to prove. I am in the position to question that. So
Yeah,
you
yeah.
have a positive claim.
Everyone who had the old TV and saw the snow on the screen, so part of it came from the same beat.
Yeah,
That's what
What
they
do
tell
you
us.
believe? You
Yeah.
believe it's something we detect. You put an antenna and you hear the same beat. You can hear it.
Yeah, and trust me, man, you're not in the position you think you're in, and it's quite comical.
Oh, yes, I am, buddy. And I'm enjoying every minute of it. I'm enjoying somebody like you that's educated, that you do experiments and you think you got it all figured out, bro. But meanwhile, you have absolutely no clue. It's all observe and declare. You have
Observe.
absolutely
Don't
no
think
proof
we
of
have
what
it
you
all
talk about.
figured out.
Zero.
Don't think we have it all figured out, but we certainly can demonstrate specific things, specifically what we're talking about here, demonstrably, definitively, and irrefutably showing you to be wrong. Yet you continue to pretend in your own mind that you somehow have the upper hand, and it's just laughable, man. Come on.
Absolutely. You have demonstrated absolutely nothing.
Right?
Zero.
Because you said so. Because you chose to deny it.
You pronounced it, bro, so it's true.
No, it is what it is. It just is
Look,
what it is.
you look out,
Exactly.
you look out to the universe. You see, as far as the galaxy, as it gets far away from us, it gets redshifted. We see it until the CMB that there's no galaxies there anymore. It's a progress. It's not something we say we found the CMB. Now we can find all the galaxies in the way and see that by some, I don't know, conditions, they and correct me if I'm wrong, there was a period where the redshift was greater or smaller, and they separate the universe into like two sections. The one that the light was redshifting more, and one that was redshifting less. Why? We don't know.
Look, it's not my fault that your predictions are all wrong. You heard Professor Parks, right? You heard an
All of
honest
them.
person say that this is a huge problem,
Excuse
right?
me.
And he didn't.
I didn't hear him say that they're all wrong. I heard him say that there's a new observation that's not fully explained yet. Perhaps I misunderstood.
Yeah, he said he was going to look into it, and if true, it's a big problem for
Yeah, but
cosmology.
I don't recall him saying that. That means that everything is wrong.
Yeah, we had big problems before, and they will be solved someday.
Well, maybe so, but until then, it's a big problem. And he didn't even look into the Five
Data.
Sigma, which that is like spectacularly a big problem for you guys. Five
No, it's
Sigma certainty that dark matter doesn't exist. That's a huge problem right there.
Didn't that come from a fake satellite in fake space? Yet you're saying that, so yet you're using this to hammer the Earth. So, I mean, come on, you can't have it
Fake,
both ways.
fake, huh?
Well, according to you, it's a fake satellite in fake space. Yet you're using data from it to.
So you can't refute what I'm saying. You can't refute
What
the
I'm saying is,
findings. So
how can you use
you're resorting to this. Yeah, I know.
how can you use data from the Webb satellite in space and then use that to bolster the flat Earth position?
He won't address
It's
it.
called
He won't
backyard
address it.
strategy.
Oh,
Yeah, he won't address
it's
it.
called cherry picking. I'll
no.
pick and choose
In
what I
other
want.
words, coming into your backyard, taking your basketball away
Cherry
from you, and using your information against you.
called
Yeah.
cherry picking. Got it. Cherry picking.
No,
So,
I'm using your
Effie,
scientists'
Cherry picking.
findings.
Come in and well, but this data comes from a satellite in space. How about that?
You see, that's all you got. That's what I'm telling you. That's the
Wait a minute. So
beauty of it.
you're using data from a satellite in space. So you assert that the satellite is in space, that it is where we say it is, and is doing what we say it's doing.
You see, that's all you have. You
What do
can't
you mean that's
refute
all
the
I have?
issue.
What do you
That's
mean that's
you.
all I have? You're using data from a satellite in space to say that space doesn't exist.
See,
What is the issue here?
let me
What's
repeat.
what are you guys discussing?
It's called backyard strategy.
It's called cherry picking.
It's called coming into your backyard, taking your basketball in your court, and defeating you in it. That's what it's called.
Cherry picking.
Can you summarize the argument? I just hopped in chat. I'm sorry about that, but I want to catch up.
Essie's got a problem with light traveling long times. He thinks that, I don't know what he thinks, but he doesn't think that we can see 13.8 billion years into the past. He doesn't think that a satellite, or not, excuse me, a telescope sees into the past, basically.
Yeah, of course. But the past is so small that you can just neglect it, right? Like, you don't have to say it that way, but I'm with you. I understand what you're saying. But you can't say, like, oh, you're looking backwards in time. You're not, just because it took time for the light, the image, to get to the optics.
Right. He thinks we should be able to dial in a specific time we want to look back and see that time.
That's not what you're saying, though, right? That's from my understanding. That's not what you're saying. Yeah.
No, I'm asking. How does this work? You guys say that you look back. All this started when NASA got triggered. I put a Michikaku thing that he says a telescope is a time machine. We look back in time. And I asked them, so you guys believe we look back in time? And as we were going through the steps, they started saying, well, that's not really like that. It's the light actually left. And yeah, we got all into this. Yeah.
I see. It's just semantics, yeah.
Well, you would have to believe that a light. You would have to believe that a radio signal, something of substance, left somewhere, like I Love Lucy. The show left here intact as a single, traveled 13 billion years, and now we can play it and watch it on TV.
Something like that. Yeah.
I don't know about.
If there was an alien civilization 13.8 billion years ago, and they broadcast "I Love Lucy," and suddenly we're receiving it, yeah, we would see it from 13.8 billion years ago. How could we probably?
Yeah, this is where I'm absolutely lost. Like, you're not talking about propagation velocity of like the electromagnetic wave, right? No, right?
That's what they're talking about. Yeah.
Okay. Well, no, I understand what you're talking about. Actually, like I couldn't. The Lucy TV. So if they sent it like what, back in time, or they sent it 13 billion years ago, they broadcasted the signal.
Yeah, they're saying this. They're saying this.
Well, okay.
I Love Lucy got broadcast right in the 60s, right?
Okay.
Now, some civilization 10 billion years from now, right?
Yeah.
Will be able to pick up that signal if they're that far away and listen to the program intact.
Yeah, theoretically, yes, correct. Theoretically, we should be able to pick it up too. Just the amplitude will be diminished over time quite a bit. The energy of the wave, so it'll still be like theoretically, right? The vibration or the signal should be still there if you have if you can dial up enough gain with your amplifier without getting noise, because that's what's going to happen. You're gonna get too much noise when you crank up the gain to isolate the signal, because you won't be able to isolate it from the noise. You need a certain like signal to noise ratio. So theoretically, yes. Practically, no. Of course not. Like, but
so in reality, no way, right?
I mean,
in reality, mathematically, maybe on a piece of paper.
With enough power, you can do it. You should. I mean, for how many years though? But yeah, like there is substance. There is substance there in the scientific. Just in the physics of it, not do we actually use this? We don't use this, man. Like, but it's cool. Like, as a flat earther, like I'm cool with that. Like, there's nothing like theoretically, yes, sure.
Okay, I guess theoretically possible, but
for me, my opinion, man, this is me. I mean,
yeah. Hey, respect, bro. Yeah. To me, it sounds absolutely preposterous to believe that a television signal could travel 10 billion years out there. Who knows what it's going to meet in between and what. And it's like more than like the Twilight Zone for me.
No, yeah. We those who will meet something you will not see because they met something. But okay, you say it can travel forever. How far can it travel?
How should I know, Jackie?
I don't know. You say it can travel forever. You must put a barrier somewhere.
Well, take a walkie-talkie signal, or a CB radio signal, right? Everything has a propagation distance, right? You drop a pebble in the water. It ain't going to vibrate forever. It ain't going to go across the ocean. It's going to stop somewhere, right?
No.
You think if you drop a pebble, it's going to go?
I got you. I like this guy, sir. what frequency band are you on, and I'll tell you how far you can travel. Like, all right, tell me because this will actually make a difference. Like the wavelength. What wavelength are you on? I can do wavelength frequency. I'm good with everything. Let's go.
So tell us the longest one then.
Well, longer wavelength. I'm sorry. Go ahead, man.
What is the wavelength they use on the what's those probes? The Voyager probes.
I'll actually look it up. I'll actually look up what they say. Voyager con.
I know that the output is 20 watts.
Yeah, so it's I would assume it's microwave, like millimeter, but let me make sure, like 5 gigs. But let me check. Let me check. Because most satellite stuff is around that frequency.
20 watts SE. And this thing is almost one day light away. And they still hear it. They still control it.
Well, the NASA show he dipped, but he can tell us what band they're on quicker than I could find it. I would have to read too much BS.
Look Voyager mission. They have some data there.
Okay. Yeah, that's what I'm saying. I know there's data for sure. It's just I have to go read a lot to get it. I just want to get boom. Direct answer if I can. It's not happening. Regardless, man, that we don't even. I don't have to pull it up. Longer wavelengths propagate like pretty far. Shorter wavelengths, they get absorbed easier. So and scattered too. So there's all that we have to deal with. That stuff that happens to waves, you know, diffraction, refraction, scattering, all this stuff applies. So now in space, this is what I'm saying. Like this theoretical area, well, sure, theoretically, but down here, we know. Like we could only do the skip propagation, the bounce off the ionosphere. I've forgotten, like the 10 meter band, roughly like 20. Let's see. So that's HF, high frequency. So in the HF band, that's the one you can bounce off the ionosphere. Like others will not do that. So you have to be on that band if you want to use skip propagation. Like you want to talk to someone around the ball in your world. For us, we're just bouncing the signal, just right. You know. Like
doesn't it have to be below a certain? Like I think it's 30 to get through the ionosphere.
Yes, it depends on the time of day. That's at during the day. I think at night maybe 14 megahertz, something like that.
Yeah,
which is like 30s. I think 30 megacycles is 10 meters, something like that. So.
Yeah, I forget the exact amount, but it's below a certain amount that it can go through the ionosphere.
Yeah, there's
otherwise
a band. There's
they
a
wouldn't be able
range.
to communicate with their fantasy outer space satellites, right?
It's a window. It's a band, right? So like you have a window of frequencies that they will bounce off. That's why it's a band. So they call it a band. So the HF band will do that off the ionosphere. But the others will not. Some will penetrate, some won't.
Yeah, I remember reading it's below a certain hertz.
Yeah.
But whatever, we know some
whatever,
can get through it and some can't,
Yeah, anyways, but you talk about signal propagation, you got to know the signal strength and all that, and, you know, antenna type. And so nothing really travels forever according to our current domain. It's not real.
That's what I think. Yep. This is all fantasy, light traveling forever, and even if it has of course it has to have a constant speed, right, for their fantasy to work. Yeah. So it has to take time.
Actually, there is a theory that blue light is faster or red light is faster. But this is very hard to test.
I can prove to you that blue light is shorter with a very simple experiment you can do. It's not that simple if you have
speed.
The speed. Yeah. I don't know what. I'm sure I can look up the experiment data, but it should be pretty simple. It's not too bad.
No, you need to wait 13 billion years, and you need to know where two photons went out at the same time. Yes. How do you measure difference in speed?
Well, there's no. there's no experiment these guys have done with mirrors and lasers to actually prove that? Guarantee we have, because we have lasers of different
No,
colors.
on short distances you don't see it. But the theory that if the Planck is really like space is really divided to Plancks, then it will take for blue light and red light different time to move to space. Very slightly, you'll need a long time to measure the difference. I don't know what the difference will be if there is a difference.
I get the theory. Very interesting. Is it faster? I don't know. What did they conclude?
No one
slower.
tested yet.
Should be slower, right? No one tested it, huh?
I don't know which one.
Very interesting.
You need to read about it, but they say if the photon will need to jump from one Planck to another, then one of them will be faster than the other.
No, now I understand what you're saying. I thought you were talking about wavelength. I was talking about wavelength. That's my mistake.
Yes,
you talk about the
wavelength.
speed, yeah, like the speed of the
Of the
photon.
wavelength. Yes.
Yeah. Very interesting. Speed of propagation. Interesting. I will read about it. Thank you. Like right now.
Because the Planck length is just a number. We don't know if it relates to reality in some way. It's helpful.
I personally like science and knowledge. But I understand like there's a yeah, whatever, some people don't like that kind of science, but I do, it's not for everybody.
Look, the way I look at it is we lost a lot of light, a lot of light energy, and we got a lot of space instead. So I think this direction needs to be investigated. I'm sure it was. They always say that there's not enough energy. There's not, because if you convert the energy that was before in the universe and now, you see that how they call it, the energy that expands the universe is much greater than what we had before.
Yeah, I see that. See, that's garbage. But light stuff is interesting. This universe, nobody was there. So whatever, they can come up with all the theory they want.
I wouldn't say garbage.
Okay, cosmic microwave background radiation. The first results from the WMAP satellite. Do you know anything about that? Specifically the WMAP, because they launched another satellite, which is the Kobe Fears. Okay, and because the WMAP is a faulty instrument. Why? Because it showed that the Earth was the center of the universe. Because for a very simple fault, because we understand. Let's assume it's a globe, right? Why did we get this result? Faulty design, because water emits microwaves. When you actually see the graph, that's where you'll see all the microwaves were coming off of Earth from water. Because that, which is, we know this that from physics, a good absorber is also a good emitter. If water absorbs microwaves, guess what? It also emits it too after it absorbs it. So that's what we discover of the WMAP. So whichever way you want to slice the data, I can play any part here. I can play globe and shut it down. I can play flat Earth and shut it down. I don't have to. I can just shut it down from the faulty grounding of the black body to the instrument, to the actually satellite, the mechanical assembly of the satellite. That's why they scrapped that and they launched Kobe Fears. And there's problems with that too, the math, because that didn't give them the data they wanted. I looked deeply into this before Flat Earth, actually the cosmic background, and I didn't subscribe to it even when I was still like living on a ball like model. No, it actually made no sense. They fudged the data very clearly to fit their model, which is not proper science. So I actually wanted to get to the bottom of the universe. How was it created and all that? So that's what I was after.
That's it, roaches. Scatter. What's up, Cyrus? How you been, bro?
Not bad, man. Oh, he scattered. Oh no, what happened? He got
took
got
off.
scattered. Yeah.
Yeah. See, Cyrus, you just come with
He
this
got
genuine confidence, and you do know what you're talking about. So people are like, "Oh shit." Well,
Just go read it.
it's
Just
been
Google what
fun.
I'm saying, man. That's all I'm
Well, that's
saying.
the thing.
Yeah.
I know, but it's like they probably won't even do that. So like, you one up them just because you looked into what they believe, and we can't even get to the point where we've alerted them to the mistakes, all of the mistakes yet that they should be admitting, because they notice them too, right? It's not these aren't dummies, right? They're just stubborn.
Man, I was hoping for a decent combo with him. But he's gone now. So, man, I was
Yeah,
gonna get
he'll be
into the
back. That's
globe.
Chikey will be back.
Yeah. Because I'll enter his domain. Yeah, Earth is a ball. Let's go. Let's WMAP satellite, please. Like let's see.
Oh, okay, yeah, let's check that out. I always love these.
Whenever he
So
swings back around.
beautifully, put together.
Yeah,
I'm
that
not
tends to
disagree.
happen
Yeah,
when somebody
Montreal.
lays down some logic. Things tend to be quiet for a little while.
It's a little bit too quiet, though. You know what I'm saying? Like you just dip. It's like, oh, all right, that's not cool. I just want to hear something about the Kobe Fierce and WMAP.
Well, I don't know. He's got a puppy. Maybe the puppy's doing something. I don't know.
He'll go read about it, hopefully.
So far in the link he sent, I'm seeing cartoons. Not seeing anything real. This tracking schedule. So this is just cartoons and numbers we're supposed to buy. Oh, look, something's happening somewhere. I'm just going to believe this is a countdown, not arbitrarily placed on anything to support a narrative. No. Holy shit, they launched this fucking dinosaur in 1977? That's crazy. That is crazy. So they expect us to believe that thing's been up there for 50 years? 50 plus years now?
Functioning like a champ.
I guess. Well, there's probably not any oxidation in space, right? They'll probably tell you something like that.
Yeah, no cold welding, no radiation, no, expansion, contraction due to hot, cold. I'm sure the lack of pressure doesn't affect anything. Stuff like that. It's all good to go.
Have you seriously sat down and considered that you might have been duped by these stories? And if you answer right now, I know you wouldn't have thought about it. Come back. Think about it tonight. All night, Globers. Anybody, everybody. Think about how you could have been duped. If it's possible, here's how and why not. But if you haven't genuinely said to yourself, man, this whole thing could be just a fucking bust. You know, if you empty your cup and say, I don't know either way, I'm not going to believe any of it. Let's start over. That, to me, that's the best way to start out. Even veterans of researching with us or against us, rather, obviously that tipping point of growing still needs to happen. So however we got to get there, guys.
Hey, Montreal.
Yo.
All right. So, what's your problem with photons? I want to understand why you dislike photons.
When did
You
I
don't
say
know.
that?
You don't. Well, I'm just saying. I picked it up when you were talking to what's his name, other dudes earlier, NASA shill and the other guy. Picked up like you didn't like the photon.
I never expressed like or dislike to the photon.
Yeah, I just picked it up. Like I said, it is my deduction. I understand that you did not say those exact words.
Do we know what a photon is, first of all?
I understand what they're saying it is. Like, you know what I'm saying? You can take their photon and take it back to classical electromagnetics. This is where it really comes out of anyways. Comes out of like our electrical neck of the woods.
Well, I'm not so sure that I agree with what they say a photon is. Do you?
Oh, I don't believe in ball bearings flying in space. No, that's no. Well, I don't mind it.
Exactly. Yeah.
I don't mind it conceptually. It's cool as a concept to do some math with and shit like that's fine. Cool. I'll take that. Like as a ball bearing flying, no. The nature of light, no. But like because like when it comes in history, it's interesting, right? Why they come up with this photon stuff and like the packets of photons or discrete packets and shit like that. But
Yeah, because they messed up on something else. Yeah,
they did. Because they're trying to. This is where the Einsteiners enter the electrical realm to ruin it, to explain away electromagnetism pretty much and replace it with a ball bearing.
exactly, bro. Exactly. That's where they did the magic. Yeah, that I agree with you. Yep.
Because Max Planck, and that's what we still like in all from classical electromagnetic understanding. Well, we have the photon theory called the Planck. It's the same thing. It's like no difference, and that's what's like discovered that like this is energy. These units of this, photon or Planck's, whatever they existed in like discrete quanta. Right, that's the first. This is where quantum mechanics comes from. Max Planck and his quanta, his discrete packets of energy.
Yeah, the
Have you
amount of
noticed?
energy, quanta. Yeah, exactly.
Yeah,
Yeah.
it's and they happen like steps, discrete steps. That's why they called it like packets of energy because that's how it is. It just the energy that's like flowing down the let's say the wire or whatever. They happen at like these nodes or these crossings, Plancks or photons. They happen at discrete steps. So like here you would have one, here you would not, and here you would. There's like they're absolute, and they have fixed like the position in steps. That's why they say quanta. So and that's what 1890 something or something like that. So it's like, and then so they enter this domain, they ruin it with their garbage, and they continue on. Right?
Yeah. It's like one assumption after the other.
Yeah, you're dealing with stuff you really can't see. So I mean, so it's like I don't mind the photon. It's cool with me. You can use it, do some math and all. But is that the nature of light? No, I don't think so. I don't believe in ball bearings flying like that. But this energy transfer, absolutely, yeah, of course. There's energy going from A to B when you turn on your flashlight, obviously. You can see it. The flashlight is in your hand and the wall is over there. You click the button, the wall is lit up. It's like, cool. Okay, that's pretty cool.
Yeah, some say it propagates. Some say it doesn't travel. Some say light is always there. It gets activated. Yeah.
Believe what you want here. Everybody has their own ideas. I'm going to believe the founding fathers of the science of this domain in general, the electrical domain, and I'll subscribe to their ideas until proven incorrect. And all these guys are proving the older guys correct. The quantum.
Well, yeah. To me, it does look like it. Yeah. To each his own, right? To me, it does look like it travels, but I do understand the propagation thing as well. Like I said, light to me is the most mysterious thing of all. Mm-hmm. So, like, yeah. I mean, does anybody really know what light is?
It depends how you want to model it. So we're gonna have to model the stuff like mathematically, or what are we talking about, right? So essentially, you get something hot enough. Oh, okay. So we're gonna rewind time At some point, we are going to have to introduce math to what we're saying. But let's say, okay, back in the days, you get, discover, I burn stuff when I get stuff really hot. It glows. It emits light. Take a piece of iron, take a torch to it, start emitting light, a dull cherry and whatnot. And the more heat you input, so, and this is where we're going to theorize, but it doesn't matter. We don't have to. The more temperature, the higher the temperature of the object, the more glow it will have, and it will be brighter in color. So up to here, we don't have to theorize anything. We can do all this. What's happening inside the piece of iron? Now, that's going to need some theory. Outside, we don't need any. Just thermometer, torch, heat, just blast the thing. And you'll see that it will get brighter and brighter until it reaches like liquid, and then will vaporize and all that. So you can do this with any substance. Everything has a different boiling temperature and pressure and vaporizing temp too. So, but anyways, so this is where okay, stuff gets hot, emits light. Why? There we go. Right.
Yeah, but that's what they thought in the beginning. That's where the ultraviolet catastrophe came in.
Yeah.
No,
we don't need it. We don't need these guys yet. We're this is way before. Why do things glow when they're hot? Right. So later on, now they're gonna tell you why. Electron drops out, blah blah, orbital, blah blah blah, spits out photon. Cool. Okay. This is the math we have today to explain this old ass phenomena that everybody knows about, incandescence of elements, just from the days that man knows about fire. Get things hot enough, they glow. So it's why are they glowing?
Okay, yeah, okay. Why are they glowing?
Exactly. Why are they glowing?
We're talking about light now, right? Let's not
forget.
It
is. It's emitting light. The area around it. Why are heated objects glowing?
Well, yeah, that's the question. Why? Yeah.
Right.
Yeah. I didn't use any electromagnetism here. There's a torch. Blasted heat. Now we have light. So we have to now. We can just stop here. We don't have to do anything else. The double split. We don't need anything else. We can just stick here. But you understand we're going to have to enter the metal, right? This is the issue.
You have chemical light. How about the light coming from the sun, though?
Oh, right? No. That's too sophisticated. We're not there to crack it open to see how it works. We can just take readings off of the light and pretend like we know how it works on the inside. Thus, the readings, okay, so let's make sense of the readings. But the readings are the readings, so that's why they have to come up with their hydrogen fission stuff, because that's what it's showing. That doesn't mean we know how it works, but it's just that's what it's showing. Cool, take it. If you can come up with a better method in your mind than these guys, and I believe others can. It's just there's too much Einsteinism in mainstream science at some point. Never probably, but once people wake up and they burn the books of Einstein, I think mankind will truly advance, and perhaps we might actually understand the nature of the sun one day. Perhaps. With real, legit science.
Okay, so where are we now with light? Where are we at?
Well, I'm stuck with you at the glowing object. I need answers from you. Why is an object glowing when it's hot?
How did you get it to glow? What did you do to it? What object?
Torture. Torture. Torch. Grabbed a socket, heated the hell out of it until it's red. Yeah, like a socket piece of iron. Steel, iron. Yeah, socket. Just grab a socket.
So you took some iron and you did what to it? You put heat to it? What did you do to it exactly?
Yeah, correct. Input heat. That's all I did. Input heat. Only heat. Until it starts to emit light. Now, why is it emitting light? I'm just inputting heat. Of course, the flame is emitting light too, but we're going to neglect that. We don't have to do it that way. You can heat it by other methods where you don't have to use a flame. No, still do the same thing.
Know. What are you trying to say? Are you trying to make me say the known thing that the atoms are moving and causing radiation and glow?
Absolutely not. I'm actually asking you.
I don't understand where you're going with this. What?
Oh, nothing. I just want to know what you think is happening here, because this is where we begin. Sort of we don't. have to advance the concept like more than this, because the electron comes out of the vacuum tube and stuff like that. So that's later on. This is like so primitive, where the fundamental understanding here may help us out later with the what they call the electronic phenomena, or J.J. Thomson discovered in the vacuum tube, in the cathode ray tube. So listen, no, I'm not going. I just want to know what you think, man. So I'm not having a debate. I'm just ideas. I want to know.
Yeah. Okay. So far you got heat. You heated up the metal, and the metal is glowing. And you're asking me what I think is going on, right?
Correct.
Well, I think it got hot and it's glowing. What else can I can go into what I know from science, right? I can go into that.
Yeah, of course.
The particles are moving and all this, but I don't understand like what you're trying to do here.
Oh,
obviously nobody knows what's going
to do
on.
anything.
Obviously, do you know what's going on? You put fire to metal and the metal turned red. What's your explanation? Go on.
Oh, it got hot. Well, okay, it's hot, sure.
It got hot. Yeah, okay.
It got hot. Why is it glowing when it got hot? Why is it emitting light? Why is it illuminating, or that's incandescence? Why is it incandescent? Which it's emitting light. I mean, that's the Edison bulb. That's the principle it works on. It gets a filament white hot, so it emits white light, not red light, so it's usable. The problem was with Edison at that time was whenever you get anything to white hot temps, it just melts. Bloop, it just melts, man. So the trouble was in the filament. They didn't have tungsten yet at the time. Today we use tungsten, of course. But at the time, there was no tungsten yet. So
he experimented with horsehair.
Yes,
all kinds. Yeah,
it was carbon. Carbon was the answer in the end. Bamboo. Yes, that's it. Because he's like, yep. So carbon filament. Boom. Lo and behold, we have our incandescent bulb based on this principle of incandescence, where you just get something just white hot based on just simple heat input, and it will emit light, very usable light. So this is where I think it would seriously help me out, or help everybody out, where this is where it's like you can stop here and try to understand this phenomena before we now go to shoot the stuff, like, because it's already shooting out, but we're trying to understand the emission bit. That way later on we'll study the transmission bit, but we need to kind of, I'm at the roots here. I'm at the fundamentals. I'm at, like, why does stuff emit light?
Good question. I wish I had the answer for you. I mean, this is the age-old question. This is how quantum mechanics began, like from these questions that you're asking right now. And they still haven't figured it out, by the way. So, yeah. But I'm interested. Go on. What do you got?
So is it spitting out photons at you, or is it spitting out electromagnetic waves?
It ain't spitting out anything, though, the way I see it. The best way.
I mean, it's emitting light for sure. It's like it doesn't go all. It just in the surroundings. Depends how hot your socket is. Let's just use a small little piece of iron. You'll see the glow. Like if you got on a piece of concrete or whatever, your anvil, whatever you're doing this on, the glow will be around it. But the more, like, it's just in a small little vicinity, just an inch around it or whatever, just a little glow. If you're in a dark like area shop, the more heat you put into this thing, the more the light will expand out. This radiation, right? This radiation will expand out, and you'll see that there's a bigger sphere of radiation around it now. It's glowing absolutely brighter, and the light is going further now, and it's illuminating more of like your desk or whatever, your anvil, whatever you're burning this on.
So, yeah, but there's a limit, though. There's a limit. Even if you increase the heat, you can increase it and make it glow more and more. There's a limit to where the glow will change.
Yeah, depends on the material, like vaporization temp, essentially, because you're gonna go from solid, liquid, gas right away. So your iron eventually will be gas, and you won't have any. The socket will be gone. Eventually, just keep heating it. So that's the idea. Well, what's being emitted out of this solid object, such as just a little chunk of iron socket on my bench.
Well, it's called radiation, for a lack of a better term, right?
Yeah. I just called it something that's kind of radiating from it. Just to use that term, because it is beneficial later on as we develop ideas of what's going on with this hot object. Why is it doing this?
Okay, so next. What's next?
Oh, dude, I'm not going anywhere. I need to understand what's going on here. I understand that I cannot approach and actually understand. I can pretend that I understand if I keep on going, but because I didn't understand the building block. So if I don't get the building block, anything else that's said after this is just belief. Whomever says it, I'm gonna just have to take their word for it, because I don't understand myself what's going on. So, I'm gonna have to subscribe to something and see if that leads me down a useful result. And if that theory is incorrect, I have to scrap it based on experiments. But I'm gonna have to theorize now, because this is science. We observed something, and we have questions. So now we need to set up an experiment, right? Because we observed illumination from the object when it got heated.
Right.
Yeah.
Heat caused the object to glow. Yeah. And people with Forge figured out that if you put air in there, right, it'll even get it hotter and make it glow even more. Right?
Yeah. Because that's
so heat
because they're burning
air
carbon.
equals more. Yeah.
It's oxygen, right? It's not. Yeah.
Oxygen. Yeah.
Right.
For lack of a better term.
Sure. So sure, yeah, it glows brighter. So absolutely, we discovered that heat. But why does the heat cause it to emit light? The solid object.
Well, the carbon thing kind of threw me off, but
that's in the forge. You're saying that the blow, when you in your furnace, when they discovered that they're burning coal. When you blow into this forge, now you created a hole and you force some air through it. It burns way hotter. The coal will burn way hotter. Now you can actually start to melt steel, where you won't be able to melt steel. You'll get it soft and hammer it, but to get it to actually start melting, you need some really hot fire.
Well, at the most basic, fundamental understanding, wouldn't it be that each of the envelopes are just vibrating at a high enough?
No, we're not there yet. We don't have equipment to do that with you. We don't. You can theorize that. Now, good luck. I'm taking you back to 1600s or whatever, or even way earlier than that, when people discovered this really early on. But not till now. We were made bulbs out of the concept. Just in the past 300-400 years. Not I'm not rewinding further than that. Just in our recent history.
So I'm following.
Yeah, we have to why is this object doing this? Because this is going to go later. This is where Thomson comes out, J.J. Thomson, right? And he discovers the electron. And after that, because of his discovery, oh my God, the table of element drops in place and all that. This happened because of the electrical realm. It was happening together, because these guys discovered this and these guys were working on chemistry, and boom, 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 boom. So they started developing really good ideas, especially Thomson. So I don't want to take you to vacuum tubes yet and field emission versus hot cathodes. I don't want to take you to the cathode yet, but I do. That's eventually where I want to build up and go to the cathode, because we're going to discover something interesting. Yeah, the corpuscles. Yes.
Matter.
Mm-hmm.
Didn't read those, so I may know where you're going with this.
Well, no, I mean the hot piece of iron is emitting quite a bit of infrared, a lot of heat off of it, and you can measure this. So it is emitting Now, even that, the photonic guys, yeah, that's a yes, it's emitting photons, infrared, even if you can't see it as heat, infrared below red. But that's most of the heat transfer with hot objects happens in a non-visible red area. It's actually like the electromagnetic wave. So why in the
Okay.
world are these
So you
atoms
don't have.
emitting electromagnetic or photons? Like, this is within the metal. You see, this is the issue here. So you have to go in the metal morphology now. This is and then we're going to work our way out of it back to electricity, and then into morphology again, because we have weird phenomena here with the cathode ray tube,
Okay.
and then
So
X-rays and all that.
assuming that we understand temperature and pressure, and we're moving on from there without any equipment, right? You're going back to primitive days. So what next?
Well, I mean, once we develop an idea here, we're gonna go forward in time pretty quick. But yeah, why is it? You know, you can verify today it's emitting infrared. It's like everything emits infrared. Okay, waves / photons, however you want to understand it, I do not care. But this infrared discrete quanta of energy, you can say there we go. J.J. Thomson's like language. So, yeah, what's going on here? If we understand what's going on with something like this, copy image, where you actually have to wear like eye protection. It gets pretty bright. You can't stare at it. And you can absolutely feel the heat. That's why they're wearing something that's lined with like silver or metallic lining to reflect the heat, especially the infrared waves. It's to reflect the waves, the infrared, more than anything else, more than the visible spectrum. The infrared is where a lot of the heat that will burn you from really hot things.
Yep, we're good. Infrared heat, shield. Got
Yeah.
it.
Well, yeah, we're going to have to make up something at this point. We're going to have to subscribe to a theory. We're going to have to assume and kind of carry forward in time because we have these guys that did the experiments for us. But if we were back then, we're going to have to make an assumption and carry out an experiment, right? Because we observe something in nature, but we don't really know why the metal itself is going. We understand we input heat, but why is the heat now? This is the right where, cool, check. Heat caused this to glow. Now, why did heat cause us to glow? Now it's like, all right, you're another layer into the question, which is like interesting because this is where the quackery comes in here. When we're like, we try to enter the metal with our minds to understand what's going on mathematically, so we can model it and like predict it and make shit out of it, essentially, right? That's what we want to do as like a mankind, or to innovate.
Yeah, but you say okay. So you introduce the heat. What is the heat? What is heat? It's a higher vibrational electromagnetic wave.
No, see, this is where it's like, all right, you're gonna have to. Yeah, I see that you have your vibration hat on. This is advanced science. Vibration shines in morphology when you go in the metal. So right now we're gonna table it for a second with the fire, because the fire that you're using on your torch is an oxidation reaction. It's exothermic. That's why it creates heat, but it's oxidation. It's a chain reaction of oxygen attacking the fuel that you're burning, unless you have flame in your torch. So it depends on the fuel and all. But anyways, so we're just going to use that subscription for no vibration yet, because that's going to come. We can't. If we introduce vibration now, we're lost. Like this comes out later, like vibration stuff. At this point, it's kind of like you use it. It won't shed light upon you here at this level. You can use it later to actually understand more, especially the quantum
So you're
mechanics
looking at
and stuff like that.
the structure and the composition of the metal.
I'm trying to get an answer, like, why is the metal emitting light? Is essentially it. Why is the metal giving me light, and the more heat I give it, the more light it gives me? And it just happens to be the same temperature that will emit the same color of light for all like substances at that temperature, which is very funny. It's like, oh, okay. So if you see anything that's like yellow hot, right? It depends where the yellow, like bright yellow hot, that's like 1100 degrees C, right? It's just like anything. It's just like doesn't matter, which is crazy. So that you get this later on too. People do this to get shit red hot. Well, they discovered that stuff really glows red at the same temp, and yellow and white. So it's very interesting. So based on the color, just the color that the object is emitting, we can actually determine temperature very accurately. So this becomes
Well,
another
see,
thing we discover.
I
It's
would
super interesting.
assume. I don't think I can take the vibrational hat off then, because it's when you're talking about the different colors, it's ranges of wavelength and frequency, intensity,
It's
energy.
Yeah, but frequency frequency is just how fast you're cycling something. So what are you cycling with your vibration? See, that's what I'm saying. It's incomplete what you're saying.
Wavelengths,
Of,
wavelengths, and
of what?
ratios.
Wavelength is a length of a wave which has a trough and a peak between. You know what I'm saying? So the length of that physical wave is wavelength. So wave of what? What are you talking about? You see, that's what I'm saying. You introduced it too early. Too early of a hat. So what are you wavelength of or frequency of?
Vibration is what I
No,
would say, but
no. Vibration, same thing. Like no, it's essentially how fast the vibration is happening is what you're saying is frequencies. How frequent is it vibrating, or is it cycling?
it's resonating with the thermal ether.
Ah, yeah. See, we can't word salad. No, can't do that. We
Word
have to.
salad, my butt. That's not
That's
word
word
salad.
salad. No, we're trying to get somewhere with science. No, that's so. Okay, cool. How are you going to test that ether resonance theory?
Well, perhaps you change the substance. Maybe I don't know about the pressure, but you change the substance and you vibrate it at the same frequency, the same wavelength, the same ratio, and see if you get the same effect. See if you can expose another substance to the same thermal variables and cause it to resonate with that frequency and see if it glows the same color. That's where I'd start anyway, with my thinking, which is very remedial, I'm sure, but
No, it's too advanced for this. Where it's like it's can make you like lose grasp of what's going on. But because if you subscribe with the oxygen thing, you will actually get somewhere, and you can empirically test
okay,
it.
then you would
For the flame.
you would
Why is the
conclude
flame hot? Or
the ether had a lot of oxygen in it for it to resonate with it. Like the thermal ether would probably resonate, I would assume, like where I would go from there with oxygen. So I'd find substances with oxygen, maybe. I don't know. I don't know where you're. I'll just sit back and listen for a few minutes, see where you go with it. Because I'm stuck.
yeah, there's too much stuck on too much vibration. Gotta drink less of the vibration cup, more of the material cup, because the vibration comes from the material that we're vibrating.
So you increase the pressure, and you cause a differential in the pressure, which is greater enough than the substance that's glowing.
No, what pressure? Pressure in what? Great. Okay, pressure of. See, it's incomplete.
It's
Like
caused from
pressure
the
of X.
vibration and oscillation.
No. That's what I'm saying. Word salad, I can tell. Like it's good concept, but we're trying to mathematically pin some, like narrow it down so we can stick some numbers and formulas to what's happening. Because we have to understand what's going on here. Because the electron photon comes out later. We don't need electron photon or vibration. We just need fuel. More coal, baby. You got more coal, man? Yeah, let's get this thing hotter. Right? He's, oh, look, it emits more light. More coal equals more light. Anyways, we'll bore everybody with this shit.
Oh, I'm right here on the edge of my seat waiting.
Well, no, it's a long journey to get to the vacuum tube now.
So bring us to the next stage. What are you looking for? A chemical reaction with the air? What
No.
exactly are you looking for?
No, that was for the fire. That was just for the flame. Or she mentioned the fire of the flame.
Okay, so we heat the metal. The metal
heats
up, produces radiation. Next, what you got next?
All right, cool. What do we got next? So radiation of electromagnetic waves or photons? Which one are you going with here? Because it doesn't matter. It won't matter really.
Neither at this stage. How do you know? It's a visual thing. You're going. Well, it's two things. You got heat.
Mm-hmm.
You got heat that you can feel, and you got visual. You got light. So you're going with two things here. You're going a color change, and you're going with heat, something that you can feel. Yeah.
Right. Yeah, and we're gonna like fix the color or something. We're gonna take this now into a bulb, into the tube, the filament, Edison, and we're gonna go to William Crookes. So we're gonna take that filament. We're gonna make it out of tungsten.
So now we got into the electrical field.
Yeah, because
we're into
we're gonna
the
heat it
electrical realm.
Correct.
Yeah.
Because I'm going to do the same effect with current flow in the filament, right? Not like from a battery, just straight up battery, direct DC, not AC. So there's no vibration because we're not introducing an alternating signal to the filament at this point, right? So there's no waves like radio. There's no RF being emitted, right? Because like we have 60 hertz coming out of our wall, right? So essentially, like all these wires are 60 hertz antennas because they're emitting actually this vibration, which is a fluctuation of the magnetic field at the generator, right down the line, because the shaft is rotating, so it's fluctuating north south. So every time it does that, that's why you get flip flop, and that causes a wave to ripple out, electromagnetic wave.
It's alternating. You mean it's
because it's alternating.
Yeah.
Yes.
Yeah.
So if you have a wave like that's it's called the transverse wave, right? The transverse or the sinusoidal wave. Okay.
That's the up and down wave.
Mm-hmm. Correct.
Right.
That's the sinusoidal wave.
Okay. Yep.
So we're gonna take this same filament. We're gonna excite it electrically now. Same thing, and we're gonna use Edison, of course. Now we understand. We're gonna use something that can get up white hot and all that. And we evacuate the bulb because oxygen, when you get things that hot, oxygen is really reactive and it will oxidize it. So your tungsten or whatever filament, if you don't evacuate the bulb even partially to remove most of the oxygen, your filament will get destroyed from the first ignition. From the first, it will just turn into oxide and you'll see it turn into powder, like tungsten. So you can test this out. Just break the bulb envelope, grab a $1 bulb, Edison bulb, break it, plug it in, boom, poof, it'll go up in beautiful smoke, and you see the tungsten will have like a white oxide layer on it. Because it got white hot in the presence of oxygen, it got attacked really bad, and turned into pretty much tungsten oxide, which is what you have, this powder that you have in your head now. So tungsten is gone now, turned into oxide. So we remove the oxide. We know that this stuff is not good. So get it out of the bulb. And we have our incandescent bulb. So we're going to take this bulb now, and we're going to kind of modify the concept where I'll do a cold, which is now field emission. I'll do something called field emission, and like regular hot cathode, or they could just call, what do they call that? Just regular, actually, mode of operation of vacuum tubes. So. Because light bulbs are essentially they're vacuum tubes. Not all of them. Some have like filled gas, but they're evacuated from oxygen in general. All of them, because we don't want the stuff in there. It's going to attack our stuff when it gets hot. It's going to destroy what we're doing. And but for vacuum tubes with the cathode ray, because I want to get you up to the electron photon. All this is really quick. So when we have like a capacitor sort of thing arrangement in a vacuum tube, when we don't have air between the plates and we pull a really strong electrical tension between the plates, of course you'll get discharge, right, at some point. But in order for that discharge to happen, this arc spark to happen, actually needs to ionize the air. It needs to charge the air to create a filament, a wire from the gas to flow through, right? Otherwise, space does not conduct electricity and it can't flow.
Polarization.
Yeah, well, yeah, that's why, it ionizes the gas, it polarizes it in a certain way, negative, whatever, so it can flow now. So JJ, when we do this, he discovered that there is a ray that comes off, right? That's invisible, right? That will excite a phosphor screen when he puts it on there, okay? And this is where the electron comes out. And like this is where, and also morphology of the electronic theory of materials. Up to this point, the electron and the theory of materials, there wasn't like chemistry, they weren't tied yet. But Thomson, because of this, and he measured the speed of the, you can replicate his experiments and do it of the electron and stuff like that. So this thing that we just pulled out of the metal electrically, we pulled it out of the metal, right? And if we do this at room temperature, it takes higher voltages to do it, to strip it out of the metal, right? To get this electron sort of thing in the tube to flow, to fly. They are charged because you can magnetically deflect it, because TV is going to come out of this, right? And the image. So this thing is legit. It's electron thing, whatever phenomena is pretty legit. And from that, if you heat the cathode, okay, well, we discovered this. If the cathode is hot, especially at glowing temperatures, it emits more electrons. You can strip off electrons at lower voltages. You can just pull them off easier, right? And of course, my subscription is the lines of force, not electrons, which are electrons in the metal. They're the termination point of the lines of force between metals from the electrical fabric, the electrical lines of force, according to Thomson. So this thing that we strip out of the metal is the end of this tube, the electrical tube, when we actually break it out. So when the metal is hot, it lets go of these tubes way quicker. And this is the electron, essentially. And then when it hits the phosphor, right, because it has it's bigger, than the photon, it will excite the phosphor, and the phosphor will give you visible light back to your eye, because you can't see this electron. It will absolutely excite the phosphor and give you a visible. You can use that for down conversion to give you visible light, because it's not visible light. You see, so that's where the electron. And after that, they're going to call it the electronic, theory of materials, composition of matter, electronic theory of matter, because this is what they call anything electronic during that era, early 1900s. The term electronics we use today is incorrect, because electronics referring to the electron in the tube, right? So TV was, electronic and all that.
I still have one of those radios with those tubes.
Yeah, tubes.
It's too cool. Yeah. Just to see them glow, man. It's something else. Yeah. Well done there, Cyrus.
Yeah, I'm just trying to. And then this is what they saying, right? This electron, let's take in the case of the phosphor. We definitely know we have this charged, appears to be a piece of matter, a really small piece. We strip that out of the metal when we do this, and this thing has enough excitement in it where it hits the material. The phosphor now is going to take that energy from a higher level, like the invisible light that you cannot see, because they will do that with UV too. That's how we kind of we try to understand now what's going on, because ultraviolet will also do that, right? It will excite phosphor, even though true ultraviolet, your eye can't see. It's above what your eye can see. But once it strikes phosphor will down convert it to a visible light. And we do different blends for different colors, of course. But that's how this works. So this down conversion they call electron dropping in orbital from higher energy level to lower energy level. And they say when it does that, it spits out a photon in the process. And that's what reaches your eye. That's what they say. But you see how closely related this is all, man, J.J. Thomson, all this, and these guys believe in fibers. The reality around you, it's a fabric. And when we break the fabric, we get the electron, because it's a termination point of the tube of the thread of the fabric, you see, on all materials. So when you do that, go ahead.
No, go ahead. I thought you were.
No, I'm done. That's the idea. This tube of force or this line of force is terminated in the middle. So when you pull it out, you're pulling something subatomically out of the element, which is super interesting. And this is a different fucking world when you understand JJ's, because JJ's the guy. He got the Nobel Prize for the electron. Like and man, grandfather of electricity, and his stuff. If you subscribe to his theory, then you'll develop phenomenal ideas in your head with the tubes of force, which is the electron, right? And after they're going to take that and they're going to build a table of elements, they're going to refine our world with that concept. So this thing is real because, of course, you can see that it excites the phosphor, but what the hell is it? We don't have to really know. But if you do want to know, because we pulled it from inside the metal, it will shed light upon how matter is made up, because every table of elements, all this stuff represents is literally the ratio of electric fluctuations inside of material. They know it's electric. That's why they have the table of elements for you. It's a ratio of protons to electrons and all that, atomic mass and all that. It's just all of it is electrical units because of this man right here, Mr. J.J. Thomson, and discovery of the electron, the subatomic particle, which is not particle. But all it is they're going to quantify this into electrical terms now to lay out all the materials in our world.
Would it just be like a phase change at the point where the polarization happens, so that you, which
plasma,
gives you the light? Yeah,
plasma. Yes. There's a phase change.
Because when they measure off the plasma beam, no matter what the intensity of
electron beam. Yeah, electron beams are non-visible. That's the thing. So in order to get electron beams, So if you pull up any electrical discharge bulb, right? So they're under discharge bulbs. There's HIDs. There's high intensity discharge, and there's like low intensity. Neon bulbs are low intensity, but this filament, when you see the neon glow red, that is current flowing, and that's charged. It's negatively charged. That's just ionized gas. It needs a gas to do this, and the gas will glow and get excited. And you're right, it will go, because of the electrical excitement, it will go through a phase conversion from gas to plasma. And they're saying the down conversion back as it cools is what emits the light. This down conversion of the electron excitement state of the outer shell of the gas. We don't have to suck to that. We don't care about that right now.
Not just a phase change of matter, but a phase change of energy.
Yeah, but in the cathode ray tube, in order to get cathode rays, you got to get the vacuum down low enough where you don't have plasma. Why? Because we want air molecules or gas molecules will immediately deflect and reflect and absorb the electrons. So you will not get this electron ray in the unless you get the vacuum down really good, where you remove a lot of atmosphere, a lot more than like neon bulbs and all that. They're not. I wouldn't classify them as vacuum tubes because they're partially filled tubes with gas. It's filled with a rarefied gas at low pressure. So it is a gas tube. So it's a gas tube discharge. That's why they call them HIDs, high intensity discharge bulbs, not vacuum tubes. Edison, that is a partially evacuated tube, correct. You can do an Edison bulb with an inert gas backfill. It just costs more money. No need. So you can make it into a gas, just a backfilled gas, while you're just glowing the filament. It wouldn't be a discharge tube. Discharge has no filament. It's a physical separation between the anode and the cathode, the two ends of the wires into the glass. They're not touching each other. You're going to make the electricity, you're going to make them touch each other with plasma, with this gas, this hot gas that's carrying electrical charge down with it. And it will absolutely carry the charge. You can test it. But only when you get the plasma. Once you get the plasma, now you got current flow. To get the plasma, we're going to increase the tension. We're going to increase the voltage. Bop, 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 until the voltage does what? Breaks one of those. Now we got plasma flow. Now it's ionized. It's charged enough. We have current flow. But we're not going to get into the theory of the current flow.
An arc with plasma type deal.
Yes. Yes. Any arc, correct. Any arc is a plasma arc of whatever gas that's surrounding, 100%. And without the gas, you cannot create plasma. We understand this. So we need to remove the gas to create the ray of electrons, not the ray of plasma. We need to get rid of the shit that will cause the plasma. So we're going to get rid of most of the gas now. We're going to get it really, really low. Why? Because we want to create an electron stream. And this is why it's called cathode ray tubes. Now, just all you have to do is just Google CRT tubes. All CRT tubes are cathode ray tubes, where they have magnetic. Yeah, yeah. All these are TV tubes.
Yeah, this is crazy stuff. This is fascinating stuff for sure.
Oh my, bro! This is because of what happens down this road with tubes. With a man called Philo, who's Philo Farnsworth, inventor of the TV. They scrub electrical research, right? It gets interesting, right? So there's stuff here that gets snuffed out of history, especially like the inventor of the TV.
Because they're reaching into counter space. They don't want you to understand that portion of it. Reaching into... I mean, it's okay. Why would they choose inert gases to begin with, and then to remove the gases, because it would polarize it and give it like somewhere for it to flow. So if you remove all of that, then you don't have that. So it's like just each step closer to counter space.
You should make a presentation. You should whip something up, and we'll schedule a presentation if you like.
I've done already 2 on electricity before, man, but I can always fire up, and I've been asked for a 3rd, so might do another. Why not? So look, and this is the electron gun, essentially. That's why they call it a gun, right? All these are this is the term electronic comes out of here. Anybody spits out electronic, doesn't know what the hell this thing is, just don't tell them you don't know anything. Just scrap their beliefs, scrap all their knowledge. Talk about electrons and they don't understand the CRT. No CRT in your mind, no electron. I'm sorry, because that's what JJ was playing with, the Crookes tube, when they discovered this stuff, this invisible ray. Because at the same time, a guy's about to discover X-rays playing with the same exact device. So yeah, Mr. What's his name?
Have you heard of? You must have heard of this. Have you heard of the Tesla cathode ray? The one he made. He named it something else, but are you familiar with Tesla's work with stuff like this?
Here, Tesla is where I started, bro. Of course. You talk about his open-ended vacuum tube.
Well, he called it
about
cathode ray.
Are you talking about the one that he tested it on, like a pendulum made out of different materials, spheres? Are you talking about that? The tube that made stuff move, physical matter at the other end?
No. I'm talking about an actual X-ray thing. But he called it a cathode ray, something like that. And he actually took like X-rays, like you see a person's foot,
his hand,
with a shoe, and you see the nails in the shoe, and I don't know if you've seen that one. That's freaked out.
I have. Well, from my understanding too, but I this is just not mainstream. But Tesla's the
no, definitely not mainstream.
Yeah, Tesla is the inventor also of X-rays, but it just happened too close. This stuff was happening so close in different parts of the world. So Mr. Röntgen comes out with it, and like a year before, but I don't think Tesla published his work before. I'm not sure. I have to go dig into that. But I accredit both of these guys because they're physically separated for the discovery of X-rays. But regardless, it comes out of the electronic phenomena, and only from the electronic phenomena.
Absolutely.
And what we do is we just take you can make this. You can make X-rays out of any tube. You just you need acceleration, which just happens to be directly correlated with the voltage between the plates, cathode anode voltage. So you get this electron happening, this cathode ray happening, and you crank up the voltage to like 100 kV, any bulb will emit X-rays, right? So now we have this so-called electron or corpuscle flying so fast in our evacuated envelope that when you smash it into the anode, we need theory now. But regardless, we're going to block out what's going on. But Mr. Rentgen and Tesla discovered that there is another order of waves that come out of this. And Tesla's going to have his own theory of X-rays now that's not really written about. But that's a wonderful story for another day, maybe. We'll go with the
Yeah, check it
mainstream.
out. I posted a thing of it. It's pre-Rottingen. Have a look.
19. That's when he discovered it. 1895. The Rontgen or whatever. Rontgen. So watch X-rays. Let's see. Rontgen published his stuff. Let me look it up real fast. It's right around the same time. And by the way, the power, the wattage, this guy, this madman Tesla was working with, because this is why his X-rays were not the same, and he clearly said they are not electromagnetic waves. This is why I said Tesla comes out with his own thery with X-rays.
Bro, you're the only one that has said that. Exactly. They were not electromagnetic waves.
This is my bread and butter, bro. This is where I understand why the where you follow this the tube. What happened with the electrical world and the electronic phenomenon? Oh my God, we have the table of elements now, dude. What is going on? And then it was funded heavily from the government and then snuffed out by the government. No more tube research. Boom, monopoly. Whoa, illegal to what's RCA and all that. During the war, they used the excuse of the war to snuff out the tubes. And then, funny enough, when they, because I kind of like tubes, when they come back from Germany, I mean, after World War II, they come back from Germany. For some reason, AT&T puts up the first coast-to-coast, if I'm not mistaken, telephony using these Klystron tubes in the 40s. So this is later. But right there, 30s, because Philo is right there, right? 30s. Right, and all that, and he's the only, according to the wizard, I believe he's the only man that understands what electricity is today, still alive. Eric Dollard, the only man on video in the 80s, replicated Tesla's stuff, proved his direct,
he learned it with Philo
longitudinal.
Farnsworth, right?
That's correct. Yeah.
Yes, and he stayed with Philo's family, and he said that Philo was the only man to understand truly what the electron was, and that's it. Because, correct, even if you read on Wiki page, read Philo, I've been studying Philo deeply, man, for the past week, you will see that he's the guy that invents the, they don't give him credit of the TV today for this reason, right? So he invented the all-electronic vacuum like television, which was, at his time, they were experimenting with this electron tube, because now tubes can see too. We're further in now, not just the emit light. You can use it to capture light and now display it on a screen, right? We're up to that point, but not a TV yet, because like you have to scan and image capturing. Like he also, if I'm not mistaken, Philo invents the video tube, the tube that can capture image, right? So the TV thing was the rasterization, like the scanning and lines. So they were all like electromechanical tubes to be able to do this, to display the television, something on the screen. Philo's the first guy, and it had serious issues. You can read about it. Philo's the first guy to make an all electronic television. That's what it was called. That's what he was famous for. He made $0 off of it. All electronic, as in no mechanics in the bulb whatsoever in the tube. It was just all like electric, right? Wow, we understand. It was done by the electron. He used the electron to scan stuff. So, of course, scanning electron microscope. Who invented it? Philo Farnsworth, of course. One of the greatest tools I love today. And used these little things that were shooting out of this ray tube, the cathode, essentially, cathode gun. You can actually scan material at a really, 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 really fine detail. Because they're pretty small. So it's very interesting. Anyways, and they excite material, so they emit electrons back and whatnot. But this is where the electron comes out of. Tube. Then Philo just takes it to a new level. But essentially, you have to rewind back to the photon thing. This is what they say, the down conversion from this thing that we're accelerating pretty fast. And if you accelerate fast enough, when it smashes the anode on the other side, now it's going to spit out X-rays, right? And the X-rays of Tesla and the magnitude he was working with, if you were standing in front of that tube, Tesla's tubes today, as he was standing in front of it with the GE tapered anode tube, you're dead. You're dead in like seconds. You'd be cooked. So standing in front of like a 15,000 watt wall of X-ray tubes. Continuous, like he's just running it, not like Paul's. He's just running continuous. Oh my God, bro! You understand? This will cook, like this will literally cook material. But no, he didn't get cooked. And so Tesla, his understanding and his X-ray tubes were not the same. And this is so snuffed out. It's hard to get any written material on. Besides the little snippets that Tesla talked about.
Look at 43 past the hour, what I posted.
43. Oh, this is the open-ended vacuum tube of Tesla. Yeah, I know about that one. Yes, this is genius. Genius idea. I've never heard of that. I was like, what a genius. Of course, he's the one that's going to make the open-ended vacuum tube. What a crazy man.
Death ray, he called it. Yeah.
Compressed air. Yep, that's the open-ended vacuum tube. Yeah, the thing is, the rays he shot. That's the thing with Tesla and his tubes. They're operating on the Tesla current. That's why he didn't die using those X-ray bulbs at the wattage he was using. But
exactly, because he wasn't using electromagnetic radiation.
Correct.
Like he said.
Correct.
He separated it somehow. He explained it. Well, one of the person that wrote the thesis explained it like he passed it through magnetic
quench spark gap.
Yeah. Exactly. Yes, sir. Exactly that.
Correct.
And it's all in the gap. The power was all in the spark gap. That's where he got all his power from.
And you, man, you're actually onto the true nuggets of free energy. Wow. You're reading Jerry Veselatos, aren't you? But yes,
that's one of the guys. Veselanos. He did the thesis. That's correct.
Yes, yes. The secret is in the gap. How in the world do you isolate this? And that gap.
It's insane, bro. It's insane.
Well, later on, post Tesla, this is where it gets weird. The secret is right here, and people replace that with tubes. And this is why, for another reason, besides Philo's phenomenal story, we have another side phenomenal story of why tubes get snuffed out of existence. Because you have these crazy nutheads that are trying to extract energy out of the ether, and they do. Okay, following Tesla stuff, especially when they replace the spark gap with a tube of certain design. Right? So, and what's his name? One of the guys, he demonstrated this, man. He would light up bulbs and he'd stick his hand in the water and he'd use the water to conduct it.
Ballard recreated a thing with spark gap. He recreated one. Yeah, and he created the white energy, and he showed that the bulb with the radiant energy
attract the copper.
Yeah, bro. Yeah, you know your shit.
You watched it.
Exactly.
His materials.
It had an attractor. That's right. Yeah. Exactly.
That's why I believe what this man says, because he's like, go read this and that and that, and here I've done like he's the only man on the internet alive still that you can find that actually replicated Tesla's work. Because
that's
Tesla's
a
work
true
had
genius,
issues.
like a walking genius, like in our time. Yeah, Dollar.
Yes.
Yeah.
And Dollar, that's all the stuff that I get it from the books that he told us to go read back in 2012, where I had privilege. So did Ken Wheeler. That's why he's got this stuff to be on this website where these are the guys that found him in the desert, and they were posting phenomenal material. They actually got taken down for copyright strikes and stuff like that. So actually some of that footage my friend has, and I got a copy of it, but it's actually no longer on the internet for anyone to see. And they had a phenomenal book deposit website. They called it Key Chests, and that's what I cried about. Like when that website, when the gremlins, like Dollard said, they always come out of the woodworks and they find him and destroy his lab. When that happened, like his words came true again, right in front of me, as he's spilling out all the knowledge that he's got, and all this gets taken down. And the website still exists, not Key Chest. Key Chest is gone. And the other one, more than half of the content is no longer there, and just kind of like fluffy ether stuff now. But all the dollar stuff got taken down and all that. So yeah, what he said is true, for sure. But he just gave us the material. Go study this. You'll understand exactly what I'm saying. When you study it, you understand the electrical history well, which sheds light into all the other sciences, especially chemistry. Remember, because right now, like, I'm really into morphology and chemistry and quantum mechanics, which I'm going back and rewinding time and walking with these guys as they came up with stuff. And I'm saying it's just crosstalk between everybody. And J.J. Thomson is at the center of everything here, actually. It's like, wow. If you're trying to understand this shit that they don't understand, then you have to stick with J.J. Nobel Prize, Rutherford too, but you don't have to. JJ's got phenomenal ideas. He's got phenomenal understanding of the Faraday tubes. And Röntgen, right? So with Röntgen, however you say his name, the X-ray, because he did this cathode ray. He discovered that it would still go through materials, like thin materials. It would excite the phosphor screen even when he put like something in front of it. At that point, he didn't know what it was, so he called it X. For a variable in mathematics, so it's called X-rays, unknown rays. But he discovered another ray coming off this cathode ray when you crank up the voltage. Right. So when you crank up the voltage, there's this other ray coming off of this when you smash it into the anode. And here we go. This is the tapered anode GE, General Electric tube that's still in use today. And this is the only X-ray tube that we really have. But you can make any tube create X-rays. You just need the 100 kV realm approach, that sort of thing. So yeah, this is where
this is fascinating stuff, man. Yeah, for sure.
Yeah. I'm only on page 45 of the history of ether and electricity that you sent to me. So
Whitaker, bruh, promise you, when you're done, promise you, there won't be nobody will be able to uphold any your argument. You're gonna smash every single ether argument, anti-ether argument, down with certitude, bro.
450 more pages to go.
Certitude. Well, you could always jump in. You can fast forward to the future, a little bit, and then rewind and take your time to get up there. But you can catch up to Mickelson.
Best to know the base. Best to know the base. Got to know the base.
Yes, the fundamentals, bro. Whitaker documents all this. Just takes you by the hand, and then he will even talk about the electronic theory of matter that these guys are about to come up with after JJ with this electron discovery. This thing that we're stripping out of the material electrically with electrical tension, which seems to be subatomic. It's within the atom.
So a little bit of a side note, but when we're talking about Tesla and kind of this realm, right? Have you guys heard that Apple is coming out with a device that you can put centrally located within your home and charge through the air your phones? Like the new iPhones are going to be not just contact wireless charging, but Wi-Fi charging.
Those fuckers, they stole Teslas. I've been talking about this for I don't know how long. Seriously?
That's what I heard. I haven't confirmed anything, but if that's the case, I guarantee you it's way worse for your body than what probably Tesla was dealing with.
Yeah,
so.
I would never put one of those in my house. No, thank you, bro.
Yeah,
I think the energy output of the antennas. I would love to read about their device because there are limits. Unless they got some secret sauce cooked in there that they're not going to reveal. Yeah, don't buy one of those.
Yeah, that sounds really dangerous to me. And unlike Tesla, it's not. It's I'm sure it's in the electromagnetic spectrum. So
It's electromagnetic
problems.
Yeah, absolutely. Microwave RF. You already know microwave in your brain.
Yeah. Wow.
Yep.
How much you want to bet that they've had this for quite a while? Like they've had it for a long time. Just now.
Oh yeah.
It to us.
Shit. Montreal, where are we at, bro? Yeah, man. You took my brain off track, man, because you actually know about the Tesla race, dude. That's crazy. Not many people know about the quenched spark gap. the secret sauce comes out of the quench spark gap. Because that's
Yeah,
hard to
bro.
replicate today. Like, unless you understand what he's doing, and then you get the idea of separating the two. It's like, oh, what a genius, man. What a
Bro, I had to
genius.
listen to the thesis of what's our buddy name again? I forgot.
Dollard or who?
No, the Greek guy that did the thesis on him. What was his name?
I don't know which Greek guy.
Bill something or other. You said his name before when you said, how do you know about the spark gap? Vasilios or something or other.
Vasilatos. Jerry Vasilatos.
Yeah, Jerry Vasilatos. Yeah. So yeah.
Oh, bro,
he's the
Jerry
one that talked
Vasilatos.
about.
Jerry Vasilatos went through the Library of Congress, okay, and he photocopied the entire electrical archive, photocopied page by page in an 11-volume book called the Vril Compendium, which thank God I have all of them. That's the entire electrical history from like the 1600s. The oldest document. He just photocopied it before they moved the archive somewhere else. You can't
For
really
real,
get
huh?
your head for real, dude. Jerry Vessel, it's the Vril Compendium, he calls it. You can get it for free, I think, online.
Yeah, well, he has like they interview him, and he goes through the whole story, explains all this. I posted it many times.
Oh, for real?
Here.
I've never heard his.
Yeah.
I only read his books, man. Yeah, hit me up,
Really?
bro. Yeah.
Let me see if I can find it.
I'm
Yeah,
on
yeah, for
link
sure,
right
bro.
now. I'm gonna save it. That's my. Yep, fire up YouTube. That's what I'm watching.
Okay,
I love it.
I
Oh,
hear
I
you,
didn't
bro.
know that. Well, I read his book, so it's like, oh, I know what he's gonna say, but yeah, never heard his interview. Awesome, bro.
Yeah, somebody interviews him. Yeah, I'll find it for you. Might take me a while, but I'll find it for you
All
for
good,
sure.
all good. Wow, he talks about his X-rays, huh? Nice.
He talks about everything. He talks about everything because he did a thesis on it, right? So he goes from A to Z. He explains everything: transatlantic communication.
Yep, everything.
Everything. Yeah, the whole bit, bro. Radiant energy.
The clapping, the whatchamacallit, the telegraph, the clappers, where they would just during solar storms, they would clap by themselves at night. People would think it's haunted. When they went to the grounded circuit, where someone theorized, like, hey, instead of stringing up 2 wires, we can save half the copper. Let's stick 1 wire like into the ground, like just let's put a rod into the ground and see if we can do that, save half the copper. They're like, nah, physicists, of course, physics, like, you can't do that. No way. Stick it in the ground, lo and behold, it works just fine. And then some stations, guess what? They run, like, they wouldn't need to charge their batteries. And then some stations, for some reason, they actually ran with no batteries. They disconnected the batteries. They wouldn't need to run on batteries anymore. And with those circuits, this is the telegraph guys just experimenting. They didn't have any math to work with, just super simple. And during solar storms, the keys would just clap by themselves. And they would just play music by themselves. From the electrical activity that's induced by the sun to the earth, which are telluric currents, because these guys are grounded now, they're picking up from the earth, clapping their keys, right? Because that current from the sun, whatever, solar flares they call them, So, which was a super interesting phenomenon. And what's really interesting, when they ran on no batteries, it's like, what? Yeah, they ran on no batteries. Not all of them, but that's just like, So in some locations, I guess there was enough earth current coming up to like, okay, we can actually send a telegraph with our battery. This is nuts. So telluric currents, right? And these were the first guys that were messing with earth currents without knowing. Yeah, Jerry, really I think, talks about them. Yeah, dude, Jerry, he's amazing. This book's crazy, dude.
Yeah, he's the one that really like dug in, like you said, and really did the research. And yeah, he's like freaking James Bond, like, or like
whatever
really
he
got
says,
into it.
Yeah. If it's like fits in his book from the Vril, he's just reporting whatever he photocopied, bro, and it's absolutely true what he said from like the history that we have that people don't go dig up. And like, bro, this stuff that oh my God, man. The Vril Compendium, if you have never seen it, just look at the photocopied stuff. It's garbage quality, I know, you invest in the real stuff if you want, support Veselatos. And,
No, I don't believe you.
Yeah, dude, you gotta go dig it up, man. It's crazy.
No, I'm not going to do it.
Stuff from the 1600s or like
Not
the late
gonna do it.
1600s.
You can't make me. Fuck you, SE.
Hey, what's up, Turnip?
Hey, fuck you, Cyrus.
What up, Super Saiyan? How you doing, man?
Super Saiyan.
What's up? That's good.
Yeah, I don't know. It's just been a while since I heard you talking.
I haven't been on anywhere actually. First time on here in a
Hey,
minute. First time like
does
any
that shit have
flight server, really.
anything to do?
What?
Does that shit talking about have anything to do with the Vril Society?
No, he called it the Vril Compendium. This energy, this 0 point energy. It was also called the Vril energy. This ether we talk about is the Vril, known in classic terminology as the Vril. That's why there's a reason why he called it the Vril Compendium. It's the ether compendium in the old language of the ether that people don't know what the hell Vril is. This is why it's called the Vril Compendium of electricity, because that's what electricity is. The flow of Vril.
That I posted, that link is that the same Vril that you're talking about?
No, it's a 11-volume book series by Jerry Vaselatos. 11 volumes. At some point, I'll drop them in here if you guys have a book collection or some section. If you guys make one, an information down below, I would happily, whenever I transfer from my old computer, I'd happily drop them off. It would cost you like not an arm and a leg, but a little money. If you were to buy them, but I got them for free, so I like to share. Sharing is caring. So yeah, X-rays, man. Where were you? We had a phenomenal story going with our vacuum tubes. We took it up to the
Here you
X-rays
go, bro.
pretty quick.
Here's a present for you. Enjoy.
Thank you. Appreciate it. All right.
No worries.
Open time. 2 hours. Love it. Yes. Thanks. Nice. Yes, that is a present. Oh, man. If it was going to be like 15, 20 minutes, I was going to be so disappointed. It's like, that's it? 2 hours? Appreciate it, bro. Nice.
Yeah.
See what happens when I ask you what comes out of the metal when you heat it up, bro? This. Jerry Veselatos.
Look where we
Jerry
got to. Like,
comes out.
I'm saying, what the hell is this guy talking about? Metal glowing. I'm going, okay, I'm going to be patient. Let's see where this leads. And yeah.
I had to follow what Dollard was saying. You got to rewind time, see what happened, see the Einstein quackery. They had riots. Nobody liked what the hell you're saying. It's true. Like, what? He's trying to explain stuff away. It was just crazy. Like, what? You're insane. So
Yeah,
not all
anybody wants to
scientists
go into another world of genius is like, listen to this thing, man. Like it's fascinating. Like, how can we not have known this? It's like, put it this way. Right now we're working on Tesla 1.0. This is how Jerry puts it, right? I believe it was him that came up with that. Now, this technology, if you think what's in front of you now is genius, all this stuff, radio waves, radios, microwave, all this is Tesla, right? Well, imagine that's his old technology. What this guy's talking about is Tesla 2.0. This radiant energy stuff. Like what was it, Napalm, that said this Wi-Fi transfer of energy, like to charge your thing? Well, he had that back then, but harmless. This white glowing energy, he would call it. So you would charge, but it wouldn't harm your body. It would be like harmless. You can tune it to whatever. It's like, crazy
Jerry
stuff.
called it white fire. Jerry.
Yeah.
This is like, how old was I? I was 20 or 21 at the time when I read his book. Yeah, 21. And I devoured Jerry's book. That's when they rediscovered Dollard. Like, it was 2012 in the desert. And like the Mayans said, it was truly new beginnings. And it was a floodgate of for the first time in my life, because since I was like a kid, for some reason I believed in free energy. I believed in breaking the first law of thermodynamics, which I hope there's no globies on here because I always use it against them. And I don't believe it's ever been broken based on the concept. But there is one man, I would say, that I was actually able to tap into something else that I actually don't understand. He broke our physics. It was Mr. Tesla. However, when you get to the white fire part, when you understand what he's doing, and that's deep, it took me a minute to get up to that point. But I passed in that journey. Even after that, I really dug into the free energy. I discovered that nobody actually did anything. I would say Stanley Myers, perhaps, maybe. Murray, there's several guys that, okay, they displayed their stuff. But Tesla he really understood what was going on, and he broke like the code of nature of electromagnetism, which these two waves are bound at 90 degrees to one another, and you cannot separate them. You can snuff one out and send like with the other, okay. But to minus, like you see how it's drawn, I would have to post a graph. But to line them up to send a wave that's electric, no one can do that. But this guy did. And this opened up a new world where this white fire, this corona that he saw around his coils, this electric discharge, was not blue. And Tesla wrote about it. He was like, this is not normal electrical corona discharge, which is blue. He understood this ionized gas from in the air. So it was white, and it was harmless. It wouldn't zap you.
Yeah. As a matter of fact, he saw the two streams. He saw, like you said, a blue stream of electrons, and then he saw this white stream, and he goes, "What the heck is that?" Like it was like amazing, like a complete separation from electromagnetic energy to a complete something similar but completely different, harmless, with amazing properties. Like, yeah, that's crazy, man.
Man, I'm glad you found Vessel. I'm glad you like, dude, my dude, Vesselados, man. He's
Is it from Within the Void?
Within the Void. No, it's what's the book?
No, like, are you going to go in and explain it? Go into it and explain it.
Explain what? What exactly? The ether?
The code light. It's new plasma. Electric to electric.
Hold
on, withhold it.
Okay, the vacuum tubes of Tesla with the other Tesla rays. So in his I forgot in his notebooks, in Tesla's notebooks, you can see that, and the notes are very interesting on this. Okay, so I think I explained normal cathode, hot cathode, like emission that we operate all like vacuum tubes on. Or we heat up the cathode, so they call it boiling off electrons. So it boils off electrons to the surface, so we can pull them to the anode quicker, with lower voltage, or you know what I'm saying, with lower plate voltage, which is electrical tension, which is Faraday tubes. We're tightening the tubes between the two plates, the anode and the cathode. And from like our understanding, of course, we're going to upgrade it because we're going to subscribe to the discoverer of the electron, JJ. And he said that's the termination point of this Faraday tube between two plates. And what you're doing is you're actually ripping it out of the metal, and the electron is the terminal, is where that tube is plugged into the metal. So it's a socket. It's not a prong. So it's a socket for the Faraday tube. That's why when we look at electrons, we see a hole and we see a cloud, because it's literally a socket for the tube. So what you're going to see is a socket. You should not see a sphere. But anyways. Which confirms Mr. Thompson's ideas. So this ball with this electron, the end of the tube, we're going to strip it out of the metal, and so if we heat the metal to red hot, it lets go of this tube easier. That's it, right? So that's why they call it boiling off electrons. So it's good to understand it in their terminology, quackery, and it's good to understand it too in the way it was discovered, not their quackery of boiling off electrons. They don't a cup of electrons and stuff like that. But anyways, it's true. You can strip off the electrons easier when you heat the cathode. And so there's another mode where you can operate vacuum tubes on, which is field emission, they call it, or cold cathode mode or operation, where you just operated at higher voltages. There's advantages and disadvantages. Like any fluorescent bulb, like the long tubes, they are hot cathode. They heat up the cathode, and once you have the plasma, you don't need to heat up. It will stay high. You can, the flow will keep going as long as the current keeps on flowing, because the gas is hot enough now. It's ionized. We have a filament of gas flowing through it. But if they burn out, you can always still operate them in cold cathode, because what happened is the cathode filament burnt out, but you still have the anode and cathode intact, and it didn't leak gas. So if you were to operate it in field emission mode, you'll get light just fine. You just need high voltage, like really high voltage for that tube length, and you could make any burnt out fluorescent tube glow again, give it a second life that will last actually near forever until it loses vacuum or the envelope cracks, because you don't need the filament for anything. You just need two plates. So in cold cathode, shit doesn't burn out. But you need higher voltages. And anyways, there's advantages, disadvantages. But Tesla stuff in his notes, which were insane. He came up with vacuum tubes where he hung pendulum, like a pendulum of different materials in front of the tube, and he was able to move them with these rays he was shooting. Wood, rubber, he said, glass. He said it was able to move all material. That's after isolation, post isolation of the white fire that me and Montreal were talking about. After the isolation of the white fire, he was able to put this fire through these vacuum tubes, and it would actually impart kinetic energy on materials outside of the tube, which is super interesting. And he noted that when the cathode heated up, the anode refrigerated, and vice versa. And that's an interesting phenomenon on its own. When he operated this in field emission cold cathode, he noted that, I forgot which one for refrigerated, the anode refrigerated, I think, or one was hot, the other one refrigerated and had condensation around it. And that's just crazy on its own right there. It's like, what? Okay, that never happened to any of my tubes or any of my vacuum apparatuses. Gets hot. Everything gets hot.
It was able to attract the heat one side, kind of like magnet will attract the iron filings to it. It's like it was doing the heat that way.
Yeah, if you notice though, on the anode of regular vacuum tube, yeah, if you overload the tube, it will get red hot. His got refrigerated. Like I'll say, it's like time out. Like this flow of current refrigerated instead of heating. This is where we enter a different realm. And Tesla's notes is like, what are you playing with, bro? Like, this is not regular electricity, even though these devices are regular. When we apply our own electricity to it, we can't get these phenomena. It just doesn't work. But Dollard was able to replicate stuff, so proved it.
Yeah, so imagine a city where you have one big, huge tower at the center, kind of like the tallest building, let's say, in the city, and that is broadcasting that white light energy that we were talking about, separated from the electromagnetic energy, which is safe. And imagine now everything you have, car, lawnmower, electric razor, shaver, whatever, a weed whacker, all drawing from that, all cars, all motorcycles, everything.
Like that big tower in the middle of that tower in the middle of that city.
Yep.
The wires running from it, yet there's antennas on all the buildings.
Exactly. Not a wire. Wires are, forget about wires. Wires are non-existent. There's no such thing as wires. You don't got to plug in anything. Any light in your house, heaters, anything that you have, radios, TVs, your your joystick, everything runs like Wi-Fi, but safely. That's what Tesla wanted to do. But of course, JP Morgan couldn't have that, right? He told him, if we can't put a meter on it, I don't want it. And he cut all funding. So that was the end of Tesla. He couldn't borrow a dime from any bank. They blacklisted him.
So do you big brain guys understand how Tesla caused his body to glow?
What?
How Tesla.
Yes and no. Yeah, we've heard, like, sure, but like that's why he was known as a magician. Like nobody can do it. You hook up your body to a transformer equivalent of what like they said he used, you know, you go into the grave. So yeah, he did it, but again, that's why he was a magician. He did it on stage. I forgot where. Where he held up, you know, he brought up an apparatus, held up a wire.
Oh, I
His
think I
body
know what
glowed.
she's talking about.
It glowed like a
What they used
neon.
to
He had a
do.
discharge around his body, and he was like, "Here, these are the dangers of alternating current." And he just walked off.
Oh, that. Oh, okay. Because he used to do another trick. He used to put a light bulb in his mouth and one on each hand, and he would turn on the generator and he would light it. And then when it would light without wires, and he would freak people out. I thought she was talking about that. Yeah.
Nah. Yeah, that's why he would do this sort of things. Like he was on that level. He was on that level. In
That's why he had to go.
1900, right? Like that's crazy.
That's why he had to go.
He left us his stuff. Just, I mean, I guess we have to read it like the way Tesla thinks of it, not the way we think of it.
Check
You
that
don't need
picture out.
you don't need electrons for his work. Nice.
Check that out. Imagine back then you see something like that. Somebody holding a tube in his hand and it lights without any wires.
Yep. And there's a wonderful transmitter right behind that curtain, of course.
Yeah.
Of course. Because it's 1890, or I don't know when was that pic taken, right? You can tell. But then he
1890s, yeah.
Oh, he lit up a field, right? Later on, right? Where you can just stick the light bulb in the ground, yeah?
Yeah, that's right. Yep.
Well, this guy was a magician. He was known as a magician. And people dug up the ground. Oh, he had wires in there. No, he had no wires. So the telluric current discovery, right? That's where he gets into his own nose. I think Colorado Springs, where he said he sent electric wave modulated at 50 kilohertz into the Earth. Electric, of course. Now we understand. You got to catch up to speed, because you do it today, it's not going to do anything. Because how do you transmit to the Earth? And this is where it was. I don't know, man. It was just my world stopped when I read that, like from Veslada's word from work and Dollard's lectures, where the Tesla coil, the tertiary coil, the purpose of that coil, it's not to create fucking sparks, is to push off of a virtual ground to be able to transmit into the Earth, the monopolar transmission, which is not achievable because it's just one end of the wire. Where do you stick the other? You stick two ends of the wire into the Earth, or would you just use it? Or are you just going to transmit like radio? No. We want to transmit electricity with one rod into the Earth. How do we do that? We have to push off of a ground. Where's our ground? If we use the ground as the ground. So this dude, wizard, his coil, according to him, has to be square in dimensions, by the way, in like aspect ratio, according to Tesla. And he tuned it with the mass of the copper. And he tuned it to the fourth harmonic, which is madness. I don't know how this dude is crazy, but anyways, with light bulbs, bro, without oscilloscopes, like, oh my god, okay, fine. But he said he tuned it to the natural frequency of Earth, thus creating an Earth-like ground for the coil, so you can actually transmit from the end wire, your ground wire, into the Earth, and pick it up from the other side into anywhere around. And this is what Tesla. Dollar displayed this on video in '87 or whatever. Just replicated.
I was just gonna say that, bro.
Easy,
yeah.
There's another guy.
There's
another dude recently. Yeah. Have you seen the other guy?
One,
like,
right?
there's a follower of Dollar, that has got another video up on YouTube. So there's another one that like proved this again with a radio on the beach. What Dollar is saying is correct, where you can make your physics teachers just lose their minds, walk up like MIT professor. He'll be like, hey, bro, Faraday cage, right? What if I pick up radio signals through the Faraday cage? How much money would you give me? You're about to become a millionaire if you know this trick, right? Because I'd be like, I can transmit through a Faraday cage. Can you? He'd be like, it's impossible to transmit through a Faraday cage. And you just demonstrate it, and you take your $1 million and you walk away. Because you're going to transmit through the Earth.
through the ground.
Through the cage, through the ground. Like, yeah, of course.
Yeah.
Thanks.
Hey, he caught China, by the way. I think Dollard caught China from where Marconi. I think it was in the coast of Canada. Yeah, I think it was in the east coast of Canada. Or was he in Europe? Where was it? You remember where? I think he was in Canada, right?
Marconi?
When he did that Earth transmission thing?
Who?
Dollard.
Dollard. He was in Bolinas, California, if I'm not mistaken.
Polymath.
Didn't he
Yeah.
do one where Marconi was?
Yeah, that's the RCA installment, Bolinas, California.
Yeah.
That video that you're talking about, or at least I've seen a conglomeration of videos where they're going around and basically getting radio transmissions from the ground, and then he's walking around a lot of that old facility there, the Marconi building and all that. Yeah.
Antenna field.
That's in California?
Correct. Yep. On the fault, on San Andreas fault, if I'm not mistaken. It's right
Yeah,
there.
you can Google RCA Beach is what it's called, and it's right in that area. You can still kind of see it on Google Earth, the remnants of the antenna field.
RCA allowed Dollard because he was up in there to live on there pretty much, even though after RCA got dismantled, until the sheriff it's an enormous antenna field. I don't know how many acres, just enormous. And after he found him to tell him there will be no more electrical research done on this property, Mr. Dollard. It's understood. I was like, wow. So even after the RCA had no problem, it was the Commonweal that took it over, the company, Rockefeller Company. So EPA backed and all that. So you can actually, that's the problem. Stuff he talks about, you just move your fingers on the keyboard and actually try to reach out to these people. I actually find them. Or it gets weird. And then oh man, Dollard, dude. Could only imagine if he was just given the freedom, not messed with, what he could have invented for us. Because he's pretty smart.
Yeah, this dude, man. If what he says is true, bro, this guy was genius plus, right? Now he claims he was able to visualize a machine, right?
Bearing wear. Yeah, I know what you're talking about. Go ahead. Go ahead. Yeah. This is reported by many, bro. This is reported by many people. It's great. Matt can run him through it, bro. I can't even talk about it. Too excited.
I know, it's crazy. Yeah, he was able to picture a 3D diagram now in the air, right? Like you see in the Star Trek movies, right? Okay, Captain, bring up the engine is broken, and they bring a thing up, right? Well, he's able to bring an engine up like that in his brain in 3D, walk around, move parts, change things, and then, okay, play, make it work, and then come back a month later and see if any parts wore and what broke and this and that. That's what he claims, bro. I mean, it's insane, but that's what he claims.
That's the claim. He can calculate bearing wear of a running motor in his head. That's insanity. If I don't know, man. If he can actually do that, you know what? I can't doubt him because I'm looking at my outlet right now, and it's all Tesla. His patents never changed the entire system. So, and it's his old stuff. He didn't want it to run on 60 hertz. It's garbage. He's like, well, this is just fundamentals. It's meant to run on way higher frequency. And if you look at military devices, alternating current devices, you will see that they do run on high frequency, 400, 600 hertz, 800 hertz, for a reason. They understand. So they apply the Tesla, at least basic alternating current technology. And in his own writing, he said, I have moved beyond radio, and this is not verbatim, but super close. I've moved beyond radio and alternating currents. And I to try to understand this new phenomena that he discovered of electricity, a new form of electricity, he said. Not alternating, not direct. Neither nor. And this is where the marvelous story begins.
He named it. He named it. It's called radiant energy.
Yeah. That's what he called it.
He also called it, what did he call it? Ether flow. I also heard that name, ether flow. But definitely radiant energy, talked about it all the time. I'm sure. Tell me, have you heard? Because he also talks about radiant energy coming from the sun and from
Correct.
space. Are you aware?
Correct.
You're aware of that,
Correct.
right?
Yes, of course. And if you build his radiant energy patent and you replicate it, you are not going to get usable energy out of it. So because his patent, which is so fundamental, is to actually capture radiant energy that you're transmitting, which is this one-way isolated electrical current that we're talking about, which would be like the way Dollard, because Dollard carries the math forward, and he calls it direct longitudinal dielectric
transverse waves, I think. Yeah, something like that.
That's the transverse is the electromagnetic. The other one is a longitudinal electric wave, really. So it's like an electric, not electromagnetic. There's no magnetic component. We snuffed that out.
There's no electric here. Yeah. I mean,
pure electric.
Yeah, there's no electric magnetic component, right?
Yeah, we've snuffed the magnetic through the spark gap, and we're transmitting on purely electric. So it's not electrostatic, because that's what happens if you snuff like magnetism. Then you're talking about static electricity. No, we're talking about snuffing the magnetism and using another mode of electrical configuration of the fabric, which is electric configuration.
So you're
That's
not
the better way of understanding it.
You're not producing electricity, it's dielectric current.
Well, dielectric is the same as electric. I use the same there. So magnetic. The other tubes of force are electric or dielectric. Same.
Dielectric, yeah.
They're the same word, yeah. If you use electricity, go ahead.
I was gonna say he explained it like a radiant, like a gas sort of like a. I heard it explained like, I think, was it the Vacillados that explained it, like sort of like a gas expanding kind of a thing. It's weird, man. It's not it's not electricity. It's a whole different. Yeah.
It kind of drills through the air, sort of thing. This Tesla stuff that he's talking about, where it's actually not through the air. It's like it's a different mode. Where that's why I highly recommend Steinmetz. What is it? Alternating currents, or I have to pull up the exact title, but Steinmetz is the mathematician that wrote the curriculum for the electromagnetic curriculum that's taught today in all universities. So Steinmetz is the last guy to refine it. Then Dollard tried to refine that, and this is it today. That's all we have. But Steinmetz, he covers the 8 forms of electricity that I talk about, because this is where you get an understanding, because he was hired by GE. He was brought in by GE because they were replicating Tesla's stuff, trying to get around his patents, and everything was burning up. The Westinghouse stuff was fine. Tesla, but GE's,
right.
GE was just burning up. So, which was backed by Morgan and Edison, right? So that they start recruiting brains from outside of the U.S. who can solve this right here, and of course Steinmetz figures it out.
He was the only one. Yeah, he was the only one.
Why the motors are burning up? Why the transformers are burning up? And why is everything blowing up when we try to disconnect it? Those were all different reasons. And he just writes the entire career. He gets it, man. Steinmetz is just he just summarized oh no, this is there's other parasitic forms of electricity that hop onto the grid, and our meters cannot see them because they're transient. They are transient waves. They go transient, which means in physics, changes with respect to time. But here it's not just changing with respect to time, it's changing with respect to space, where it just goes in and out of space, appears, shoop, destroys everything, gone. It's are you serious? And they would just do this over and over with the GE guys until Steinmetz, cracks onto it. And it's these pure parasitic loads that we didn't know about. And we had to build stuff to snuff it out, because it would hop onto the grid, especially when you open the switch. When you open the switch, all disaster happens. Everything is fine when everything is running. When you try to disconnect it while there's a load, while the city is running.
Yeah.
When you disconnect the circuit, when you pull it apart, because the magnetic.
That's the problem.
It has to go. Yeah, exactly. It collapses the induction, so it's going to induce a lot of current back into the wire, which it does, and it will just bridge the gap. But back in the days, they used to do something phenomenal after bridging the gap. So this arc then would expand, would grow, would grow, would grow, would grow, and it would go in and just blast the whole substation, killing a lot of
People
people.
would die. Yeah, people would get
Killing
like
a lot of people.
zapped. Yeah.
People have died. Like it was the Manhattan railway something. You can pull up the newspaper articles on it where the railroad jumped up in the air 3 feet. Okay, from the explosion, from the blast. The earth moved 3 feet up. It was severe. The blast was just madness, and yeah, you can read the newspaper articles on it. It was like the Manhattan Railway, some explosion or something like that. It was the electrical age guys trying to cheat Tesla, copy his stuff, and it wasn't happening. So Steinmetz
If
figures
it
it out.
wasn't for Steinmetz, we would have never had this because Tesla gave him the finger and walked away. Yeah.
Let me grab the book of Steinmetz that I highly recommend for the deep etheric electrical researchers to read first, because that one really, like, when I tell you about Tesla discovered a new form of electricity, people will think, oh, you're mad. Okay, go read the guy that made the curriculum that's taught in unis. If you ever spoke to an electrical engineer, or go look up the curriculum from MIT or whatever your favorite college is, and see the equations, and actually go back in history, because they're going to attribute someone else most of the time. But Steinmetz, they don't mess around with them. They have stuff named
This
after
guy
him.
was another genius. There's no question
Another
about
level.
it.
Another level.
Yeah.
So yeah, Steinmetz is he wrote the entire curriculum on this stuff. Let me grab you the book title. So that's the one that will cover the eight types of electricity. And I like to say it this way for a specific reason, because it's like quadrupolar in nature. Electricity. So it's where the mathematics, when you refine it, because you are dealing with invisible stuff. So we are going to need heavy mathematical modeling to represent the stuff that we really can't see. Otherwise, you're really lost, and we'll try to engineer something out of it. And this is where Steinmetz really takes Maxwell's stuff, which was already refined by Heaviside, to make it engineerable into algebra for the common engineer. Steinmetz took that, and with the newly understood stuff about alternating currents and all that, and he refined that one more time, giving us what we have today about like electrical equations and all that. All Steinmetz. They'll tell you it's Maxwell's. Ha ha ha! Go open up Maxwell's paper. The equation is 20 pages long. Tell them which part of this equation is this? They're lying. It's not Maxwell's. Maxwell's stuff is so thick. It's like he doesn't have simple equation. What? Doesn't have algebraic equations. Like, you're crazy. This is Oliver Heaviside's equation, which was further refined by Steinmetz. So we'll see. Depends on the equation, but these are the two guys that give us the math that we have today. Not Heaviside, not Maxwell. Maxwell is the grandfather that came up with this phenomenal stuff using calculus, and it's just his math is too thick, and these guys refine his math for us, so the common average Joe can understand it. Really.
Are you gonna post it, or is that the right one? When you were talking
No,
about
I'm just gonna post the title of it. I'm looking for it right now. I do have it. It's on my other computer though. It's just a hassle to go and grab it and drop the PDF. You might be able to find it on archive.org, maybe not. Let me just
What's
see the
the
list
name
of
of it?
That's what I'm trying to get right now. Do
Name
this.
of it.
I'm not a robot. Think first.
Not yet. Anyway.
It was one had I think it was alternating currents, impulses, and discharges, something like that. That's the one I'm looking for. That's the one I highly recommend first.
Electrical impulses and waves. CP time is that what you're talking about?
Is that the one? That's what it's called? Yeah, it's called. I'm sorry. Yeah.
I think so. Yeah.
Yeah. If you got it, post it. That's the one. Yeah.
Yeah. Let me
I
pull
think
it up.
it's like electrical waves, discharges, and other phenomena, maybe, or not. No. Let me see. Yeah. Wait, I got it. Electrical discharges, waves, and impulses. That's what it's called. CP standards. Highly recommend that.
I'm sure we bored everybody to death with this stuff.
I know,
Anybody wants
man.
to change the subject, go ahead.
I can
No,
trigger
it's just
people. Let's talk about electrons or photons.
I'm not bored.
Yeah, I was just getting ready to say, no, is class over? It's go
There's
for
no.
I'm still listening, man.
I'm just
It
spilling
is
just
funny,
stuff to references, not class. Or just go check these guys out. Really, CP's time. That's all I'm saying. Read the book and you'll understand this 8. So you'll have like on his book for alternating currents. So you have impulses, right? And that's what we operate on. Like the electricity form in our bodies are not direct, nor are they alternating. They're impulse electricity, and they set sets of impulses in like a train of impulses. That's where the coding is in, but it's just a set of impulses. And nature that's the type that's like in plants and humans and animals. So the electricity that we have it's not AC or DC. It's impulse actually that runs through our nervous system. It's impulse electricity. It's absolutely electricity.
Sorry.
We know this. It operates everything. Nervous
My
system,
bad.
like from A to Z. What's up?
I bet Dyslow. Dyslow is trying to get in. I'd like to hear
Oh, I
you and
didn't
him
hear.
go back and forth for a while, like, because he's understands this enough to hold an intellectual conversation with you better than I can, and maybe some others. But I really enjoyed listening to it. So he was trying
Sure,
to get in
yeah.
there and say that he
Hop in,
wasn't
man.
bored either. I talked all over him.
Yeah, no, I was just saying I enjoy the topic. I mean, don't feel like you're boring me at all.
I thought we were like maybe boring some people. That's why I said maybe, but yeah, I'm fascinated by this stuff.
Yeah, man. I mean, if you guys aren't bored, we can keep hammering the same subject to understand like electrons, photons, protons. You have to
Yeah, I had a
understand
question. I had a
where
question,
these
right?
guys came from. Hit it, bro. Go for it.
Yeah. So earlier you talked about the electron, right? And JJ calling it basically the terminal, right? Or the terminal end of one unit of dielectric induction, and you referred to it as like a socket. And you're also talking about like within certain effects, like dislodging electrons or something like that. Like how would you kind of like visually explain the dislodging of a socket or a terminal from something? Like what is the nitty gritty of
Easy. Fucking easy. And it's gonna the way I take it, because it'll tell you can measure the mass of the electron. Done. Yes, we know why, based on what Thompson was saying. Because that's what we're saying. Okay, so we have in nature, just scrap the tube for a second. We'll just talk about the electromagnetic wave, or electromagnetism in general. So let me post the diagram. So this is from all common physics books. Like mainstream is down with this. They don't deny this. So let me post it first. Let me grab it. Just a basic diagram to see that they're orthogonal to each other in nature, and we understand that. And they're not just orthogonal; they're orthogonal and the antithesis of one another, which makes it elusive in nature.
Are you going to post the diagram from the book you were just talking about? The
Nah,
electrical
man.
by C.P.
Post
Steinmetz?
it. Go ahead, post it. Yeah, if you got it. No, I
Is
was
that,
just gonna
is that what
post
you're
this
talking about?
basic. Yes. That he talks about the. Where's your diagram at? He talks about the 8 waves, 8
I don't
waveforms.
know, bro. I'm on my phone just spitballing shit. I don't have this stuff at my fingertips.
Oh, I'll post it for you, but give me a second. Yeah, sure, I'll grab it for you if you want. But right now, it's like I'm just describing this fabric that's kind of like just out there, and that's what we're transmitting whenever we're talking about electromagnetic waves. So we're talking with this shit right now, and Wi-Fi, whatever, cell phone is just different frequency of this sinusoidal wave, which, as you can see here, so like the yellow part is the magnetic part, okay? The blue part is the electric part. That's why they call it the electromagnetic wave. Okay. And of course, we can use photonic symbolism for this too, because it's okay. They go together hand in hand. You don't have to separate the two. Don't matter. But we don't need photons here. We're just talking about these tubes of force. These like magnetic fibers and electric fibers. There's 2 sets of fibers. And these fibers are always arranged in nature in like 90 degrees. Okay, they're 90 degrees to each other, these when they cross. And the crossing of the fiber is the photon or the electron, because this is where things appear. But this is what is like the Planck, or we call it like a quanta, because that's this nodes of energy, these photons, they happen in discrete steps. That's why they have quanta or like steps specific. Like there's exact places where it happens and places where it doesn't. So that's why they say it happens in like packets of energy, because it's in quanta. That's what we mean by quanta. That these fibers, they have absolute position in space. There's a place there is a fiber. There is a place where there is no fiber, and each crossing of the fiber is this one quanta. Okay, and this is classic electromagnetism before we even like electron pull it out. We're not pulling electrons out yet, really. That's the understanding, is that we need to understand that there's just 2 in nature. It's not just magnetic. There's an electric one too, and we use that to pull the plates in the vacuum tube. That's what's called electrical tension. It's just voltage between the anode and cathode in the vacuum tube. And because you have no flow at that point, you just have potential. There's no actually current flowing between the plates when you're just pulling. So the theory is that these electrical line tubes, which are linear in nature, and according to Thomson, because now he's going to strip it out of the metal, he's the guy that notices this is the electron. So because it's a terminal, my understanding, which is to Thomson's, right? Because we can take it to like Narnia later with his ideas. But this tube is terminated in the middle, or in the in the matrix of the material in nature. Okay, so like, you know how they say, you got these shells, electrons and protons and whatnot. So this tube is not just on the surface, it's actually in the fabric of the material. So when you pull it out electrically, and you can do this electrically, when you strip it out, it will take a piece out, where the socket, it will pull out the socket because it's like sewed in there. So it's like when you pull it out, it dislodges a piece of the metal. And this is where like this mass comes from, right? So this is the electron in nature, is that when you strip it out, you actually broke the other end. And that's what you're accelerating. You're accelerating this bungee, right? Because you broke it from one side, and it absolutely has a direction of flow, and it has charge. These electrons, absolutely negative, the charge, because you can deflect them with the magnetic field. So because you can deflect them, we know they have charge. So I was like, and the CRT comes out of this, right? We can make an image out of this fucking concept here. So they absolutely have charge, and the polarity is that which have assigned to the negative terminal. So you can, take the negative positive as like acidic alkaline. I don't care, as long as you give me the conversion factor to your lingo and which terminal to hook up on my battery, I'm cool. And I'll give it the equivalent of negative positive. They're just poles, plus minus, So it definitely has a negative charge on it. These electrons, or whatever the hell this guy's about to strip out of the metal by tensioning the tube. So his understanding is you broke it out of the metal. you've taken an electron from the metal. That's why these guys call it also boiling off electrons. But they want you to think that these balls bouncing off the surface and entering the metal, and bouncing off the surface and entering the metal, and they're literally boiling off into a cloud around the metal. We don't think of such ball bearings. We think of them as ends of our tube, especially when they exist in an electrical apparatus. And from this electrical apparatus comes out the electron-proton stuff, okay? So we're going to stick with the founders here, and we're not going to go with the crazy guys that they think they're just balls dancing. We're going to go with the guy with the tubes, because he doesn't think they're balls dancing, right? But after you break the wire, oh yeah, you have this little thing that's not a really thing, because it's a tube, and you broke the attachment point. So you're going to have like particles, so pieces of the socket where it was attached, flying at the end of the bungee of the rubber band. So if you just imagine between the plates, you got rubber bands, and as you crank up the voltage, crank it up, all you're doing, the bands aren't moving from
the
place.
tension.
They're just
like moving.
There's increasing in tension, right?
It's kind of like visualizing them moving apart, which is increasing the tension on the rubber bands, and eventually one will break loose, taking a portion, right, of the plate with it. Even though the bands are technically massless, the mass that it would get gained is from the broken
glue.
Yeah,
the glue that you glued the band with on the plate. Essentially,
so this
is their atomic glue or whatever the hell,
This makes Dollard's explanation of it, being a broken loose, hold fast is what he called it.
Well, the thing is, like with the quanta in nature, we know that there's no line that can exist free-ended in nature. No such thing. The magnetic ones are always, they form loops enclosing on themselves into the magnet or the iron or whatever the magnetic substrate is, and the other ones terminate from conductor to conductor. You can't have a wire with no terminals where it's plugged. You just don't have a free wire in space. Here's a tube of force floating. There's no such thing. It's always attached to something and something else.
Gotcha.
Anyways, yeah,
It's
that's
all about what it's attached to, so you can.
Well,
change
this
its
is
attachment.
We're trying to understand the electron. So when we get to the photon, like we have to pick at which level to deny their shit and at which level we accept. And we agree with the concept mathematics. Yep, cool, matches, no problem. Right? But there's stuff where you dismiss. But you cannot dismiss where when we shoot electrons, whatever those are, when we shoot these broken tubes that are moving pretty fast after we break them, they excite phosphor at the other end. And then Mr. Rentgen is going to accelerate them pretty fast and discover they're going to go through solid objects. Shit. He's going to put stuff in between. It's still going to excite the phosphor plate. He's going to put his hand in between. That's how you get the handprint, right? On the bones, your bones, these are X-rays. They go through actually material.
So it would allude to it not being necessarily a particle, right? But something that was already there on the other side to begin with. It was just broken on one end and terminated on the other.
Right. The way these guys understand it now, this ball, this sphere that you've stripped off and you accelerated towards the anode, hits the anode, breaks, I think, electron into sub-electron, and from that you're gonna get like secondary electrons. You're gonna get different emissions for sure, absolutely. Part of that, you're gonna get X-rays spit out of the tube, right? But Tesla differs on what these X-rays are and stuff like that. But we get these X-rays. Essentially, all the X-rays we do today is grab some electrons and you get the stream flowing pretty fast with higher voltage between the plates. You get them fast enough. When they smash any anode, they'll create X-rays. Any tube can create X-rays. Just crank up voltage. Any tube. It's all speed. Literally, X-rays equals speed of electrons. Speed plus smash, you get X-ray. So you use the speed, the electrical speed or the electrical tension field to just accelerate the hell out of these things and just smash it into the anode. And once you smash it into the anode, interesting phenomena happens. You have the secondary emission, right, of these X-rays. Like, boom. So you shot electron. Now you have X-rays, and you have other emissions too besides X-rays coming off of the anode. And now, like, what are these? Are these little spheres too? Like, are these pieces of the metal? I would say absolutely not, because if there was any mass to the electrons contained within the glass, so whatever gets spit out the glass has to be massless by common sense, unless we can measure that the cathode loses mass. And if it doesn't, then we're not losing mass, and all the mass is contained within the glass. So all this stuff is massless that exits the tube, and this is the problem with physics. Physics is the domain where deals with the study of the physical world, physics, so you need mass, as one of the units in physics, in kilograms. So if you cannot attribute mass to it, you really can't really study it. It shouldn't be in physics. It should not be the domain in physics domain. So electricity is outside of physics domain because it's not physical, it's metaphysical. It does not have mass. But they have to attribute mass to it's physics, ball bearing flowing in a wire. No, we know why we have the ball bearing effect flowing in a wire, but there's no ball bearing flowing in a wire.
But it has an effect on the physical, right?
Of course, because we know the tube is terminated in a ball bearing. There's the electron. So when we flow the tubes down in the circuit, when we bind the circuit, we get a flow of this grid. So when the tubes scratch the wire, they actually heat it, right? So not just heat it, and you get this apparent effect of flow of electrons in the wire. Because the tube is actually, the energy is outside of, it's in the field contained by the conductor or the reflector. It's reflecting the electricity back on itself.
I posted the image of the field of an electrical circuit from CP.
Would the image, would it necessarily need to come off of the plate though? You mentioned like weighing the plate and see if, or seeing if the plate lost mass. But would it necessarily have to be from the plate?
So,
and vibrate like at a high enough frequency?
DC, we're using direct current here. We're not using alternating. One way. So vibration, so this is where I'm saying you're going to use vibration is a sinusoidal wave. Whenever you're going to talk about something like a vibration, there's a positive negative cycle to it. With what we're doing here with the cathode ray, electron gun, X-rays, we're doing it one way, as in it's DC between the plate, the two plates, direct current from one way here and to the other. We're not allowing the current to flow the other way. We want them to only flow one way, so we use direct current. Yeah,
the Rayleigh wave, not the transverse.
No, not really. No, just like here, I got you. DC versus AC amplitude. Here, I got you. Basic.
The question that I have
engineering mind, so I like graphs. If you can't graph it, I say I can't understand it in engineering. I remember that's what I used to say. But so if I can't graph it for you, I suck as a teacher. So it's like, hold on, let me get you a graph of what this means, what we mean by direct current versus alternating current.
My question is if matter, like if there's matter detected or more of a mass pulled off of something, does it necessarily need to be pulled off of something? Would it just be matter coalescing from the ether?
Well, that's you went in too deep, I think. That's the problem. Like you're trying to understand what's going on now, but we're just like kind of recording phenomena right now, and like keeping it at what the hell are we spinning out of the cathode sort of thing, which is electron. And if we understand what are we spinning out of the cathode, like we can like move forward.
Okay, yeah, I'm just listening and learning, but I will have questions, from time to time. I'm not trying to derail the convo, so that's cool.
Oh, you're cool. Okay, give me a minute.
But would it necessarily have to come off the plate, though? I mean, I think that was just I guess it would have to at this point.
So, this is the problem with running too fast. Like, just kind of, this stuff is easier to go visually and see the devices and see how, like, what we're talking about theoretically with the fabric, and then when we take this fabric and we put in a vacuum tube in the circuit, right? This is where all these ideas come from, because this electron that's flowing off now, that you can measure the speed of and all that, it's like they think it's in the wire and it's like getting spit out of the wire, right? So that's what they think, it's already flowing in the wire, which is absolutely not true, because then your socket would be spilling out electrons out of the cut end of the wire. But the reason it doesn't do that, because you don't have enough electrical tension between you and it to pull electrons off to you and shoot you with electrons. It just doesn't happen. So that's where you can smash their theory with basic understanding of electricity, where, well, in the wire, we have the apparent effect of electron flow. We understand that. But because they also understand that the energy flows outside the wire. So it's like, hey, guys, don't fuck with us here. We're basic fundamentalists of J.J. Thomson and these guys. Like, relax. No, what they're saying is correct, because this is where everybody else built their ideas from. So we need to understand the super fundamentals and not deviate like they did with their ideas, because they kind of deviated too far. But out of this, we're going to get now the table of elements with, like, yeah, we're gonna get a lot of knowledge out of this electron here. So it's a great place to look into, like, in the history of science, what happened here. It's not everybody agreed what's going on, right? They disputed.
But wouldn't, oh, okay, so alternating current, it's just got a larger wave, right? Wouldn't a direct current also have little tiny, just like tighter, and they're smaller, it's higher intensity?
Where? Look, I posted a diagram explaining
know,
DC and
but-
AC. So where's the wave here?
So there's no vibration.
It's not cycling, so it's not a wave.
Okay.
Can't say you're sending a wave because it's not a sinusoidal. What kind of, like, wait, direct wave? Okay, direct. It's not a wave then.
No.
That's why we call it direct current.
Right. It's just like hard to. Yeah. Okay.
Would you say it's the difference between, like, two people standing apart from one another in their one hand they have a rope, the other hand they have a rod? You move your hand up and down with the rope, and then a sinusoidal wave travels through that rope and then reaches the other person. Whereas when they have that rod, the minute or pretty much instantaneously, you can push that rod and it's going to be impacted on the other person's hand kind of immediately. Is that kind of the same kind of concept?
Yeah, that's the difference between, like, the wave types. But this is more of a current. We're talking about how the current is just it's just measurements of, okay, so
Sympathetic
alternating
triune streams. Is that what that is?
No, we have to understand where the sine wave comes from, because it's a geometric thing of the circle, right? It's literally like all it is. Like, if I was to plug in my oscilloscope in the wall right now and slow down time and capture, and just because it's happening 60 times per second, I can tell you where the shaft position is down the station, down the generator, hundreds of miles away, whatever. That's exactly what that is. That's the speed, the RPMs of the generator down the line. That the 60 cycles is 3,600 RPMs that the shaft speed is held at. If we bump up something like more gas, more oxygen flow, more fuel into the turbine, and we crank it up to, like, twice that, you're going to get 120 cycles per second out of your wall, because it's just cycles of the shaft. So the shaft, you have to understand, you're going through a positive cycle and a negative cycle of the circle about the shaft, and that's all we're doing. That's all the sinusoidal wave is. So that's what your meter will read, because at some point you'll get the flow will be from, like, positive, negative, then it'll flip-flop on you in the trough, and the other cycle will be negative, positive. So it, like, vibrates back and forth. It alternates 60 times per second.
Alternating the polarity. So would this direct be just a single polarity?
Direct, yes. When you just go from positive, negative, and you're not alternating the direction that you're going back and not, just like batteries, essentially. Yeah. You can take, of course, an alternating current and rectify it. They call it rectifiers and all that, blah, blah, blah. But just basic, keeping it super basic. So it's not complex. So that's why I'm saying in that tube phenomenon with the electron and all that, we're not using AC currents. We're using DC. So you don't have to, if you throw in vibration, then right now it's still confusion, but vibration and the morphology, when you go like electronic, subelectronic, then of course it will help you out. Then your quarks and stuff like that. Then your quantum mechanics and you know, you believe in Narnia, so you know, quarks, fermions, and good stuff. But anyways, where are we at? Let me know when shit gets boring.
Polarity. You're going. Oh, that's what I remember last. Maybe that's not where you were.
X-rays. Talk about X-rays.
Yeah,
I think
X-rays.
I was telling you that in that tube.
So what's the
we're
where's
using
the
DC.
phosphorus coming from? Is it coming from the ether, or is it coming?
No, it's a
from the
coating.
energy, or
No, it's just a little screen we put at the end of the tube. Little screen.
Okay.
Here, so okay, so we'll go. Okay. Again, so copy image. So this is the cathode ray tube, the CRT. This is the the Crookes tube, and JJ is what let me show you JJ's. Primitive, but I mean it's the same thing. So we understand. Nobel Prize winner we was playing around with. So okay, so this ray of stuff, when it hits that screen in there, that screen has got a phosphor coating to give you visible light to your eye, because you can't see this stuff in the tube as it flows to the screen. And you can deflect it with magnetic fields. So you can steer it. You can steer the beam left, right, up, down. Just this is where you get the TV, right? This is the same tube and like TVs and monitors up to like LCDs and stuff like that. It's that little glass device improved.
What was it about this that made them stop electrical research? Was it cracking open the ether, or something else?
It's like there's the energy aspect with Philo and his fuser. Then yeah, it was pretty much the energy essentially. You take this down where the road tubes were going at that point was for fusion energy, which is to make essentially free energy using the acceleration of these beams to try to get it out of like the nucleus of the material using a fuel. And yeah, of course, and not Philo's way, but because Philo was pretty smart. But yeah, these guys spent a lot of money, trillions of dollars or billions of dollars in their laboratories, and because they didn't subscribe to what he was saying. Yeah, they spent a lot of money to really go nowhere. Which is essentially trying to make the sun in a bottle. The fusion reaction, they think it's happening on the sun.
Well, if they could produce the code light that Tesla did, then they could probably, something similar, perhaps.
Yeah, that opens up in Dollard is the only one that really experimented with that, and just it's everybody's got different interests, but yeah, maybe there's a lot more to it. To like use Tesla currents with these devices that really nobody does. We just use DC. Some stuff runs on AC, some tubes and whatnot, but yeah. From like Steinmetz and all that, from the understanding you pick up from these guys, absolutely 100%. And then counter space and stuff. I don't like to introduce that unless presenting the math behind it. And this is where it's like, okay, it gets into real presentation times, like because to grasp the concept. What's up? Oh no, I know it's terrible. Don't say that.
Don't say counter space, man.
Counter space, man. I love counter space. Phenomenal concept.
Yeah, that's where my coffee maker sits.
And the square root of -1.
Cyrus is
You
an
know what I'm saying?
expert in all types of counter space.
I like counter space. It's great.
Yeah. I
built
literally had somebody at
countertops.
my house using
countertops.
I had somebody at my house today using a laser to measure for new countertops. So
How many times have you
Nice.
measured countertop? And how many times have you counted counter space, Cyrus?
A lot, quite a bit. I do it for a living. Part of my daily. I change a lot of kitchen counter space quite a bit, quite often.
what would your best explanation though of not countertops and what we're joking about, but what if you could give an elevator speech of counter space, what would it be?
Oh, it's so easy to understand once you understand like magnetism. Okay, so electricity. The owl. I'll copy your diagram. The Steinmetz diagram that you posted. Here we go. The owl. I call the owl, which is the electric field. This is the best place, especially if I do a 3-dimensional drawing of this. But all you have to do is take this into your head and do an isometric view, if you know what that is. Which is this is a cross section of an electrified circuit. So you see these black spots. The pupils of the owl. Those are conductors, copper conductors, cut, and we're looking down the conductor. That's why we call it cross section, right? So see this C section. So we're looking at a cross section of an electrified field. Like imagine this is like
two power lines, but the black spots are the power lines, like you're looking down them.
Yeah, and at the other end you have a light bulb. Let's say, okay, just to keep it simple. You got a light bulb at the other end that you can't see is too far, and behind you, as you're looking staring at the image, so behind your head, the observer is like the battery, okay? And you got positive on the right, negative on the left, okay? Whatever. It's just terminals of the battery to complete the circuit. And this is a view of the completed circuit snapshot in time. We just take a slice out of time, and we're looking at just a very simple 2D, extremely thin section that we could never see in life. It's always multiple fibers, but this is like a theoretical section of just with single fibers, right? So we can understand how they're lined up. So the concentric circles around the owl's eyes, right, around the conductors, these are the magnetic lines of force, and that's what the kind of fabric they emit when you have electrical flow down the line. Because I have to explain to you this, out of a battery, you have no magnetism in the battery. There are no magnets, no magnetic storage whatsoever inside of a battery. But when you have when this fabric essentially starts to flow, it gives a rise to magnetism. Okay, so these circular lines of force, if you were to put a piece of iron or stuff like that, it will absolutely attract it, and you can make an electromagnet out of it. A piece of wire, just coil it, that way it's a really long wire, a lot of magnetic field around it, coil it up around a nail or something. That way the core, because I'm about to explain to you why you do that, around a piece of iron, because it'll absorb the magnetic field, because that's what iron does. One of the materials. How does this help? I'm about to explain counter space for the guy that's typing. But anyways, so this magnetic field around the wire that will definitely deflect like the needle on your compass or whatever. It's really there. It'll attract a piece of iron and all that. It's not there. It becomes there when you have current flow. but there's no magnetism stored anywhere. This fiber is not in the battery. You got just metal and acidic or alkali solution in the battery. Both will work, right? But acidic, okay, for like the batteries we use today. So it's like, that's all you got. There's no magnetism there whatsoever. But this flow will give rise to magnetism, and we know that the more flow, bigger fabric, stronger magnetic field, bigger magnetic field. So in this circuit, if we were to place a piece of iron in between, like that nail we're about to make an electromagnet out of, it's going to absorb these concentric circles into the center of it, and it's going to make like a connection between the two, and it's going to absorb these fibers, these lines of these magnetic lines of force is what we're going to call them, and they're the circular ones, not the dotted ones. They're the circular ones around the wire, and we're going to call this archetypal of space, physical space, because the bigger the piece of iron is, the more of this fabric it can hold. Because you could only jam so much into the piece of iron until you reach something called magnetic saturation. You can look up tables of your materials of magnetic saturation, different alloys, blah, blah, blah. But it's called magnetic saturation. We understand that there's only so many fibers the iron can hold on to. So if you make the piece of iron bigger, it'll hold on to more fabric. Okay, more of these fibers, more fabric, more magnetic fabric, thank you. And it concentrates it into the piece of iron. So, okay, so that's archetypal of space, physical space. More iron, more volume, more fabric. Awesome. More lines of force. Now, so this is called inductance or magnetic storage. Okay, the unit for it today is in henries, after Joseph Henry. But anyways, so this is the concept of the inductance or magnetic storage capability. Now, in the circuit, we also have these dashed or these dotted lines of force terminating from conductor to conductor, flying in straight lines from all like around the conductor, but it's trying to go just direct line, and they cross the magnetic lines of force at 90 degrees always. So these circles, you'll see where they draw the dashed lines, the dotted lines, the intersection is always 90 degrees, right? Because this intersection is important. We need it later on in our understanding what this intersection is. But long story short, this fabric in DC, when you're just direct current, it's flowing, and it's flowing one way only. It's not jittering back and forth as it's flowing. No, it's just direct. But this whole fabric is actually like it gives, when you put stuff in there, and it will flow. It will actually go down the direction of flow. Like if you put a piece of like ball bearing or something like that, it will flow down where the magnetic current, the way it's flowing. So this stuff is absolutely flowing, and it has direction where it's flowing. So if I was to put a piece of glass in this circuit, like I did with the piece of iron, but now I'm going to take my piece of iron out, which is archetypal of space, a bit more iron, more space, more lines of force, more magnetic induction, more magnetic storage capability. Okay, I'm going to ditch that nail. I'm going to put a sheet of glass in there. Glass is like a dielectric, what we call a dielectric or non-conductive / insulator. So I can do this with a piece of Teflon, piece of glass, whatever, as long as it's not electrically conductive to electrical currents. Cool? And so we're going to discover something interesting. When we put this piece of glass in there, it's going to absorb the dotted lines of force. Just like the piece of iron absorbed the circular ones, that one is going to absorb the dashed lines of force into the glass. However, the thicker we make the glass, the less dashed lines of force it can hold in there. But the thinner we make it, the more it can hold on, the more storage capability of lines of force we have. So this is archetypal of counter space. The less space you occupy, the more you can hold. Not the more space you occupy, the more you can hold. That's space, that's spatial. But counter spatial is like kind of going inwards, where you have the two vectors pointing to each other, where it's like the thinner the space, the more capacitance you have. And this is what a capacitor is, or a capacitance, where you have two metallic conductors sandwiched between an insulator, and the insulator is where the charge gets charged up. It gets held in the insulator, not on the metallic component, which is the conductor, which is funny, right? So this is charge, this is called capacitance, and I think the unit for it is farads, after Michael Faraday.
Faraday, yeah, this is the concept of a capacitor, right? Having the ability
Exactly.
to hold up to a certain amount based on the size and spatial dimensions, depending on the dielectric contained within the two different sides, right? The two different plates on each side of the capacitor.
And what's critical to understand here, piece of iron attracted the circular ones, the glass did not. So it attracted the magnetic lines of force, and the other ones attracted the electric or dielectric lines of force. I like to use electric, to use the dielectric as the material, or Oliver Heaviside coined a term called electret, with T at the end as tango. And an electret is like a magnet, where a magnet emits a magnetic fiber structure around it, a magnetic field. An electret emits an electric field, so if you hold it up to like to your arm, it would make the hair on your arm like raise up and stuff like that permanently, like a permanent magnet. But this is a permanent electret. And Oliver Heaviside coined this. And perhaps here with electrets, you can maybe there's something too into this world with it, because a lot of people know about magnets, but they don't know about the twin of the magnet, right? The magnet is not the only thing that can, because magnets hold charge of the magnetic field. There's other stuff that holds charge of the electric field, but an electret will emit this electric field. Where it's like broadcasting, it has a lot of it. It holds on to quite a bit for like a very long amount of time, you know? So yeah. So that's capacitance, and it's the ability to hold the electric lines of force. Thinner the space, the less. So you need an insulator, and the less space it occupies, the more capacitance it can hold, the more lines of force it can hold. So this is where these two are conjugates, and like, you know, they're antitheses. Like, they deny one another in existence, right? Where one wants to occupy space, one wants to go inward, not occupy space, and disappear into this realm we call counter space. And this is where in the electrical domain, because this is quadrupolar in nature, and we'll get into that mathematically at some point if you guys want. But because of that, like, electricity lives in like two domains sort of thing. And if you understand that as you go into the math, it makes your life easier when you dig into this etheric research or quantum mechanics, because it will help you understand their Narnia superposition stuff later. You understand where it's like, I get it, because I get the fundamentals of counter space, and Rudolf Steiner, and Steiner is the guy that coined counter space, by the way. That's his terminology. Anyways, I'll shut up now. Talked a lot.
No, it's fascinating. There's so much I wanted to ask about.
Thank
what
you
up,
for
Gio?
taking us back to grade 9 electronics. I remember a lot of this stuff.
Oh, nice, man.
So basically, iron wants to like gather up that electric or that magnetic field, right?
Correct. 100%.
Onto it.
You nailed it. So yeah, that's what iron, one of its, you know, interesting things that it likes to do. It's not the only one. Cobalt and nickel will also do the same. They absorb the magnetic field. They're magnetic too.
So with
Now,
the
sorry, go ahead.
Oh, this will be a quick question. With the dielectric and magnetic, would that be male, female, or is there like the male female version of magnetic and male female version of electric? Because that would make sense. That would make the quadrupole.
Correct. That's where we're gonna use the stuff that a lot of people hate. I know, on my side of the world, which is flat Earth, we're gonna use math, not just math, conceptual, imaginary math, to model electricity in a form that we can actually understand. We're gonna use something called the square root of -1 to understand what we mean by counter space. Because
would this come from Dirac?
Dirac C.
Yeah.
I don't not quite, right? Maybe did he? Maybe he talked about it. I don't know. I'm not too familiar with his work. I understand Dirac with his quantum stuff, but I haven't dug into Dirac himself and like followed his discoveries. Let me know, man. Yeah, tell me.
Sorry, go ahead. Go ahead.
No, all you know. Educate me, please. What did
No.
Dirac
I just
talk
when
about?
you were talking about it, it just made me conceptualize like Dirac's idea of the Dirac sea, right, in the quantum realm. These how did they call them? Whatever, non-existent particles that help with the math equation, basically. The opposite side, the fictitious particles.
Yes. Because like that's why I like to do a visual description of what square roots mean. And that's why I like to take people back to like algebra and a little bit of geometry visually, because we're gonna need that. And if you take that, you apply it to the counter, exactly capacitance and counter space and the dielectric/electric lines, which I talked about, the dashed lines, because physics will absolutely never deny this in anything. They'll show you the sinusoidal one that I said, the electromagnetic wave having an electric component, electric field, and magnetic one, magnetic field. Absolutely. No one denies this, right? But they just go on to quackery. So we're going to take where they kind of don't understand, and we're going to really try to hammer it home to see if we can understand something and come up with a better concept of what these guys are calling this stuff. Because I think that they're coming up with good measurements. So if we can actually get a better angle on the quackery they're coming out with, we'll understand the universe a little bit better. I think. For me, that's just what I think. I like to study it all, refine it, take the best, assemble it. You can make your own, but as long as it's sound, right? It has to be sound and fundamental, like, and just built
I'm
correctly.
not derailing it. Like, I am going to like throw out this tangent thought of speculation though for just one quick second. These
Okay.
ancient, just remember where you're at so you can carry on, because then I have to mute and go check on the fire, and I would like to continue listening. But these ancient cities and towns that are, set up and shaped like circuitry and circuit boards, you think that perhaps that's what they discovered? Like maybe they had these blueprints for these cities that if they follow these
Yeah.
well, not for the cities, but if they follow the blueprints, then they could achieve certain things. And then they realized that the smaller you go in this realm, the more power there is. So they went from cities to microchips.
So, okay, based on like Vasilato's work, because it's photocopied from the Library of Congress, like from the archive, I will say I will subscribe to mainstream realm, where in the recent 300 years, these things that you see are telegraph lines. That's why you see wires. That's why it's in the correct time frame. That's a telegraph pole. That's why you got cables running on it, right? Because these are the guys that started before Edison runs his line. There was no insulated wire before Edison. Edison invented the insulated wire. This guy was the fundamental of the fundamentals of our building blocks today. He existed pre-Tesla. And it's kind of sad how he's like vilified, even though he's not the enemy. Even Tesla worked for him, and yeah, they had a misunderstanding or whatever. So Tesla left. However, he is the grandfather, and he invented switches. Oh my God, everything. All the basics that we need today, even the insulated wire. And he burnt down J.P. Morgan's desk because he ran a wire into the leg of it's a wooden desk. He ran it inside the leg to hide the wire to the lamp, and because J.P. Morgan's house was the first house to get something called electrified back in the newspapers. That's what they called it. There's a beautiful book on this, well documented, called The Empire of Light. I highly recommend it if you love this stuff. It'll walk you through the journey pre the war of AC versus DC, because now we're this is deep in, and William Crookes, where people were playing with these tubes while this war is going on, like over in England and stuff like that. So there's researchers, a lot of researchers spread out that are working onto this. These guys are fighting for the commercial realm, not for the scientific realm. But Tesla, but of course you have to advance in science to be at the like cutting edge of like the commercial realm. And when you're at the forefront of the commercial realm, there's so much money income, and you got funding from Morgan and money that's coming in. You're doing well. Well, R&D, right? You're going to hire the best minds, and that's why Edison was able to out-invent everyone that stole his inventions and copied it. He wouldn't sue him. He would just out-invent them. That's just Edison is another level of just craziness. He's really good, super smart. Anyways, back to our what was it? We got derailed a little bit. My mind is all over, but okay,
Male,
back to the
female,
fabric.
dielectric, quadrupole, capacitance. There you go.
Yeah, square root of -1. Yes, thank God. Okay, I remember. So, because I need to explain what the square root of -1 and then just for anybody that hates math or anything like that, I can explain it. What the square root is geometrically, super easy, right? So the floor of your house, the floor of your room. If you're buying flooring, let's say it's like stick and peel like tiles, okay, and they're like 1 foot by 1 foot. Okay, we're just gonna call this one dimension, 1D, 1 foot, doesn't matter. But they're just the same exact tiles. And you wanted to know how many tiles to buy for your floor. You can take one tile, put it down on the floor, and just draw and blah 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 before you go to a hardware store and do this all over until you get how many tiles you would need. Or you could calculate the area by multiplying the side length by the other side length, and that will give you the amount of tiles that you would need that are 1 by 1 that would fit in that square or rectangle, right? This is called the area. So I multiply length by width, and that's a shortcut instead of just taking a square and just walking it over. You know what I'm saying? Drawing out the squares. That way it will give you how many square of this one by one tile can fit in this area. And because you multiply the numbers together, let's say it's a 4 by 4, 4 by 10 room, 4 by 10, easy numbers. You get 40 of these squares that are 1 by 1. And let's say it was like 10 feet, and you multiplied everything, so you got to multiply the units too, so you're going to get feet squared, right? 1 foot multiplied by foot, so it's foot squared. Because it's literally talking about a square. So I was like, that's why it has 2 dimensions, it has 2 sides. Real things, right? So anyways, so if I was to do the inverse of that, which I was to tell you, hey, if I have 16 tiles and you were to make a square out of, which means the side lengths are the same, what's the square that can fit all these tiles in? And this is called the square root, right? Okay, the square root of something. And in math, you can have 2 answers because it's a square root. You can have a positive answer and a negative answer, and we'll talk about negative answer because it's not real, but it will give you a real number. That's why we use it in math. So 16 tiles, you do the square root of it in calculator, you will get 4, right? Because it's 4 times 4, right? 4 times 4 will give you 16 tiles, if I'm not mistaken. Yeah, I think I got that memorized correctly. I better. So that's the square root of 16 is 4. Because it will give you 4 like feet for each side length of that square. That's why 16 tiles can fit in it. That's a square root. And the cube root would be to or let's say I want to fill this room up with cubes of like fluffy whatever, cubes of whatever the hell it is, cheese. I don't care. You need the 1 foot by 1 foot by 1 foot. So I would do the same thing in the room. I would measure the length and the width. But I would need one more measurement, would be the height of the room. Let's say if it was 10 feet high, and I would just multiply that. Now I know I can fit 400 cubes of 1 by 1 by 1 into this room. There's a volume, right? It's going to have a cubic notation on the unit. It'd be like feet cubed, because it's telling you it's a 3D thing. It has 1, 2, 3 real dimensions. So there's a cube root of that too. But for the square root, so anyways, square root of 4 of 16 equals 4. Or -4, because in math, a negative multiplied by a negative will give you a positive integer. So -4 multiplied by -4 will give you a positive 4. That's why you'll always have 2 sets of numbers for square root, a positive and a negative. And now what we're talking about is the square root of -1, the square root of something that doesn't even exist. And of course, there's no such thing because the square root of always talk about real squares. So the answer in math is I or J, right? 2 sets, of course. We're going to have positive I or positive J and negative I or negative J, right? And that J is or I is like imagination, but that's what that is. That's not real. So this is, and and -1. So it's like, imagine like a length of the square in your mind shrinking to 0, then going into inward space somehow and growing into inward space, like -2, -3, which does not exist in reality. But mathematically, with the square root, we're modeling that. And we're going to get two sets of answers, which is, they're vectors like I and J and all that. But this is we're modeling the invisible fabric that wants to go inwards, which is the domain that it exists in. So that's counter space, the square root of -1 in algebra. And that's where we kind of bridge the gap of understanding. Now we have really good math, which is super basic, and we can carry forward. We can even imagine it in our head as like the square root. If you can imagine the tiles and just whatever, shrink them until like you reach 0, then you go to -1, a square, which the length of the sides are -1. There's no such thing, right? It does not exist. How do you go inside of space, right? So that's the idea. It's inside of space. It's like it doesn't exist. But you can use it as an extremely powerful tool in electricity to carry forward with the understanding with what the hell this counter space is. And this is exactly what we're talking about. This domain of negative. It's a negative domain. It's not real. The imaginary domain, which is the square root of -1. And we use that to build the quadrupolar nature of electricity and, refine our understanding of nature. Hope I made sense.
Yeah, I just kind of visualize it as like, or I just started to think of it just now as like breath. You have an outward and an inward.
Yeah, bro, that's it. Just imagine it. The fabric, you just go inside your head, which you cannot imagine, but that's the idea. Good luck. But that's okay, as long as you get the idea. As you're like, you have a cube. Imagine a cube of an ice cube in your mind. In your mind's eye, draw an ice cube that's blue with whatever size. Now shrink it in your head, okay? As it's shrinking, you're going to reach the point of 0 where it's not there. And then you're going to grow it the other way into inward space. That's counter space. It's not real. That's it. That's the domain of half of electricity lives, where the dielectric lines of force live, but the magnetic live in real space. These live in counter space.
The magnetic creates the spatial dimension, right?
Correct. And that was the Tesla transmission, essentially, of where Montreal and I started the convo a while back, was the transmission with the electric lines of force, only electric, snuffing out all the real components, transmitting electric into backwards in time horse shit. But that's not how it is. It just you're transmitting through counter space. That's why it has the superluminal effect to 1.6 times the speed of light, 1.6 c.
So female moves inward, male moving outward.
Correct.
That's on one. What about the magnetic? How do you get the female movement of?
I can see this fabric, the owl that I call the owl diagram. I can take this and take you to quantum mechanics to understand the ether, more into the ether with the knowledge today from my understanding of what the hell they're saying. Not, not exactly what they're saying, but refined, which is exactly kind of what they're saying, to our knowledge of, well, there's a good question here. So this magnetic fabric, let's just talk about the one that we can actually deal with, easily. Magnetic fabric. What's causing these lines of force why are these lines of force attracting iron? And why are these lines of force there? And why is it that when we have the flow of the other lines of force, the electric lines of force, when we bind it from like a battery, there's no magnetism. Once we have a current flow, once this other fabric flows, it gives rise to magnetism where there was no magnetism before. But once we close a circuit, we got current flowing. Now we actually have magnetism appeared out of the water. There was no magnetism. Now magnetism appeared. So how in the world did these fibers, magnetic lines of force, they're not real fibers, they're magnetic lines of force. Where did they come out of? How did they come into existence? They're not in the wire. It's not in the battery. Where did they come from? believe it or not, this area right here is not really studied. Never been studied. Steinmetz is the only guy. The last guy, from my understanding, to theorize here. But the quantum mechanics, electrically, the quantum mechanics guys, from my understanding and their theories, I use QFT to actually, for the missing pieces of the puzzle, from my understanding of the fabric, because I think that they have dug in, and you can extract really good answers for what these fabrics are, especially you'll get the true secret of the magnetic fabric from the quantum guys. They will reassure us of Faraday's understanding of the 1700s. Believe it or not, this is like, oh my God, I couldn't believe it in QFT, but that's why I like it. It's a theory, quantum field.
Is it increasing the coherent polarity?
No. There's no real magnetism. Isn't real. Magnetism is an effect. Magnetic line, the circular lines of force, and we understood this
Is
while
it the
back.
ether under stress?
The law of assimilation.
Correct.
Law of attraction.
The ether under stress is the electric lines of force. So when we stress the ether, we have electric lines of force. When we flow when we move the fabric now, when we move the stress with respect to space or time, right? Because of course time, yeah. Magnetism appears. Magnetism arises, and we understand this from this diagram quite well. This is Ørsted and Faraday's discovery. Or this magnetism, what the fuck is this magnetism jumping out of the wire and moving my needle, man? And why is it attracting the piece of iron? When I closed the circuit, he was drawing arcs. Like, why? Well, he was just playing with fire. I was like, what? Piece of iron. Like, so once the current was big enough, big piece of iron jumped off the desk. Like, will get attracted to the wire as you draw this arc where we have current flow. So where did this how? So is it there? 100%. 100% there. Is it an effect? 1,000% from the flow, from the current flow. But even though the flow isn't made out of it, the flow is made out of a different fabric. But it will give appearance to this other fabric. So we can always conclude from back with Faraday that this magnetic fiber is the effect of the flow of the electric fiber. Okay, and we can define those even further with quantum field, QFT, quantum field theory. We can really refine that theory. We can take that to another notch and get a further understanding of what's going on. But the idea is now this fabric, this fiber, this line of force of magnetism that's attracting real iron isn't stored anywhere in the system, but only when the current is flowing, this appears. And here we go. Induction, AC, boom. Look at your world today. That's that discovery that runs your world. Welcome to the club. So that you can create magnetism from electrical flow. You don't need magnets, right? And this fiber, when it flows, gives you, energy. That's energy. So
sounds like how they're explaining the gravitational, if you want to call it gravity, like the attractive forces, right? About pressure. It sounds like that's what they're trying to explain here. Would that be the same concept, only in terms of
here, where
magnetic field?
Where is here? Stuff you posted? Okay, Russells. That's different. Yeah, we're not talking about Russells right now. It's good stuff. I love his work. It will can help you understand. But
the way he's talking about the electric, the pressure, would that be the kind of like the same concept, only in terms of magnetic field? Like maybe the same thing going on. Just would it have to do with pressure? I guess that's what I'm asking. Is it pressure?
Well, that's how we define the other fabric, the stuff that causes the magnetism to appear, because the magnetism isn't really there. Well, it's really there when it's there, but it's an effect. So as long as we understand that, now we take that understanding to magnets, right? Magnets and magnetism on its own is just the flow of ether under stress gives a rise to magnet. Now, and this we'll check out with quantum field theory. So this is the way I will say it too. Like that's how I have understanding of it now. Where don't get tricked, don't get fooled with magnets and magnetism. These fibers are there from the flow, or I can use quantum term mechanics, but I don't want to. But this is the stress, or due to like micro flows of the tension lines in and out of the metal of the magnet, right, around it. And that's why you have around that float, you have a rise, like magnetism appears that attracts iron. So the magnetic fiber is there because the electric fiber is flowing around the metal. And that's it. And you just can't see that one, but what you see is the effect, you see. And that's where I tie my understandings from the quantum mechanics and the classical mechanics of electricity, and I carry it forward to like further my knowledge, right? And I don't care about the terminology, photon, electron, proton. Love them, phenomenal. They're giving me quantities of stuff, which they're telling me it's the electric quantities that make up materials. Like, thank you, I love you, appreciate it. That's all I wanted. Like, it's like you guys are saying they're speaking my language. It's like awesome. So that's why I love chemistry too, morphology and stuff.
So when you have the pressure mediation with the electric, like the pressure, the stress that it's putting on, that pressure mediation causes the effect that we know as magnetism. The pressure.
Okay. I gotcha. Okay, so to explain this, we need capacitance, not magnetism, because that's what we're talking about, right? So let's discuss like capacitance, how we want it, and how it actually will be displayed like this in many books, man. It's not just how we want it. I just want I'm picking and choosing the diagram to give you the arrows, the vectors. Cool. Two plates separated by an insulator. We have capacitor. Insulator can be air too. Any dielectric / insulator, because dielectric is old terminology for insulator, is something that does not conduct electric current. However, it will hold electric charge. Like I told you, and out of this we have two electric components that you can go buy off the shelf and make yourself. One is called an inductor, and another one is called a capacitor. I'm not talking about a resistor. An inductor looks similar to a resistor, but it's not. An inductor stores energy, electric energy, magnetically. Okay, strictly magnetically. Capacitor stores charge. Okay, potential to do work. It can do if you charge it up, right? It will actually do work once you close the circuit, but you charge it. It has potential, or I'm sorry, I'm sorry, I lost my train of thought. But it holds, like that capacitor holds dielectric lines of force electrically. It doesn't hold magnetic fibers. It holds the other fibers that we're talking about. So it doesn't. It's the inverse of the inductor. So this is a capacitor. The other one is an inductor, which is a simple coil, and it can have an iron core, air core. It doesn't matter, but it just stores the energy magnetically, and this one stores it electrically. Okay. So once you have a charged capacitor, there's no magnets anywhere in there. Nothing. Okay. But once you close the circuit, and let's say you have a bulb or whatever down the line, and you have enough juice in the capacitor to give you enough time to measure the magnetism around the wire, you will see that magnetism will appear around the wire when the flow of whatever was in the capacitor started flowing. Okay. So when that happens, this is where the magnetism appears, but there was no magnetic lines of force stored in the capacitor whatsoever. That's why it's an effect of the flow of the electric lines of force. So apply that to a permanent magnet, essentially, and that's in the etheric realm, right? In the quantum realm. I hope that made sense, kind of.
Could you repeat that? I'm joking. Oh gosh. It just didn't sound like you were finished. It sounded like you were still had.
The story doesn't end. I mean, what? This is like the history of science at this point, right? Like how stuff came to be. So it's like it really doesn't end. You keep going with the stories like forever. But I have to stop so other people talk at some point. So.
So I dropped the.
I think we're all intrigued, man. I don't really have. What's that,
I was
Napalm?
just gonna say I dropped a video in there that gives a good. She goes through good visualization of like the 3-dimensional components of how these waves would be traveling, discussing the magnetic and the electric and their interactions along like a wire. I'm kind of a visual person, so it gave me a really good understanding of kind of the concepts and maybe the mechanics of the movement itself, which gives the
Yeah. Same here. If I can't imagine the flow of it, like you know what I'm saying, like I'm not there. So I like mechanical engineering stuff because it's model it.
Yeah, and she does a really good job of starting from like the basics, like here's a wave in the water. Let me show you what's taking place, and then all the way up to the electric and magnetic components of electrical current. It's pretty good.
So is it the inductor that stores it magnetically? Yeah, it does. Okay.
Correct. Yeah. So theoretically, if I had perfect conductors in the world, which they don't, means they have zero resistance to electrical flow, which means they don't destroy electricity. They just reflect it with 100% reflection, because any conductor of electricity must be capable of reflection. Because what we're doing is reflecting it into, or we're trapping it. That's what we're doing. So it has to be
Would
capable of
gold be the
reflection.
closest?
Gold, yeah, gold is a perfect grade. It's a great reflector. I think the best is silver, if I'm not mistaken. Silver than copper. Well, is it silver, gold, copper? Yeah. Silver, gold, copper. I think silver is better though.
Yeah.
Silver is the best, I think.
So this electret is interesting. It looks like all you need really to make it would be
Beeswax and
a corona discharge, right? A wax and some sort of corona discharge, which looks like is easily achievable.
yeah. No, it's just this. Really, I haven't made any yet, but I've seen some failures and successes on YouTube. It's when the idea is when the wax is crystallizing, you want to do this really slow and controlled between two capacitor plates that are charged up at as high as voltage as possible, but without it breaking down. You don't want sparks without dielectric breakdown, because you don't want that. That's going to ruin everything. Because we want just tension, so we want it to dry, to crystallize in the tension field, and that will line up the crystals and make it emit this field. The same idea with the magnetism. We're just doing it to a wax.
And the dielectrics are the insulators.
Yeah. So like you have two plates, and you just you pour your hot wax and your positive plate and your negative plate, which is, let's say, your metallic bowl. The key is in controlling how fast it cools down. You want to do this in a controlled fashion, which that's what these guys lack. If you do it the proper, like you'll find patents and stuff like that on this. So maybe you can cook up some of those. The idea is that the plates are touching the wax, and the wax doesn't conduct current, but it will once you crank up the voltage to the dielectric breakdown of materials. You can look up that table. It's a very cool table to just look at. Everything breaks down electrically when you crank up the voltage. Crank it up high enough, it'll blast anything. Doesn't matter if you got enough juice.
What is it called?
What's up?
What is it called?
Dielectric breakdown of materials or elements or materials. You'll see there's some engineering tables on that, which will give you values. You can just compare, kind of just a quick idea of, what breaks down with what. Like air, I think for travel like 1 centimeter in the air at like, depends on the humidity and all that. I forgot what, like, just say whatever ideal temp and humidity they said it was at, 23 and maybe 40% humidity. It's like 30,000 volts per centimeter, something like that. You can look that up. That's how you can, if you have a spark gap, you can measure the voltage of your circuit. If you can measure the spark gap accurately, you know how many volts you're running on because of the distance to jump the air to ionize it. You need there's a certain threshold where electricity will just punch through stuff. The
Yeah, this
voltage
is
threshold.
this is the concept of lightning, right? It's
Yeah.
The charge difference or the charge potential difference between the two areas, right? The clouds and the ground, or wherever you're holding that charge, it gets discharged between the two of them, right? So that's basically like a really big spark gap.
Exactly. And just breaks down, and we understand the other charges, like between an insulator, they all rush to that point. And because of the heat, because now Dollard and Thompson, these guys have a phenomenal understanding, like of this discharge lightning capacitor discharge thing. Is that when you break one of these lines of force, the neighboring lines rush in to fill that void. And because of the density of the lines where they're rushing into one spot that's really, really small, they're trying to go into this counter space realm, you get fire because of the heat, you know, and plasma. It excites the gas, and here we go. This is how electric plasma phenomena, which is caused by the rush of these fibers when we break them.
Yeah, just think of like fibers attached between, like, let's say the ground and a cloud, right? And the tension becomes so strong, or the difference is so great that it makes its maximum capacity to where one of those snaps, but all the rest move instantaneously to fill in that gap that was filled by the one that snapped, and the snapping of it and the movement of the others to fill the gap is where you get the noise, the light, and all that shit.
Right on. Nailed it, man. So it's if you stick with that sort of understanding, it's kind of, you can really build up really good concepts with JG and the electron, and better understanding of morphology, table of elements, and I think it far superior actually.
Could you even go so far as to say that lightning is a discharge into counter space?
100% is exactly what we're saying, sir. Thank you, sir. You understood exactly what we're saying. You see that electron that we ripped out? Remember that socket? Yeah, the socket was in the material. Remember, we said it's literally holding the atoms together, right? It's this outer shell of the material, right? This electric outer shell that's holding the material together, and these fibers, this is where they terminate, right? Between the material, like in the outer shell. So they're in the outer substrate of like anything, right? They're on the surface of everything, right? So these terminals, these sockets. So when we strip that out, that ruined part of the material for some reason, all the other lines of force, the bungees, they're all going to rush to that location in the socket where we just broke it. And it causes fire. Maybe just seal it shut in counter space or something. I'm not sure. Use your imagination as you wish. But yeah. But that's the idea. It's exact. They're discharging, running into counter space. So in the appearance in our realm is, lightning. But it's like a sideways discharge into inwards of nowhere. Of into the abyss of the other space, the conjugate of space. Counter.
Could you say it's a rush back to its? I'm not going to go there. Okay.
Hey, all you brother, because you can take this concept now, and if we take JJ's concepts, JJ runs with it like he runs wild. He runs wild in his books because he gets into like vehicles. Why is it when I step on the brakes, right? Dollar talks about this. I don't come to a instantaneous halt. All right. JJ has a different concept of this, and it opens up your world into a different view. Anyways, I'll be back. Just give me 5-10 minutes. I'll be back in a minute or two.
Yeah, are you taking off, Cyrus? Was that to the room?
No, I'll be back in 5. Just give me 5. I'll be back.
All right.
I'm taking off from like my computer desk.
Gotcha.
All right.
Yeah, but I would say that J.J. Thompson was talking about that car not being able to stop because it's not discharging the energy quick enough. Is that what it is? I think that was his concept.
Yeah, it was the it accumulates charge, and we can absolutely measure that like electrically, right? So his idea was electrical. You have to discharge electrically. So his idea was, what if you find out a way, right? Because it's morphology, essentially, they're going to come up with, the stuff, the atom and stuff like that. What if you can disconnect your vehicle? Take these electric lines of, not magnetic, right? Electric lines of force off, which they're all around you, and not be touching any of those. He theorized that when you hit the brakes, you'll stop right away because you're actually not held by the fabric. You're not touching it. But in order to do that, you need to ground your vehicle. Can you guess where? Because you can't ground it to your world, because that's why the fabric is there. Counter space. So if you could find this neutral, universal ground plane, some people call it something like that, the universal ground, the neutral plane, and literally hook like an alligator clip, right? Your metallic shell of your vehicle to somehow this device that's touching the ground and counter space, which doesn't exist. Now you're free. Your vehicle is disconnected and you can move about freely. You can take 90-degree turns and you don't get shoved to the right or left. All this Newtonian stuff disconnects off your body. This is Thompson, Nobel Prize.
This is the vehicle concepts of like behind UFOs, right? You would technically be creating this counter spatial bubble around you, right? For lack of a better term, like a shielding that would allow for this movement to take place without affecting what's inside of it. But you have to figure out a way to establish that counter spatial bubble or shielding from the spatial around the craft in order to operate and flow through it. And then, yeah, like you said, you're now free to move about. Fascinating.
Yeah, it is. I've always been wondering about all this stuff, especially since I stopped trusting mainstream science. I'm just like, oh man, is anything worth looking into, So it's good to actually hear some real science.
I mean, for me, a lot of this makes so much more sense to my brain, certainly conceptually.
Mm-hmm.
Like this mixed in with like Walter Russell's ideas or conceptions of what the periodic table should be, right? In more of a structure of vibration and octaves, as opposed to atomic mass and that whole conception, like two fields of thought.
Right.
I don't know if are you familiar with like Walter Russell's conception of the periodic table of elements?
No. If you link it, I'll look at it.
Yeah, I just posted it there. See how it flows in that like sinusoidal wave. You got different octaves, and the resonant frequencies of those objects within this spatial realm fall along the lines of a vibratory pattern.
Oh, hold on just a second.
It's a pretty interesting way to think about it. It's kind of like he's coming up with this conception to where he could be like, you would have the same ability to predict where another element would be, right? Or another thing should be expected based on this type of pattern.
Mm-hmm.
If I'm not mistaken, it matched exactly with the atomic number guys, what they found out with their predictions. So
Really?
Walter is correct. It was based on the like harmonic progression, essentially music. But it's like right on.
Dude, to me that whole conception
Fascinating,
makes
right?
so much more sense to me, and it's opened up a much better understanding of this whole entire field of study, just kind of, or whatever you want to call it, these ideas or concepts. Just thinking of the world in
Oh,
more in
man.
terms of like the vibratory nature and how you have the harmonic nodal points and how you can,
Yes.
just it makes so much more sense to me.
I should introduce you to the guy that discovered quarks before even anybody knew what a quark was. The subelectronic element. And his story is so fascinating that, too many red flags for me, but I kind of like, wow, I wish this guy's correct, man. But yeah, I don't know.
Interesting.
Walter Russell completes his work, right? He's older than Walter Russell, and he was competing with Tesla, making motors. Because he made some wild claims, and this is where maybe you should have dialed it back 2 notches. Talk about Keeley. I'm sure you've heard about him.
Keeley. Yes.
Yeah, because Keeley theorized or discovered, according to him.
Sympathetic vibratory frequencies, dude. You and I in truth have sat in a room and listened to a lecture on Keeley for like 3 hours at 2:00 in the morning.
Yeah. So you still remember good. It was one of my golden nuggets throughout history where the concept helps and it matches what these nutheads are saying. Like the 3, parts is like wow. If he actually said that, one, he's either working with some demons, man, or like he was a wizard, way ahead of his time. Like no way. And because dude, it's crazy. If there is actually like quarks and they are like that, and it is correct, it matches Keeley, and he said he made machines work with his mind energy, and this is where it gets weird, but I love it because it takes that musical idea and it carries it forward, which is not bad. However, it's like, it can shed light or shed darkness. It depends how you use it, but it should shed light, especially with Walter Russell. Walter Russell kind of refined Keeley's, like the missing parts in Keeley's like ideas. I like Walter. Polarity and all that, of course. He's got great tables and great like graphics. Have you seen the pendulum of nature or whatnot or whatever?
I just found this.
There it is. Oh, I think there's another one besides this one.
I think I took a snapshot. Yes, let me. Yep. Okay.
Because I think he was trying to bring in like the spiritual God aspect to it. That's why his stuff was like really trying to complete the picture, not look at one half, right? Sort of.
Nope, you can't talk about the metaphysical, okay?
Well, that's what these guys are trying to measure, man. Electrons, like what? Photons, what? Like,
I know. They're going to miss stuff if they don't realize it has a deeper level to it.
But we can play along. But yeah, I think this fundamentals of like science and stuff like that is really essential.
Yeah, I'm gonna post something here in a second. You're gonna be like, yep. Hold on. Scroll through all my freaking pictures.
To Russell. Yeah, dude, classic, man. Good stuff. This is yeah. I know you've read all this stuff like Napalm, so I like. It's different, man, than these nutheads tell us like how the world is. Space time. I mean, it's nothing new. These concepts aren't new, but like the way they're presenting it is just madness. Because it's been presented
I want to
before.
hear you. I want to hear you have a conversation with Jace. Have you ever talked with Jace?
Yeah, I talked to him before, but like I don't know. He's okay. He's cool. I like him. I think he's pretty smart.
No. Me too.
But he's into his fermions and all these, and like that's like I don't stick with that terminology, but I understand what you're talking about. Standard
Look at
model.
that!
All this thing.
Look at that screen grab
Yes,
that I randomly have
that's
in my
it.
on my
The
phone.
Keely's morphology, which I subscribe to, which is the modern morphology. So I have to subscribe to it. Why not? Why not? It just happens to match and precedes these Quarkians, predicting the
Yep.
Quarkians and how many. Like, come on, dude.
I agree, and I don't know.
And
Maybe what we're arguing over is two ways to look at the same thing, but I feel like one way is an intentionally retarded path.
not
Like
even, bro.
intentionally.
I don't think so. Like nature, right?
Yeah.
Coin. I like the coin like I'll use the coin analogy. Exactly what you said. There's two halves of that which make one. They're stuck on they haven't even seen the entirety of one half, which is the brute force way, hammer, sledgehammer, accelerator, smash atoms into another to make another one. There's another half into it, right? The other half, which they don't want to look there. No, electrical world. Nope. Even though they believe it and it's the core fundamentals of what the fuck they're doing, it's just how they're trying to brute force nature or brute force the creation of materials, which it does work. Okay, when you shoot it with this, yes, you can assemble new elements, but the energy scale is just retarded. So perhaps if they studied the other half of it, they can make this come together with less energy so we can actually make usable energy out of it and new materials and all this stuff and advance our knowledge. But they haven't been doing that. They're stuck on like half of the half on just one side of the coin. They're just one. They don't want to look at the other side. Nope. It doesn't exist. Einstein scrapped it. So it does not exist, and they're stuck into their just sledgehammer. That's all I got. Make it bigger, make it bigger, make it bigger. That's it. We have other ideas because we're trying to understand the other half and look at it in totality. That's why I disagreed with you. You said two ways of looking at it. We're looking at totality. They haven't even seen half of it, right? So they're just blind.
They haven't seen a quarter. They haven't even seen a half of one side of the coin.
Exactly. Not 25%. They're just blind.
Yeah. That's why I'm saying it's like they're on the right path. It's just such a, for lack of a better term, a much more retarded path to take that slows the advancement, right? Like it's
if you look at the
nothing but
table
a hindrance to advancement, which I'm not using. I'm not using it in the special needs way. You understand how I'm using it, right? It's literally a retarded path.
It is and with how fast the advancement in knowledge was coming out. Me, of course, being a conspiracy theorist, I like this. Even though early on, I don't know, man. Gut feeling, nose, whatever, instinct. I detected something there. Something happened. 30s, 40s. Something really happened, especially right around that with the tubes. It was then it got government monopoly and all that. It really got snuffed out. And we entered the transistor realm. And of course, we know why transistors took over and all that. But in general, this was the end of the electronic research into that. And then because of the fusion and Farnsworth, that's it. That's the only vacuum research that's really left now is fusion, which is still vacuum tube stuff. Just kind of done with stainless steel, not really glass, but with glass like view windows so we can put a camera and see what's going on inside with the plasma. But that's it, man. That's where we're at today. And for me, it was fundamental to see why they snuffed it out. Why? This is where you grab your lever and you dig and you peel it apart to understand why they snuffed it out. This is the key. That's the missing piece. And it was, of course, in the energy domain, 100%. It's all in the energy domain. Just pure greed and nothing even else. Just pure greed, energy domain. And they found the right shill to hang this shit on, which was Einstein. There you go. Where we love you, bro. You're the smartest. Here you go. Controversy over the Nobel Prize. You can read about it in the newspapers and stuff like that. Yep. Victimized his way into it.
Mm-hmm.
Simping his way
gosh.
through it.
I just realized that this one has the shape or that has the notes in it.
Oh, I should send you that. Yeah, that's the pendulum. There you go. You found it. The cosmic pendulum. Nice. Beautiful. Walter Russell is amazing. And then you should watch the vibratory physics lecture I got. It's pretty long, but it's cool because it ties us with music theory, and which is absolute. Like it's according to Dollard, is this and optics are the two fields of science that haven't been like adulterated. It's just nobody really went there, and there's no. It hasn't gotten snuffed out. It just hasn't been developed further than what has just been left there, and nobody really tried to bury it. But with the electrical research, yes, you can find it easily, where people come up with the invention and stuff like that, and they just get deleted out of textbooks, man. You can go back. Oh yeah, this guy invented the TV. So, why do you teach this? Why do you teach people about the person that invented the electromechanical TV, which didn't really work? The one that got the one that got spread out was the electronic television. And why didn't Philo get money for this? Oh, lawsuit, RC. Oh, I see. And then, Philo is a true inventor. Okay, so do you give him money? No, and we still snuff him out of the books, just like Tesla. So there's weird stuff that happens in the electrical research realm, and then no more research. And they still suck billions of dollars out to do their fusion research until now, and we're nowhere. We're at CERN, and this is where we're at. Go ahead, read whatever they're doing with their accelerators. That's the last of the vacuum tube era. This is where it ended. It ended up being just that. These guys, since the 60s, that's all they've been doing. Playing with the same toy, essentially. Which Philo did in a glass tube. Without the billions of dollars. $10, $100, or whatever. Philo.
Probably got a better understanding from what he was doing inside of a glass tube than they're ever going to get from CERN.
Correct. Because he understood what this... He's the one that really understood what Thomson was talking about. Why? If you read about his invention of the electronic TV tube and what was the problem with the other one that didn't exist, because he had this idea since I think he was in school early, man. He was young. And I think his chemistry or one of his school, he excelled in everything. He's super smart. One of his school teachers actually encouraged him, instead of Tesla, you cannot create a motor without brushes. Guess who's the guy that creates the brushless motor? Nikola Tesla, the guy I was told in college you can't do it by his professor. Same thing with this guy, but he tells him, dude, do it. Of course. You should do it. And it should, in theory, like what you're talking about, should work. All electronic photo tube. That's what you just read about that, which there's no moving mechanical parts to scan with. It's like, wow. So he was able to scan using the electron itself. That's why Dollard said he's the one that understood the electron. And so with his fuser, when you get into fusion now, because now where it's like, this is where I'm at in the world. I want to understand here. This is where, I would say, collegially, I kind of left off just because, I ventured into the other, this realm and stuff like that. But I know where I need to go back and just study the garbage they teach me, or I would have studied if I would have entered nuclear engineering or something like that, about fission, fusion, and stuff like that. So that's what I've been studying recently. And I had to catch up on my chemistry and their electron proton morphology stuff. And by doing that, I couldn't believe it. I finally understood what the hell I was looking at. It's like I'm looking at the same exact thing that Thompson and these guys were saying. I just had to go back, Whitaker's book, of course, that you're reading, and spells it out in detail, accurate detail. We can go dig it up what these guys were saying. What happened after Thompson with the electronic theory of materials, where people now postulated that materials are made out of these corpuscles, out of these materials on the outer shell, because we can pull it out. So it's a phenomenal thing, because now based on this ratio, shit works. Reactions and stuff works. So perhaps they're onto something correct, but not exactly how they're aligned in the atom to create the so-called tangible shell. That's nothing really there, right? It's just this energy fluctuation or electrons floating, however you want to understand it, vibrations in and out, doesn't matter. This material realm, all the science agrees, is kind of not really there. It's there because of this. But if you can tap into that and break that, that breaks. It disintegrates in front of your eyes. Like, it's fine. You can shoot it. You can do it with brute force, right? Sledgehammer approach. You bombard it with like particles, you know, and whatnot. But anyways, that's yeah, it was just electrical properties of materials kind of piled up together in chemistry with the work of like electricity. They went together like hand in hand to come up with this stuff. And with the atomic number, bro, I'm not an atomic number hater. Do you know why? Can you guys guess the device that was used with what Moseley? I want to say Moseley. Yeah, Moseley did this to predict. He even predicted, bro. I think the what was it? What do they call them? Not lanthanides. What do they not lanthanates or something like that? Anyway, something like that, where he said they would have to be 15 and 15 only, based on he was doing X-ray. I forgot what the process was on like the elements, and to determine like the ratio of protons to neutrons, like in the atom. Just ratio again, musical, right? It's all in the ratios. And just based on that, I was able to predict materials and spots in the table of elements, and it came out with the atomic number. We found him later. He was legit, and he did it, of course, with the X-ray vacuum tube. Boom! Let's shoot it with electricity, electrons. Once we liberated this thing out of the metal, right, and we got it to flow in a straight line, man, this opened up a lot. That's why he got the Nobel Prize for it. Like, goodness, man, JJ is so important. Like, digging into chemistry, he's there. Electricity is there. It's like, wow, man. Thompson, and even weird UFO stuff, he's there. It's like, what? Who is this guy? He got the Nobel Prize. So I was like, I mean, okay. Him and Rutherford, right? They shared it. Rutherford, whatever. So yeah, so like that's why I don't mind.
Go back and give a little more detail as to the atomic mass being discovered through the tubes. Is this through X-ray?
Yeah, I gotcha. So it was Moseley. He was doing. Let me get you the process name real quick. Hold on. Yeah, X-ray. He did like X-ray diffraction through crystals. Okay, like on metals. Okay, so it was X-ray spectroscopy. So it was 1913, early on, like when this guy was playing with this stuff. So let me hear. I'm scrolling through Wiki on his section. Let me tell you what he did with the Z number. Yeah, it's Henry Moseley, known for there's a Moseley law right after him, because he predicts based on the stuff. So this is where you can gain better understanding into chemistry, studying what this guy was playing with electrically, right? And if we don't understand what the hell we're shooting out of this stuff, we're lost to begin with. But it's interesting to just see how chemistry is coming out of bulbs. Bulbs were the forefront of this when we understood that when you get rid of air, okay, we have these invisible streams. With enough voltage, we can get these invisible streams out of the cathode to fly out. And they're absolutely something is coming out. You can excite physical materials such as phosphor and stuff like that. There's absolutely something coming out of there. But like in the air, it will get snuffed out pretty easily in the air because you can't shoot electrons if you got a thin window in front of the electron gun, really thin glass. Of course, under like the nice vacuum and all that, you will actually be able to shoot it into like a couple millimeters out of the air and all that. So you can't, and it will just get snuffed out, right? It gets absorbed, diffracted, and all that shit. It gets into secondary emissions, just gets absorbed, right? It's just like energy gone, right?
Which is why you need the vacuum tube, right? Because the air would be acting
in
like a dielectric or whatever.
Oh, it's the particles are physically in the way. The gas is physically in the way of these things. Like, think of it as it's actually physically in the way of the tube. So when the tube breaks, that chunk is really tiny. On the end of that discrete quanta of like one tube of force, one electron. So now we're going to have this piece of metal at the end of the tube trailing behind, like stuck at the end of the bungee, right? The glue. at the end of the bungee. Let's say the glue is the only visible thing, but the bungee is not. Right now, as it's being accelerated towards, it's still held on the other side. Right, it's going towards the anode now. Because it's smaller than the air particles, because air like multiple particles attached, it's really big, right? The minute it hits it, done. It's like, you're shooting a little, let's say a billiard ball into like, a set of bowling balls, essentially. Some or even a little bit bigger, or bowling balls stuck clustered on each other, clusters of bowling balls. So it's just going to absorb it right away. It won't fly straight. It was just boop, 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 gone, done. It won't go to your screen. It won't fly in a straight line. So you need to really get rid of the air. You don't want gas in there. You don't want the ionization where the gas becomes a plasma and you have this discharge. No. We don't want that. We want to table that. We're not interested really in that. I could post videos for you guys on the CRT if you're interested. Because I'm here. You want Mosley's? Have you found them? If you're interested, bro, this right here, like side reading, because that's the lack of collegiate level stuff. Like I said, I missed because it wasn't in my area. So, but I was always fascinated with it, and I knew one day, I just didn't know when. I know one day I'm gonna have to study it. I just didn't know where to begin because I had a phenomenal wizard in electricity, even though that's not what I studied. And I studied mechanical engineering, but I studied the electrical domain because it was just a love of mine. And I found Dollard and stuff like that. But I never found an Eric Dollard for chemistry to take me by the hand and be like, nah, someone that did the heavy lifting to actually be like, bro, this is the true understanding how things in chemistry came to be. Because people today will just read, whatever science book it is, and that's it. And I don't want that. I want the fundamentals, how I understand electricity. I can take everybody by the hand because I have a good imagination of the non-visible fibers that the demons, I call it the gremlins I'm dealing with. So in chemistry, I know it's even worse. Morphology, the like subatomic gremlins that react with each other, and they're absolute, and I've got no idea where to begin. Funny enough, so recently just digging in the rabbit hole of electricity, I come across how exactly chemistry came to be in the modern realm. Because there were chemists and before that, but this is where it gets refined to what it is today. Mr. Thompson. I was like, funny enough, that's it. So I followed that trail. Now I'm getting a really good grasp of chemistry and the morphology, the quantum mechanics, and all this stuff. All comes out of this guy. So yeah.
Nice. That's why I was wondering how much you've talked to, or if you had talked to Jace, because I think that's kind of the realm that he deals with, like in a lab doing chemistry and dealing with.
Yeah, his level of chemistry is way over my head, my friend. Way over. I know nothing in chemistry. I'm more interested. I like morphology. I'm more interested in morphology than the chemistry bit, which is the electrical bit too of chemistry. So
I think he deals with that though. I could be incorrect, but
yeah, he's gonna subscribe to the muons and fermions. Just common mainstream. That's what I'm saying. I don't want that. I know I can read about that. You can pick up any book and read about this. Cool. Good luck. Let me know how much you understand. Cool. Come back here. Tell me if they're going to tell you about Thomson and walk you through the hand of what the hell the electron and the Faraday tubes from 1700s. They don't have enough space in the book to do that. They don't want that. That's just too. That's a full understanding of what just happened in your world. Of two dudes, one guy in Italy before then, early 1700s. One dude dissecting a frog, and he comes up with this animal theory of electricity and all that. It's like, this is where we start, man. Frog dissection, dissimilar metals. And what came out of the theory of dissimilar metals? Mr. Alessandro Volta, 1700s, predicted electrons. Okay? That's how he predicted. All the batteries today are still Mr. Alessandro Volta's called voltaic pile. And a battery means an array of. It's a cell is like two plates in a caustic or acidic bath. And you line those up. Now you have a battery of cells, and that's what a battery is. That's what it means. But before it was called a battery, it was called the voltaic pile. Credit to Alessandro Volta, which opposed the other Italian fella He said, no, the electricity is coming from the animal. It's called animal electricity. Versus Alessandro is like, nah, dog. It's the atmosphere around dissimilar metals. When conveyed by a caustic bath, you get fire. This is what they called it back then. So you have to take their terminology, because you're going to read that in the 1700s stuff. Fire. And if you don't know what the hell they're talk about the electric arc that you can pull off a battery, you're lost, bud, because they're talking about fire, electricity, electrons. Listen to this guy's theory. He said the dissimilar atmospheres, auras of the metals, of dissimilar metals, especially in color, when placed in a caustic bath and you have an array of them, and you put a plate across, short circuit all of them, you have something they call equals fire. His theory is the electron shell theory today, man. What the hell was this guy drinking, man, in Italy, 1700s? Like, wow, bro, I want whatever he's eating, whatever he's drinking. And his battery, to prove that this guy's theory is right on, any car battery you buy today is a voltaic pile, just like he designed it. It's just kind of a little different the way we are, different materials and different, like slightly different arrangement, but like the way geometrically it looks, but it's all piled up based on his concept. That's it. And this atmosphere, when he said when you put it in this caustic bath, it now can flow, right? And it creates fire, which now these guys will take it today. You're going to not mention Alessandro Volta, and they'll tell you it's the electron flow around the wire or around this metallic plates because the chemical reaction, and they'll give you why it happens in acid, negative, and all blah, blah, blah. Boom. Back to Alessandro Volta. He was correct. Okay? This atmosphere flows now. This is now, because that's what we're saying too with our fabric. But what these guys missed is they imagined that this atmosphere as ball bearings, vapor, just floating around everything, right? Everything's got an or, which it does, an infrared, correct. But it's not ball bearings. It's a fabric that's connected to everything. That's what they missed. It's a three-dimensional fiber that appears at the end of the fiber as it's a ball bearing, kind of, because it's moving, it's kind of vibrating around, but it has absolute quantas and discrete steps in three-dimensional space where we live in, just all around you. And this is where you take Alessandro, refine it with Faraday right after him, 1700 still, and these guys built our world, man. We live on their backs. Their discoveries, just a few men, like 10 guys or 20 guys, that's it. Built everything. That's it. And yeah, and after that, of course, Faraday.
Huge leaps around, 1800s, early 1900s.
Man.
Like huge.
Enormous scientific leap throughs to discovery. They
and
set up a mile-long...
we've had technological advances, right? But as far as the propulsion or electric, we've had such little advancement in those areas since their time.
You think these guys didn't have it easy, my friend? Franklin, which was replicating Faraday's stuff, because the scientists were like, there is no way. Electricity, it's not even voice, but the physicists, because they deal with physical substance. There's no way you can transmit electricity through a conductor, there's no way. What are you talking about? Early in the days. What they set up? They set up a mile-long line of humans in town, people holding each other's hands. And with the other end, they discharged a Leyden jar, something called a Leyden jar. If you guys are familiar, of course, with electricity, you know what I'm talking about, is a capacitor. The earliest form of capacitor is made out of jars because, remember, glass is an insulator will hold charge. Absolutely. These guys knew that. 1700s. Franklin almost died with one, which I have. Same here when I was 10 years old. So I love Benji. Our lives correlate. I got zapped by a capacitor that blew me backwards. So did he. And his report, he said he flew back about 6 yards or something roughly, and I believe it. So I don't know how he lived after that because he was playing with a really big Leyden jar. He said, and he touched it. Just in the early days. Hey, look, he lived to tell us about it, which is phenomenal because that was too big of a capacitor. So what they did, town discharge capacitor, one end of the line, everybody felt it. At that point, this proved all the physics wrong. Absolutely. Electricity can't be transmitted down the line. What are you talking about? Everybody felt it. Everybody said, yeah, done. And now it was thought of to be instantaneous because everybody felt it at the same time. However, the guy up front would have the most intensity. The first guy on the Lightning jar would get the highest voltage because the voltage will decrease as it goes down. But everybody felt it at the same time. But the guy up front gets the most voltage, so feels it the most. But yeah, so that's the early days of the newspapers, man. It's crazy when you take a look at this stuff. It's amazing. It's amazing. You're just like, wow. The physicists opposed them. The same exact enemies were there from day one. The university physicists dudes, which the materialists, right? It's crazy with the electrical discoveries. It's just resisted all of it.
Sorry, I was helping my duck. Yeah. Crazy that what they were messing around with and getting blown off your feet 6 yards. I've seen somebody pretty much get blown out of their shoes accidentally touching large electrical circuits within. I used to work at a car wash back in the day, and all of our equipment in the back room, we would have these huge lines coming in for specific pieces of equipment and stuff. We'd have this one electrical circuit box where it was like sometimes you would have to reset the breaker, but it was these huge breakers with just enormous wires coming into these things, and there'd be like one little square barely the size of your finger that you would have to go in and you would have to push that to reset it. And just opening that box was the scariest thing in the world. And one of our managers went in there and he was still holding like a wrench in his hand when he went to go reset the breaker. Dude, wrench hit. I don't even think it hit a wire. I think it just got close enough to arc it. And dude, like, shot back against the wall. Crazy.
Mm-hmm. There's a lot of reports of this on DC Navy ships in the early days before they discovered what was going on. Especially, it's so dangerous, especially DC. When you open the circuit, when you have a high load, big motor, whatever, got a lot of stuff loaded up on the generator, and you open the switch. Oh my God, everybody died. Like this stuff killed everybody that opened the switch in the early days. You open that switch on that ship, you're dead, man. Then they installed a resistor to snuff it out. And that was the key, is that all the magnetism that's stored right around the wires from the current flow down the lines from the generator. When you open it up, well, it's like an inductor, right? It's going to collapse back on itself. So when it collapses, it induces electric charge. So when it does that, now you got these, like, electricity shoots out the end, discharge touches the other end. Screw you, bud. I bypassed your that's if it doesn't latch onto you. If you latch it onto you, you're dead. And if you're lucky to make it alive, it'll grab the other end of the wire and it'll just blast a hole somewhere in the transformer, in the winding. It'll usually find a way out. The energy will go somewhere. It'll just blast the material out of its physical space, and you'll see a nice big burn hole chunk missing. Material, just some of it turns to vapor from the heat. Well, yeah, a lot of people died, man. Still dangerous on big, like, DC motors. But now we know the contactors, like the switch, those are big snuffing resistors. We understand this now. But we didn't back in the DC days. And that's how we started DC. And stuff would kill people. Stuff had a mind of its own. Just didn't understand what was going on. This discharge, right? When you open this, so remember our counter. This is where Steinmetz comes in, right? So this is like chat, that side chat between you and I. Globy's like, hopefully they don't hear anything about this. So this is non-Glober talk. So remember our counterspatial inward sort of lightning discharge.
Yeah.
So this
Square
would
root
give
of
a
-1.
rise. Yeah, this would give rise to parasitic currents that go in and out, like, of time. They don't appear in our meters. That's what Mr. Steinmetz talks about and discovers. These parasitic loads are they're transient. They change with respect to time. They're not constant. Can't read them, right? So they would come in when you, especially when you open up this discharge to counter space, this portal. When you strip an electron out, we call it like the demons come out. It also gives rise to a parasitic load. Demons that hop onto the circuit and blow something in the circuit. But he was, he was tasked by GE to snuff out the demons, and he did. He figured it out. It's the parasitic loads. But man, it's a lot of money. But he's just a genius on another level. So he refined electricity to actually what we understand it today. Like, so he's where the good old age kind of left off. That's it. After that, done. Electrical research, mathematical. Someone else take his work and carry where he left off, which was into talking about the fabric itself. Now,
Yep.
the speed of propagation of where this magnetic fabric has to come from, and stuff like that, and all that. And this is where it's essentially quantum mechanics. Now we're going to really try to understand the ether. What is this stuff, man? Because now it's like he snuffed it out. He understood it enough to actually deal with stuff that was in the invisible electricity was changing with respect to time. It's coming into the circuit and just disappearing, and you can't really catch onto it with your meters. So he was able to understand it to that degree. So where he left off, where he died, that was the end of this, trying to understand more into the lines of force and the propagation, or when they expand out from the wire. How fast does the magnetic field expand out of the wire or wherever the hell it's coming from when you have electrical flow? And it's a great spot to pick up again. But we haven't had anybody like Steinmetz, of course.
No, well, around the time that he was coming up with these theories and doing a lot of the engineering was around the time that some other gentleman was coming onto the scene.
Yes, the other guy. Yes, I understand who you're talking about. The guy that said Tesla's the smartest guy in the world. Yes, that guy. I understand.
Yep.
And they buffed him. Yeah, and they shined his theory, and his math is trash. Yes, that guy. Correct.
Yep. With his stolen ideas. Yeah.
Yeah. He's a fraud. So. And he's why this electrical domain and this beautiful kind of research kind of gets snuffed out with this terminology, because other experimenters keep on going. Of course, universities and laboratories, they want to get to real things. But man, good luck with the lingo after that point. Because they're going to get wild.
That was the person that came in and ensured that the path became retarded. Yep, I agree.
Yep. That's why back to the corpuscle. You understand the corpuscle quite well. Understand what the electron is. Perhaps we can understand what Philo is onto. Because nobody ever really picks up that trail. There's forums dedicated to that. I just started hopping on there and reading, so we'll see. Because people did get it to work, of course, absolutely, 100%. It's not like he didn't work. He said, "What the difficult takes time, the impossible takes a little bit longer." Mr. Philo, that dude, genius. Love that Philo quote.
Yeah, I was just reading his story.
Philo T. Farnsworth is who you're reading, correct? Oh, Benji. Are you reading about Benji? Mm-hmm. Okay. Yeah. Lighting jar. Yeah, let me know how many feet he flew back. Don't quote me on my number, please. It's fuzzy in my brain.
It wasn't as colorful a telling. It was more about the science side of it.
Okay, no, there's some colorful stories
Yeah.
out there you'll see about the Leyden jar. When he once was experimenting with an extra large one. Brave man, dude. Brave man. Because capacitors, like, they'll kill you because they discharge their electrical potential at once. Depends on the resistance, of course, but unlike a battery, it kind of releases, has a limited amount of current flow will give when the resistance even equals 0, right? It depends on the chemistry and the internal structure of the battery and all that stuff to sell. Capacitors, I mean, with perfect conductors, theoretically, it should be instantaneous, right? Near instantaneous. That's how sharp of a rise you can do with like capacitors. Where it's like it'll dump all this energy in like a nanosecond if you want. You can, because like one of like my lasers I built, that's how it had to be. Capacitors had to discharge that fast in order to be able to laze air or nitrogen. It's the pulse width has to be super sharp and crisp. Can't be too wide. If the pulse is too wide, you won't laze. It has to be narrower than that in order to get the lasing effect with the air. It's just one of my lasers. So it's like that's how you have to control. Like you can control how fast it discharges too when you have a resonant circuit and all that. So capacitors will just dump all their energy at once. So with enough voltage and enough capacitance in it, you're going to the grave with one touch. Boom! And it's done. See it, bud? And if it's big enough, theoretically, you're going to go straight from flesh to vapor. That's how hot you'll get really fast. That's because you can do this on conductors, wires. And Tesla starts here with his exploding wire experiment, where you take a large capacitor and you dump it all at once in a thin wire. And then it just goes from metal to vapor, straight up.
Do you think it's possible that this realm in which we reside in could be somewhat analogous to the conception of a capacitor?
Yeah.
Oh yeah, even on ball Earths, ionosphere and Earth, absolutely, for sure, absolutely. There's no way around this. We got capacitor plates, sky and Earth, for sure. We have charge between them. MIT demo right quick of the exploding wire, old Tesla experiment where discovers all this phenomenal stuff, white fire and all this Montreal and I were talking about earlier. So theirs just turned into liquid, or some vapor, but more juice. They need bigger capacitors, more capacitors, add more capacitors. But you'll see how the wires just go straight to just liquid, and it just cools off as it goes into the air. And I can't believe that you guys aren't bored with electricity, man. Damn, no one is resisting the flow. That's crazy.
Yeah, we have no electrical resistance.
Gold, then. You guys are gold, I guess, or silver.
High
Good.
capacitance, low resistance. What's going on? I don't know.
Oh, I was going to tell you guys something phenomenal in the theoretical world of Narnia, which we don't exist. However, this is the idea, and then this does happen, but because of resistance, it gets chewed up. So remember the capacitor inductor conjugate relationship I told you about? This one stores magnetism. This one stores electricity.
Right.
So an inductor is fully charged when the circuit is closed. Okay. All right. And when you open it up, it's gonna the magnetic field around it is gonna collapse, and now it's going to give you electricity. That's how it stores it in the magnetic field. And when you open up the circuit, it collapses, and it's going to give you electricity out of the two ends of the wire. Okay, the coil.
So it's like
essentially.
the Leyden jar, basically.
No, an inductor looks like a coil. It's just a coil with a core, with like an iron core or
Well,
something. It can have air core is
because it was
fine.
storing electricity, but then when the circuit was opened, it leached out all that it had, basically.
Well, I'm about to explain the capacitor, right? Because the capacitor is the other way around. Capacitor is
Right.
fully charged when it's open circuited. It will hold the full charge. When you close the circuit, it will discharge into 0 volts. It will dump everything when you close the circuit, right? To charge the inductor, of course, we close the circuit to charge the capacitor, charge it up. And when you open it up, it holds maximum charge and it will hold it there, right? For the inductor to hold it there, the circuit must be closed. When you open it, it releases it. But when you open the capacitor, that's where it holds onto it now. And when you hook up something onto it now, a load like a bulb or something, now it'll discharge it. Okay, so if in the perfect world, wires made out of perfectanium or something like that, right? No electrical resistance whatsoever. I'm going to make my inductor out of that. I'm going to make my capacitor plates out of that. So I have a capacitor on one hand, inductor on another. I'm going to charge up my inductor or capacitor. I can do either or. Let's go capacitor, charge it up, light and jar. Perfect material, no electrical resistance, light and jar. I need an insulator though, so I chose an insulator which does to hold the charge. Charged up my light and jar. Grab my inductor, which is just a coil of wire bunched up like a coil. It can have an air core, doesn't have to have an iron core. Iron core ones have more inductance, more magnetic capacitance, more So when I discharge / close circuit the inductor with the two ends of the capacitor wires, the leads, what's going to happen is the capacitor is going to dump its energy down these two wires, right? Or the one wire, I'm sorry, with the two ends, yeah? So once we do that, remember what happens when we have electrical flow? It gives rise to what? Magnetism, right? So a magnetic field is going to appear now and charge the inductor, okay? And now because the capacitor has discharged and the inductor is charged up, okay, and the capacitor discharged, the field is going to collapse and induce a current flow down to the capacitor. It's going to charge the capacitor, and the capacitor is now going to dump it back, and lo and behold, we have the LC circuit, the LC resonant circuit. You can look it up, look up the equations, and thanks to Oliver Heaviside, of course. The LC circuit, all this is due to Mr. Captain Oliver Heaviside. But this is the resonant circuit which you can build using an inductor and a capacitor. You can use it to a resonant, you can time the bounce between the inductor and the capacitor based on the values you can work out from the equations. Simple Googling. But now we've created a resonant circuit, and if our materials did not chew up the electrical flow, it would resonate, do this bounce forever. But the idea here is how one stores the opposite. One stores one half of the whole picture, and the other one stores the other half. And together, they create the full thing that we use today, which is electrical flow, which is power. And that's what we need to move things, illuminate things, refrigerate, all this stuff. Electrical flow. We need power. So the flow, of course, of electricity from the Leyden jar created the magnetic field, but it wasn't, because it didn't charge it. It didn't hold any magnetism. But now connected to an inductor, and because now the inductor, can hold the magnetic field, it will store it, then discharge it, charging the capacitor. And this is, like I said, this is called the LC circuit in electronics. And I've just introduced you to class, not first semester, this is not DC, this is AC resonant circuit stuff. So 102 electricity, 102. There you go. Welcome to the club. But I took you by the hand with a simple geometric concept, because that's all it is. And based on these geometric values of the physical substance, we're going to actually derive all how they work and how they resonate with each other, how they bounce the electric current back and forth. So, because the resistance and all that depends on the internal arrangement of the metal that you're using for the conductor. And this is where morphology and all this chemistry is tied. It's all together, together, nature. And that's what because I like philosophy of Goethe, because he said the scientists of today they just take things apart and they dissect into smaller and smaller pieces, missing the totality of the overall picture. He said the proper science would be there are times to where you go in and dissect, and then once you understand something, you must assemble the picture to understand everything in totality. And the problem with everybody here today, the quantum mechanics, the guys, everybody, they're too specialized, so they only dig in, and that's more like deep thinking versus what Tesla said, clear thinking. Because Tesla also liked Goethe, and this is where like this, I love like that's the philosophy you have to follow, I think, to understand nature, the two sides of the coin. Use the male science to dissect and break things down, understand, rewind, reassemble, now put together the knowledge and go forward, right? If you can't do that, you're onto the wrong trail. Science is incorrect. Your theory is incorrect. That's why Einstein is incorrect, because you can't assemble his stuff into anything. His dissection is wrong. So that's Goethe's like philosophy into science and natural science. That's how it should be. You dissect, then you reassemble to see everything, what you've just learned. These guys don't do that with any of the fields, really. They stay specialized in their realm, and that's it. That's all they do.
It's almost like they don't truly test what was taught before, right? Or what was told before. They don't actually challenge it. They just kind of go with it.
Well, I think Einstein put him down the wrong freaking path, right? Like he took the dissection, right? Compartmentalized everything, put it into frames, right? And when you can change to each individual frame and come up with different results, you're never gonna put the parts back together, like you're saying, and get a full picture. I mean, we have people that come in this server talking about the physical interactions changing, like what's physically taking place changing depending on how you view it, or your reference frame, or the reference frame of some inanimate object that lacks the ability of perception and knows nothing of how to perceive the world around it. It just knows how to react within the world.
I like the double slit experiment, right? How light reacts, or how, I don't want to say how light reacts to that, just how light acts while you're doing that.
Yeah, I mean, it's not, I don't know.
Well, I mean, remember our electron gun?
Mm-hmm.
Yeah. Just imagine a laser as a photon gun, but it doesn't give a shit about the air. But boom, right, drills right through it. Okay, I don't care, because electrons do in the air, like molecules are in the way. Light is like, you know what, air, I kind of don't care. However, it will scatter like the blue light, so it does affect, right? Like the sun, you can observe the sun when it's far away in the horizon. So you do have a lot of air in between, for sure. Just have air vapor and becomes more orange. So that's a good theory. I love the scattering of the blue light because it's shorter in wavelength, even though it's higher in energy because it's shorter wavelength. Yeah, and shorter like wave radio comms that do the same thing, right? So it's kind of interesting. And the long waves that we propagate them easier further around the Earth. Short wave, really short wave, is for local communications. The shorter it is, the more local kind of it is. So yeah, it's kind of interesting, right? And that's why 5G and our millimeter wave, like the millimeter band that we're on for the wavelength, we need a lot of repeaters, because we have the same exact issue we have like with UV, right? Or blue light. As you step up in frequency, the wavelength gets shorter. So you gain it's a balance, right? So you gain stuff and you lose stuff, right? So you'll gain energy, but you'll lose distance because it gets bounced off stuff easier, and some of it then you'll gain penetration power too, but only for a short distance, not for long distance. Long waves are you just need one antenna. You can send the signal to like halfway around the Earth with just at home, on a different band, but not on a millimeter band. You'd need so much you need crazy power. But you see, so it's like the lower wavelength or the longer waves, which are slower in frequency, lower in frequency, travel further easier.
This LC circuit is really interesting. I was just gonna ask if it could be used to like detect certain wavelengths, basically, different energy amounts. If it
you can use it in so much stuff.
Yeah, it says storing energy oscillating at the circuit's resonant frequency, and sure enough, it says if you a tuned circuit of the shortwave radio transmitter, output tuned circuit.
Yeah, you can make a small radio at home based on that, either a transmitter or a receiver. Like that's essentially really what you need is the oscillator to be musically tuned, and this is where music is so important. As this bounce ratio. No. This bounce ratio in the transformer is based on the length of the wire, which is the amount of windings we have around the core. And it's just the ratio of the windings will give you the same exact ratio to voltage and amp output. That's it. So it's literally a number of windings and volt per winding. And then the other side, how many windings do you have? If it's 2 to 1 step up or whatever, you know what I mean? Or it would be like a step up would be like 1 to 2 or like 1 to 4 step up or whatever. Just a ratio of windings to windings and volt per winding, and you multiply by the windings. That's it. Nice and easy. So this is where you can take it like high voltage, low current, and then step it down to with at the other end of the transformer would have less windings, and depends however many volts you want to step it down from your beginning. You're like where you start from. You work out the ratio that you want, and you just do that. How many turns, whatever that is, and now you went from high voltage, low current to low voltage and high current. But the amount of power you can extract will be the same, of course, plus/minus the losses. Just heat resistance into the iron core and all that into the wire, of course. But this is electromagnetic induction. And we need alternating currents to do this because we need to collapse the magnetic field around the wire. We do that. When we do that, that happens. The other coil sharing the same core, it will absorb that. So it will resonate back and forth, right? And this musical resonance is the transformers that we have. Every house runs on that, steps down the mains voltage from the line that's suspended on your utility pole down to your panel to, what is it? 2 legs of 120 hot. That's off of the transformer. Just like, what I'm saying? It's a musical device, is what I'm saying. Just essentially the same thing, music, right? The ratios of the division of the wire. That's all it is. Coils to coils. I mean, for the guy that thinks this is bullshit, you can test it out yourself, man. Build a little step-up transformer or step-down transformer. You'll see that this is how you do it. You either pulse DC or AC. You can't do it with DC because you need a magnetic field that's changing in state, and in the change, that's where you get the induction. When it's changing with respect to time, but it must change. It cannot be fixed in magnitude with respect to time. It won't happen. You won't get induction. And that's the whole key in the electrical domain in general, is we're always studying electricity in the phase of change. And when it does move is where we get the effects. No motion, no effects. So we're always, that's why it's hard to study. Because like I did with the owl diagram, I had to take a 2D slice of time of the circuit flowing in time to like freeze. Look, this is what's happening. But this is a three-dimensional thing of super complex double helical waves that are flowing on top of each other. It gets way worse when you dig in. It's like, goodness. Okay, cool. Oh, all right. You know, the quadrupolar nature, like we said. Welcome to the Cyrus monologue, I guess. Everyone is sleeping now. Sorry.
No, you're fine. It's music to my ears.
It is one of my obsessions in life, for sure. Passion, obsession, love. You know, once you got that Leyden jar, experience when you're a 10-year-old kid, you never forget about this stuff. You never forget about it. It's like, man, that really hurt. All right, that's dangerous. So it's always fascinated. It's like, I don't understand what this stuff is.
It's shocking, isn't it?
Yeah. Yeah, man, what do you guys want to talk about? I just don't want to keep on rambling. It's not cool.
Dude, I don't know.
What? Okay, let's see. In your electrical studies, Napalm,
Don't quiz me.
what are you like fuzzy on? What are you like? What's not so
Oh my
clear?
gosh, I've been muted. I don't know how long I've been muted.
Oh yeah, the whole
Don't
time.
quiz me.
Didn't hear a
Got
thing.
What I've been fuzzy on is time to actually devote to investigation.
Yeah.
Yes.
Oh. Gosh. Yeah, I was actually saying that what you're talking about with the AC, it reminds me of women in our cycles. I don't know if you've ever heard that women are like waves.
Oh, totally.
Like,
Lunar cycle.
yeah. If you understand that, then you can take advantage of that if you're a lady.
Oh, I'll
Probably
tell
if you're
you
a man
how
too.
I kind of like this deep etheric dive these days. It's for the stone connect stuff we were talking about, right? And I've actually gotten onto like a frequency band, right? That's why this stuff is really hot in my head these days. So there's personal research into this, but yeah, the nature. This is why I like this. The understanding the nature of this is so crucial to the domain I would like to explore in science. Like in my life, is like I need to understand what this stuff is. Electrical substance. What is this?
Yeah, I agree. Seems important to me. It was always weird to me that they never really taught what all this stuff is. They credit our entire society to it, but they never teach it to us.
They do, but just not this way. Because
Right.
the teachers don't understand it. Teachers
Exactly.
are specialists. I mean, at what level? High school and stuff like that? Oh, they don't have. They're not professors, so they don't really
Right.
know what they're. You know what I mean? Like, you have to pass through that garbage, then to enter a domain of like, oh, we actually don't know. Ha ha ha. Yes, but we're gonna make assumptions and we're gonna carry out. Okay, cool. Okay, learn how to do that. They're gonna teach you how to. At least in the engineering world, physics. They're crackheads. Theoretical physics. from our engineering perspective, like they're madmen. They come to us for help to make stuff for them, then they're just nuts. It's like, come on, bro, make something real now. Stop wasting money. But yeah, that's what the physicist versus engineer sort of thing. We have to make real things for the theoretical experiments that they're doing to maybe their theory is correct or not. So they want wild stuff. Well, like I said, electricity is not the domain of physics, so this is not a study of physics. And that's the mistake that's made. It's not a physical thing. If you attribute like physical properties to it, you're kind of lost. I don't think you'll get too far with that sort of understanding.
I'm just wondering where gin fit into all this.
Yeah, I'm studying essentially their substance, right? That's for religious, like, side research to understand their material, sort of their flesh material.
Right.
Plasmanoids. If you want to translate them into my book of understanding, plasma beings, plasmanoids. Interesting.
Are you guys
Okay.
talking about the Muslim conception of jinn?
Yeah. Beings made out of fire, plasma. Yeah. So it's like, okay, fire, huh? Very interesting. Just happens to be another obsession of mine. It's like I like fire. I like it's interesting, right? Torches and stuff, like hot torches, and plasma, the hottest of fires here. It's like, cool that we have.
Maybe we can only observe it when it's hot.
Well, it's a gas, right? To make a plasma, it's a gas that you get it really excited, and it emits light. So it's this ionized gas concept of what we have. So I don't know if that's actually exactly it. It's probably not, but I don't know. So the more we understand about electricity, I think more of electricity, really. I would call this the fire of electricity, but maybe. I don't know. It's essentially still ionized gas, right? All of it. So it's like, okay. But like electrons, those things we were talking about earlier in a vacuum tube and stuff like that, this cathode ray isn't a plasma. So it's like, it's like, okay, this is interesting now. So yeah, there is like more into this. That's why I like the electrical research, because I found it to be the closest thing that could make me understand what this religious stuff is saying. It's like, oh, okay. And of course, make advanced tubes and stuff like that. So everything, the more knowledge you have, the better.
I just can't help but think about how in the periodic table of elements, all of them are either solids, liquids, or gases at room temperature. But where are the plasmas?
All of those, you can take all of those and crank them up to plasma. It's a matter of temperature, heat. You got enough heat, excite them enough to hot enough temperature, they emit light. Yeah, so you can take all these to, which is, so solid. Let's say we use the worst one, tungsten, highest melting temperature. We use filaments out of it for a reason, because it doesn't do that at white hot heat. It will not just turn into a liquid puddle of molten metal. It won't do that. Tungsten. So tungsten is just gangster, just the bee's knees for temperature resistance. And
Did you just say bee's knees, dude?
That's correct, bro. Tungsten,
Old,
man.
old,
yes, that's right.
old.
I'm pretty old. I'm
Old.
old. How old are you? You're probably Gen Z. That's why. We're boomers here. It's okay, kid. It's fine.
No, dude. Not even boomers say that shit. Like it's a joke. You're decrepit.
Anyways, what we're talking about?
What's the problem with tungsten?
Nothing. It just has a high melting temperature, so it's very useful. Crucible metal. Like you can make
But
a crucible out of it to melt like every other metal. Because it's not going to melt itself, but they'll all melt inside of it before you touch it. It's still holding its structural integrity, molecular structural integrity at white hot heat.
but okay, but get this. Gin don't seem to be hot.
Well, that's different. Yeah, that's kind of taken like that's kind of taking what we're trying to take what we best understand from men and apply it to that. So I don't think we're there. I don't have a full like theory on this yet from like the religious
And
aspect of things.
there could be plasmas that are room temperature.
There's dark plasmas and stuff like that, so you know, it's interesting. Like electrons aren't necessarily hot; they're just moving fast. So
if they
they
were
have a lot
cool,
of
they would
energy.
stay water, right? Because all living things were made with water.
Yeah, living things. Yeah.
Gin are definitely living.
So yeah, I don't know how to make that blend yet. You see, I'm not there. That's why I said I'm not there with that full. So the more I understand about plasma, experimentally, the more I'll understand. But we're not.
Well,
We're
you're
stuck
looking at
still.
like 8
Science
types
sucks
of
right now.
plasma. Weren't you talking about like the 8 types of plasma or something?
For what? Like God?
Yeah, from the
Seven.
7.
Seven. Yeah.
It could be that they're hidden from the table of elements, you know?
That's what I'm saying. It could be we're not even there yet. Like really, we're all these plasma are gaseous plasmas, or you take any metal or any substance to vapor. Okay, where it's in gas now. It's a metallic vapor, and you excite that, and we have like I said, HIDs, which they use metallic salts, sodium, high intensity sodium, bulbs and stuff, high pressure sodium bulbs, HPS, and stuff like it. It's metal. It's a metal plasma that's emitting the light, and some metals emit invisible light. Like mercury will emit ultraviolet. We use that for like sterilizing stuff like that because ultraviolet will sterilize stuff. It will kill all the bacteria and shit. And it's the true ultraviolet, which mercury will emit. You might see a purple glow, but guess what? When you're looking at that like that naked, man, if it's a quartz bulb, because it'll allow the UV to go through, it depends on how many watts your eyes are getting damaged. Bad. Look away. But that purplish glow, just because some of it is near the visible spectrum towards the upper end, but it's true UV is invisible to the eye, like UVC and stuff. Or all the bands of actual ultraviolet, they're all invisible to the naked eye, but they will react with phosphor, like photons and X-rays, and they will excite phosphor. So we know this higher wavelength light that's very close to what we can see will excite like phosphor and stuff like that. So they're pretty energetic, So yeah.
Mm-hmm.
So UV is pretty cool too, because you go UV, X-rays, and then you go up higher in the electromagnetic spectrum. So this is where you go above violet, and life becomes interesting here. And I believe there's other like this is. You'll understand that like the faster we can create oscillations, the more advanced our society is, essentially. Even from like semiconductors, which is computers and stuff like that, silicon, semiconductors, or just which took over from vacuum tube oscillations, which before that there were mechanical oscillations, an alternator on a shaft. Because we are trying to do this, we're trying to create fast oscillations. The faster the oscillations we can create, I think the more we'll understand. They give us just more tools. So yeah. Oscillations, and they kind of, for me, they mark the advancement of humanity. How fast can we oscillate stuff? Because it is a true achievement, actually. So it's a real thing. Hey, Napalm, you there?
Yeah, what's up?
All right. In this pic, that's Farnsworth. Okay. It's a fuser. Okay. Can you guess who? There's someone to the right of that picture he's talking to. Can you guess who it is? The quack of the century. You know, hopefully one day he should be on Time magazine as the label quack of the century. Can you guess who's on the other side of that? They're discussing.
Eric Dollard?
No, quack, bro. He's just mad. He's a crazy guy. But
oh, you mean an
no.
actual quack?
Yeah, an actual quack, actually, like 100% quackery, 101.
Einstein.
100. Yep, correct. That's Einstein. Correct. That's Einstein. Einstein, the other side of the picture.
He looks like a Fed.
That's just people like that from the 30s. That's what they look like. They're just it's an old school look.
Doesn't he though?
Yeah, he does. He's got that look too.
Yeah, it's funny when you said quack of the century. I thought you were talking about what mainstream people would consider a quack.
Yeah. No. The real quack.
Piss drinkers.
Einstein,
real quack,
correct,
then
correct, yeah.
Einstein. But a lot of people eat up the quackery.
Yeah.
Oh, his wife was ultra intelligent too because he gives her credit for the TV tube, the all electronic television tube. He gives her half credit, actually, legit, because there's a lawsuit that follows right with that. And,
Farnsworth?
Yeah. RCA, bro. Try to rob him. Like I said, man, they snuff him out, man. He was a Navy guy, by the way. So you picked up on that. Good job. Correct. That's where he comes out of, right? So he does have like that military background. Ultra smart dude, though.
That's who the character is named after in Futurama. Must be
What's the character's name in Futurama?
Farnsworth.
Oh, really?
Yeah, he's like a super mad scientist guy. He's like the main character's like great ancestor.
Really?
He's not the main character. What are you talking about, Boomer?
I said he's Fry's great ancestor.
That's hilarious. I mean, I've never watched that show, so I had no idea. But I've heard about it. So Farnsworth, interesting. It's probably where it comes from, for sure.
Yeah. Or he's not his ancestor. Sorry, he's his progeny. Just he goes.
Descendant is the better word.
Yeah, descendant.
No, actually, no. He's not his child. Like he's like a relative's child.
Right. True. His brothers. I've watched way too much of that show, to be honest.
Yeah, bro. His family, they still have his notebooks that they've never been published, and Eric is the only one that really got to read them. So.
Oh my gosh, he looks like the latest Doctor in Doctor Who. His last photo. Or not the latest one. The latest one is a woman. Whatever.
That's the TV. That's television. That's the television tube you're staring at. The one he invented.
Really? What year?
Gotcha. Give me a second. Farnsworth electronic film.
And so this time the oscillator is set for imaging. It's not just sound.
So let me see what year he patented this thing.
He must run his fingers through his hair when he thinks. Look at that. I saw on the Flat Earth Telegram, Flat Earth and More Telegram, they're like, if this is the biggest if this is the first camera ever made, pictured here, then who took the picture?
The other camera. It had a twin. It's right around the 30s, like early 30s. So let me read a little bit more to get you an exact date.
Oh yeah, and they claimed it took 24 hours to take the full picture, and there are people in the picture. It's like, I don't think so.
So here,
A 24-hour exposure? It must be a pinhole camera.
1927, September 7th was the first electronic image transmission by file.
Sorry, what year? What year?
1927. First all electronic image, like television signal, which was a simple line, straight line, but
Right.
it wasn't. There's nothing mechanical in it.
Right. It's right before FDR. Great Depression.
So, with all the talk of Tesla and his possible technologies that could be used for harm, right? The death ray, all that kind of stuff, and even the possibility of splitting the atom and the nuclear bomb. Do you think the person who created the biggest weapon ever used on mankind may actually be Philo Farnsworth?
Come on.
Why would it be Philo though?
What do you think one of the biggest weapons used on mankind may be?
That's such a out of like. Come on, man.
Hiroshima, and that's the claim, right?
No.
Nagasaki.
No, not even that.
Come on, you're gonna so the TV is the biggest weapon.
What is it?
It's probably the radio.
The television.
No, the radio, dumbass.
Dude, why am I talking to you? Was that question to you?
Yeah.
You must be a Glober. We were doing good for a few hours. They were coming in and just dipping out because we were having an intelligent conversation, and then here we go. Welcome back, Cyrus.
It's good to be back. It's all gravy. It's like, hey, when I'm like in serious discussions, just like, hey, bud, listen, man, stay out of my capacitor, my vacuum tube. I have no space for this quark. Sorry, the quark's out.
The quark stops.
I'm trying to figure out, man, like where, like, to pick up the research where this ended off, because it's not difficult. And with Tesla's and Philo, is like that's the keys, and like these other currents have different phenomena. So now we need to take him to the tube, right? We really do, and it appears that Philo, I think, is the guy that was able to do it, man. So, like the splitting and all that, I'm trying to understand that, because when you read into that, it's always from their domain, from their angle of things. So it becomes but as long as like you keep track of the fundamentals, you can understand what they're saying. You can decipher what they're saying.
Yeah, from where does that release of what we would consider energy come from within that process?
Like byproduct, let's say fire
Yeah.
or oxidation, exothermic. Yeah,
Ah.
oxygen attacking a fuel will give you byproducts like if that oxidized whatever hydrocarbons, and also heat. You know, if it's hot enough, it will create plasma around it from the envelope around it. Now you have a flame. If you have enough heat to ionize that area around it to give it that beautiful plasma glow, which you call fire, which just gives off light, which is like what they're saying is that's when the electrons, right, in this cloud of gas is super excited electrically too, right? Anyways, but because you can do this with heat input or electrical input to cause heat, right? But when they're excited like that, they're saying when they cool off or when they drop in orbital, in modern like terminology, right? That's when it squeezes out a photon, and now it squeezes out light. So it's like light is like a byproduct of an electron dropping in energy orbital levels, if I'm not mistaken. So, and it's cool mathematics because you can take this and lasers and stuff like that. So it's not bad to understand it the way that they're saying it is. It's cool, not bad. Because essentially, remember this electron, remember, coming out of the cathode ray tube, this electrical quantity. So we're cool as charge and stuff like that. It's cool. It works. I'm down with that. Just see what you can make out of it. If you can't make shit out of it, toss it in the trash. If you can't, cool. Just follow that. Just conceptual math. Why not? Perhaps it doesn't look exactly like that, but just why not? So it's cool. So yeah, the like matter and electricity since day one, since the 1900s until today, is essentially what we're talking about. Even with the quantum field, like their theories, the dipoles, fluctuations of the dipoles. Which is there anything there fluctuating? Absolutely not. It's just potential, charge potential. Fluctuating, positive, negative, or rotating. It's like, oh, cool. Okay. And this does that, and it's a cool theory. I appreciate it, and it kind of ties into my understanding of everything. Why not? Sounds pretty cool. Well, maybe it's right, maybe it's wrong, but we'll see. But it kind of gives me more understanding into the fundamentals of electricity and morphology.
Yeah, it's fascinating.
Yeah, I knew at some point. I knew I would have to go beyond my teacher, Eric. Like I know, I have to go where the professor hates, the photons. I understand. But with that, which the knowledge he gave us to go read the classics, you can easily enter that realm and you'll understand their quackery from non-quackery, and take that which benefits you in your journey to whatever you want to understand in life. I have my stuff I want to understand. I am just compiling true bits and pieces to the whole picture, and we'll see one day, right before I die, what I understood. We'll see. It's an ongoing journey of refining the puzzle that you're picking up. All of this I was wrong here. Oh shit, I made a mistake here. Oops, and then put the right knowledge and all that. Refine the tapestry or the painting, sculpture, so on. So Napalm.
Yep.
Ultra nerd talk, deep level. To summarize the gazillion-dollar fusion nutheads, because they're using magnetic confinement. Crazy nutheads. Philo in the Technilim jar, he used electric confinement, and you can absolutely get neutron counts right off of that thing. So 100% works. But they used what's called something electrical confinement. And I'll look it up, inertial or something like that. I'll look it up. But that's the difference between a smart wizard and he, literally billions of dollars, and this guy's got a glass jar, got the same effect. So crazy.
Yeah, because gotcha. So he's using electrical confinement with the glass, right? The glass is the containment. Is that what you're
The
saying?
glass is just for the vacuum apparatus. You can replace it with stainless steel glass so we can see what's going on kind of with the plasma.
Can't use steel.
You stainless, yeah. Stainless steel.
No, you can't.
100%. It's all stainless steel construction. Okay, I'll show you.
Don't look like glass to me.
Man, wow, these real photos on the inside. Goodness. This donut chamber looks like it's got a lot of metal on the inside. Oh, and LEDs to see too. Wow. Do maintenance on it. Yeah, these are real donut reactors that use magnetic confinement. They're not. Philo's electric. I'll show you Philos.
By the way, these are also devices that many times people will send when you ask for like pressure, gas pressure without a container. Ironically. They'll send these fusion chambers. Like, look.
Here's some teenagers building it in their garage, the Philo, because again, you can build it for $100. Now, all you would need to get fusion now is introduce deuterium, a fuel. You just crank it up, and you better have some. You better understand what you're doing at that point, and you got your safety gear and neutron counters and stuff like that, because that's how you're going to know that you actually achieved fusion. The neutrons start getting spit out of the reaction. So once you start getting neutron hits, it's like, you're achieving. So now, like, the idea is to get free energy out of this. Essentially, it's a long story short. All this Philo and the other guys are for energy. This is for energy research, for electricity for free. It's like, or very
there's
cheap.
some over unity within that, right?
That's
the
the idea,
possibility.
yes. Correct. Mainstream does not deny that.
Yeah, it's like harnessing the usefulness of it, right?
Well, if you think about it, bro, we're really we're dealing with counter space. If you really think of what's going on here, right? Yeah. We're doing with, you know what I'm saying? It's counter spatial elements in our dictionary of terms. So yeah, perhaps it is correct. You can do this with material when you enter the counter spatial world of it. Maybe you can actually extract more energy out. So mainstream says you can, yeah.
The math works. How do you tap into it?
Philo. Dude, I'm telling you, there's a lot of replications of this as I scroll through, like, just the internet. Like, the Philo, a lot of people know about Philo's fuse. There's patents out there. And, like, the one I posted, this is a refined, I forgot, other guy, his lab partner, built the grid. The idea of the hollow grid, which really simplified construction. Absolutely, people got reactions out of these, So you want to see, because universities do around the world actually work on this. This is a real file. This is something more legit. This again, Philos. This is other people working on Philos, more professional, not people with even though he was working on a glass jar. The guy said you can't use what? Stainless? I'm sorry? Can't use steel, huh? Vacuum chambers are made out of, stainless, man. 304. Because we don't use other metals because of off-gassing.
You can make a vacuum chamber out of stainless steel. What are you doing inside the vacuum chamber is what makes you decide whether you're going to use stainless steel. What are you attempting to accomplish here?
Oh, we're talking about fusers, bro. So we're into
for making fusion?
Yeah, but this is electrical fusion from Philo Farnsworth. We're talking about the inventor of the TV, what he came up with. Different sort of fusion, but similar. Just the confinement method is different.
How'd you get on that topic?
Vacuum tubes, electricity. Ended up here, pretty much. Morphology, electron, photon, proton, neutron now, of course. So that's what we're really just kind of...
Quantum, ether, all that fun stuff.
Yeah, people are enjoying it, so why not? The minute people tell me, "Yeah, you've been talking for like 3 hours, shut the fuck up," I'll shut up. And I'm down. Like, I've been talking a lot. I know. I just love the history of this, man. It's so exciting. Because the people that are really dedicated their lives into the work of Philo, they truly believe any guy can actually at home break through this. Because look at the stuff that I'm posting, man. Like, look how you can get super expensive, sophisticated stainless, or you got people in glass jars, and even Philo doing it in a simple apparatus, right? So, and the fantastic story is here. The tubes that no man has seen except Eric, because his family's got the collection. And this is Eric's phenomenal story that I only understood now what he was talking about after I understood more into the science and like radioactivity and stuff like that, because of the brown chocolate charring on the glass. And anyway, so it was whatever they're drinking and whatever, huffing and puffing. Everybody's it's its own cool stories and all that. Electrical, nerd stories. And so Philo busts out a box of tubes. He was like, "If you're so smart, tell me what this tube is." Right? And he gives him this tube, and Eric was talking about it. It was like it had really thin wires, anode, cathode, so he knew immediately it ran on really high voltages because how thin the leads were. So really thin leads, and it had the evacuation stem was broken off, so it was just a prototype like laboratory tube where it just hooked up to the pump, and it just had simple. I think it was just two concave like anode cathode. And just super simple, nothing complicated. Just a concave anode, I think concave cathode facing each other in a tube, and an evacuated envelope. We don't know exactly what gas is in there, but Dollard notices the chocolate brown coating on the outside of the tube, and we understand why that happens in tubes, right? On like to the glass itself. Right, so Eric was like, something took off in this tube, some reaction, some nuclear reaction, or had a lot of radioactivity coming out of it. It was charring the glass, this chocolate brown stuff. So he said, his son, another Philo, of course. He's like, he stopped laughing at that point, and then he had free access to all his his dad's notebooks and all that, and just free access to take a look at all the tubes and stuff like that. So there are tubes where he did succeed, and obviously from the browning of the glass, it was sustainable for a little bit, like over time. And that's what his son said. When they would turn off the electricity, after they got the reaction going, the reaction would keep going for a little bit before it gets snuffed out. So when they achieved the holy grail, and then just simple glass tube, which was crazy. So we don't know the rest of the circuitry behind it and what gas they had and all that, what they were feeding into it. But That's the cool, phenomenal story of Philo, where the trail ends, really. And then people pick up the trail, and there's forums, like I said, people dedicated to this. They really believe that's the way.
Philo, huh?
Yeah, the man who knew what the electron was. True inventor of TV.
Is Dollar still alive?
Yeah, his health isn't too good right now, though. But yeah, he's around. He's pretty bitter now. Gave up on
Oh,
mankind. Yeah,
I feel
not
like
the
he's
same
been
Eric, you know. From
bitter for decades, though, hasn't he?
yeah, but you know, back in old lectures, you can see like he had more life into him, right? But I guess the consistent harassment from Commonweal, I guess, with the research he was working on, they're like, no, man, you're gonna harass him for life. He's a true genius. You can't let him. Cannot. You know, no way. Everything he said checked out. That's the crazy part, man. And he doesn't spec you. You tell him, hey, what if I do this? And they'll be like, go try it and see and let me know, man. It's like he's got no time to speculate for you. He will not combine technologies and build it in his head and tell you what he thinks it might do. He's like, go do it and let me know, man. I don't have time for that shit. So he's just reporting the history because he knows there's critical information there for someone to take it in the future and actually carry on. Where the Einsteiners just they went into the abyss with their math. And that's the end of the lecture of Ether Physics 101. We'll pick it up tomorrow with 102.
Who are you talking about?
Farnsworth.
Physics. We're talking about physics, bro.
I know. Who in particular were you talking about? I wasn't paying attention.
Philo T. Farnsworth.
And Eric P. Dollard and Nikola Tesla and Charles Proteus Steinmetz. It's been a long conversation.
J.J. Thompson. Who else?
Heaviside Maxwell.
Yeah, Rontgen. There's a lot of people, man. Heaviside. It's a good combo. Electrons, electron charge stuff.
Remotely.
Trying to understand the subatomic nature.
Jerry Vassilanos.
Jerry. I was just trying to my intention was to shed more light upon the subject of electrons, protons, and stuff like that, so they don't get as much hate. These corpuscles kind of hurts my heart from just the flat Earth community in general hates on these things. Where man, really helped us. They helped us out, like the knowledge, you know.
Yeah, it's not that it gets hated on. It's just like, yeah, you can think of it that way, but why don't we just think of it in the terms or whatever that it is more likely to be, right? I don't know.
I mean, it is the corpuscle just renamed it, just ended up being named electron. So
Right.
I'm cool with that, you know.
But the problem is the average person does not relate it to what it actually is, which is why there's not as many people thinking on specific paths. Let's just put it that way. because I think that in their mind's eye, what's taking place is actually, though useful, not necessarily as accurate.
Yeah, I would say when it comes to like modeling the physicality of the non-physical, of course, this is where you're gonna have speculation. But some stuff is pretty good with it though, like the ratios and some. I like that.
Yeah, yeah. Well, see, most of the time, do people think of it in terms of ratios, or do they think it more in terms of, well, quantity? If that would be the antithesis, I don't know.
Yeah, it was because of the nucleus, the protons. So they thought of it as ratios too, like the harmonic regression. So it's like this is where it's like it's kind of so interesting, man. And the way they predicted, I was like, wow, okay, cool. So maybe the math, like it's okay. They are dealing with invisible stuff, but they're figuring stuff out, so it's cool. You know,
Right, because you
I'll
can
just take
measure
what they
the
figure out.
effects, right? Like,
Yeah.
you know that you have a harmonic point on the neck of a guitar just above a specific fret, right? Where you don't even have to push down on the string, you just have to mute the string, but it'll still give you a harmony. And then you know that there's a specific ratio to where that's going to take place again, dependent upon the size and the length of the string, right?
Exactly. And based on like the electron proton stuff, now we can predict this should have this and that. Right.
Yeah.
This many. It should weigh. It should weigh this much. We'll see if we can find it in nature. Isolate it.
So let's go look at this particular wavelength or vibration, and oh, looks like we found what we're looking for. Oh, you DM'd me the other day, Cyrus. You don't have to speak about it, but did you ever get
Oh
that
yeah,
taken care of?
yeah. It wasn't big. He just wanted like something he posted a long time ago, like a sky scanner or something like that. So that was nothing serious.
Oh, probably the oh yeah, okay. The specific points in the sky where all of the meteorites or meteors originate from. Is that what you're talking about?
No, it was some sort of a scan that showed like the sky more like a pyramid or something like that with the size. I forgot what it was, man. That's why I
Yeah,
think
but I
he
thought that
had
was
it. Was
I
it?
thought that was based off of the
Was it? Oh, I don't know anything
anyways.
about it. That's why. Okay, yeah, that's why I thought he had it. I've got no idea what it was. So I remember he talked about it.
Yeah, it's basically like I want to say it's 3 specific points in the sky in which all this phenomenon originates from, and kind of putting together the picture of that gives you some type of what appears as though a pyramidal structure kind of thing.
Right. It was that one. Yeah, that's the one you wanted.
Yeah.
If you got it, yeah, shoot me a DM if you got anything on that.
No, I don't. I just remember him talking about it a long time ago. Don't think I have the information on it.
Okay.
Your hot mic, pumpkin.
I know. I'm sorry.
Oh no, it's alright. I just want to make sure you're not gonna say some shit.
No.
Alright.
What can she say that we can't hear? We shouldn't hear.
What right has she to any privacy?
Yeah.
She left her mic open.
I mean, sometimes people can like legit dox themselves if they don't realize that their mic's open. You know.
Right. Exactly.
Yeah, I did sex on open mic once. So what?
What? We don't want to know about that stuff, Jakey. Come on.
Well, I did let you know. So the guys giggled in the background. Then that's it.
So yeah, hey, Cyrus, appreciate
PC too far.
What's up, bro?
I just want to say I appreciate the talk tonight, man. Good hearing from you as usual.
Oh, for sure, bro. I enjoyed it, man.
Yeah, I
It's
gotta.
good. It's good summarizing this stuff up. Like, helps me, like, understand more.
Dude, the more you talk about things, right, the more the things in your head come out through your mouth. The better it is for you to comprehend it and or continue to have realizations as it comes through your mouth and over your lips. Yeah.
Yeah, it's a
Yeah,
chance cycle.
I
And
noticed
when you
that.
and when you have to explain something to somebody, it helps you think in a way that's hard to repeat after the first time you've learned it.
Yep. But I'm gonna call it a night. It's getting late on the East Coast. So
All right.
Sorry,
go
so
ahead.
you
Have a good night, dude.
want to continue this in my
Oh,
server?
sure, yeah. Yeah. Let's go. All right, guys. You guys have a good one. I head out. Peace.